We should have put the music on. It's been quite a journey, and we will wrap up today with more of an extragalactic focus. And I can't see because I don't have my glasses on. We'll go from stellar populations and star formation in the nearby universe back out to a more distant focus on black holes, AGNs, and quasars. And then even further out, let's see. Yeah. With the AGN in the second session, it's really closer by AGN. And then galaxy evolution and galaxy clusters with some cosmology sprinkled in. So just a few announcements. Reminder that for speakers, come up during the Q&A to get mic'd up. We will have an addition to the end of the morning session. We'll have additional poster flash talks then. And the posters will be up until the end of the day. For those online, I think there's also a message in the Slack. We will have the virtual conference photo then. So please be around to unmute your video so we can take some screenshots there. And two other announcements. There have been questions about getting to the airport, sharing rides. Please go on the Slack on the general channel if you are looking to share a ride on a taxi and to exchange information about how long it's going to take to get back to the airport from here. And then finally, our panel discussion, you don't want to miss that. That's at the end, and the folks who will be involved in the panel discussion will be representing all parts of the partnership. We will be getting together at lunch to prepare for the final discussion. And I think with that, I'm going to look around to see if there are any other announcements from the LOC. Anything? No, you're not, but. Okay, shall we get going? Okay.
So thank you, Janice. Good morning, everyone. Welcome to the second session on stellar populations and star formation. My name is Thiago Gonçalves. I'm a professor at the Valongo Observatory at the Federal University in Rio, Brazil. I'll be chairing the session along with Clara Martinez Vasquez, who's the virtual chair for the session here. And we'll start with Fabio Pfeiffer from Universidad Nacional de La Plata. He will talk about, he has an invited talk on the globular clusters in early type galaxies. So Fabio, thank you very much. And you have 20 minutes for your talk.
Okay, hello, I'm Fabio Pfeiffer. And these people listed here in the slide are the people who work in our group in the Instituto de Astrofísica de La Plata in Argentina. Okay, this talk is about massive early type galaxies. That galaxies is located in the left hand of this diagram, and here I list just some few of the most basic property of these galaxies in contraposition with the late type galaxies which locate on this side. So this figure show in a very schematic way the difference between the stellar population of this kind of galaxies. Early type galaxies form their stars very quickly and early in time. Okay, since the work of Tumre in 1972, we know that the interactions and the fusion between galaxies can transform the morphology of this object. However, we know that the idealized view of most of the massive early type galaxies forming by the binary merger of these galaxies is not always correct. This is a more realistic view of the process of ensemble of this kind of galaxies, where the the stars in the movie are the minor mergers. So since the work of Osser, we think that the massive early type galaxy formed in a process of two phases. The first phase is an in situ phase, which consists of an early collapse of gas and a giant burst of stellar formation. After that, we have another phase, the accretion phase, which consists of the later accretion of material that build up the stellar and dark matter halo. We think that the global cluster systems of this galaxy form in the same way. In the first phase, the red globular clusters, the metal-rich globular clusters are formed, and some blue or metal-poor globular cluster too. And in the second phase, most of the blue globular clusters are accreted along with the low-mass satellites. Okay, we started the program to study several examples of early type galaxies in the nearby universe, which show strong evidence of fusions of interaction. I will tell you about these three objects. The first example is NGC 4382, which is a galaxy, an early type galaxy in the outskirts of the Virgo clusters. It is the distance of around 18 megaparsecs, and it shows several structures that show that this object is a merger remnant. Okay, regarding the globular clusters of this galaxy, there are several previous studies. For example, Peng et al. Proposed that this galaxy is a good example of a possible three-modal color distribution. Three-modal color distribution. Santos proposed that this object have blue young clusters, and more recently, Trancho obtained near photometry for a small sample in the center of this galaxy, and they estimate an age is about 1.8 gigayears. And finally, Co obtained a GMOS mask for a small sample in this galaxy, and they found a group of globular clusters with ages between 2 to 4 gigayears. And they estimate a total population of 1,200 globular clusters, which mean a specific frequency of around 1.4, which is very low for a massive elliptical galaxy. You can see here the color distribution of this galaxy in black, and I will plot the color distribution for other two early type galaxies from Virgo, and you can see that the color distribution are really different. In this case, we don't see the typical bimodality, and it's clear here the presence of intermediate color globular clusters. In order to check if this is a correct interpretation, we run the two-dimensional Gaussian mixture modeling of Nedin, and we obtain that this globular cluster system is composed by 4 subpopulations: the classic blue globular cluster, the classic red globular clusters, an intermediate color group of globular clusters, and another group, the reddish object that we usually found in S0 galaxy. The name of that cluster is Fine Fuzzy cluster. Okay, we obtain one GMOS mask for this galaxy, and we add the sample of course, so we have now 47 globular clusters in this galaxy, and we use the ULIS code to obtain age and metallicity for these globular clusters, and we can see which could be the old red globular clusters here and the old blue globular cluster here, and a lot of young globular cluster here. And it's interesting to note that the youngest globular clusters are the most metal-rich one. This is another plot when I show you the alpha to iron values, we can see that the young globular cluster here show values from suprasolar to solar. So that means that the globular cluster were formed from progressively enriched material. Okay, we study long slit spectra of this galaxy, and you can see here the presence of the kinematically decoupled core of the galaxy, and here the stellar population parameter, or the center of the galaxy, is a region with which is metal rich, and the center of the galaxy is dominated for a young stellar population. We recently started to study the same spectra with other technique, the PPXF. PPXF is nice because allow us to obtain the star formation history of the galaxy, and you can see here that the galaxy formed a star early in time, like most early type galaxy, but then this galaxy formed a star during the last 4 gigayears. Okay, if you want to see more details about this work, please see the Victoria Reinaldi's poster. Okay, the other galaxy is NGC 7000, is a galaxy in a loose group which contains 4 galaxies. It is at a distance of around 50 megaparsec, and it shows several scenes of violent past. You can see that in the outer isophoto of this galaxy. Okay, this galaxy have a kinematical decoupled core too. You can see the presence of this here, and here is the result by Kleinenberg, where they present the result about the stellar population in the central part of the galaxy, and they found that the nucleus of this galaxy is young. Okay, regarding the globular clusters in this galaxy, Brown et al. Studied this system. They found a bimodal color distribution here, and they say that the low surface brightness in this galaxy are symmetrical, and then this galaxy is a result of binary merger. So if that is true, then they say that the blue globular cluster should be very metal poor and older, but the red globular cluster should be young and very metal rich. Okay, we obtain a deep field with GMOS in this galaxy, and a comparison field. We did the photometry. We select the globular clusters. Here I show you the result. This is the color magnitude for the cyan field, and the comparison field. You can see that we detect clearly the presence of the globular clusters in the galaxy. Here is the color diagram. And we analyze the luminosity function of the globular cluster, the black line. We fit the Gaussian function, and we obtain the turnover magnitude. With that, we obtain the distance of the galaxy, 50 megaparsec, which is a nice agreement with the previously reported value of Jensen. With this information, we can estimate the total population of the globular clusters in this galaxy. The number is 600. It's a very low number for a massive early type galaxy. Then the specific frequency for this galaxy is really low, 0.3. What about the color distribution of the globular clusters in this galaxy? Okay, we are seeing one of the histogram here, and it looks very strange. However, the things becomes clear when we consider just the brightest object. In black, we have plotted here the histogram of object which luminosity for object brighter than minus 8.5. And you can see there the system is clearly bimodal. The classic blue are here, and the classic red are here. And when compared with the previous histogram, we can see that it seems possible that exists here another peak. So this galaxy seems to have two blue peaks in the globular cluster color distribution. In order to check that, we ran the two-dimensional GMM, and we obtained that this galaxy, this globular cluster system, is composed of four populations: the blue globular cluster, the red globular clusters, the reddest globular cluster, the same that in the previous galaxy, fine fancy cluster, and the bluest object are here. So we put this the position of these peaks in this plot. This plot shows the position of the peaks of the globular cluster color distribution for galaxies in Virgo. It's a work of 10. So when we put the blue globular cluster, the blue globular cluster is in perfect agreement with the relation for the Virgo cluster, but the red globular cluster looks somewhat blue. And if we put here the bluest peak here is an outsider. One interpretation of this is that we are seeing the globular cluster system of lower mass galaxies. Another interpretation is just very simple, is that these objects are younger. Okay, we subtracted the light of the galaxies in our GMOS image, and we studied the low surface brightness structure. We detect these shells and some other structure like stellar stream, and we know that this structure here looks like an object being destroyed. So we use the unsharpened mask technique, and we know that this object is the same, and in the center of this possible object, there is an marginal resolved object with properties according to the nucleus of the early type galaxy. So we think that we are seeing here the process of destruction of a low mass galaxy in the halo of 1700. Okay, what about the stellar population of this galaxy? I mentioned the Klein-Berg value previously, but Francois et al. Has studied several massive early type galaxies using X-shooter spectra, and they obtained for this galaxy these values: young population and very metal rich. But we know that these values are in disagreement with the previous one. Another interesting thing is that these two studies use a comparison between Lick's index with a single stellar population. We obtain the spectra, the X-shooter spectra, and we use the PPXF. So we obtain this result where the galaxy is very old and metal rich, like another early type galaxy. So our result is in contradiction with the previous values. Okay, the last galaxy is this 5018, is another galaxy in a loose group of 5 galaxies at a distance of around 30 megaparsecs. We have in the stellar population in this galaxy, several authors found that the presence of young stellar population in the center of the galaxy and nearly solar metallicity, and they reported weak magnesium-2 index. So that is very strange for a massive early type galaxy. Regarding the globular clusters, the only previous study is the Hilker and Kissler-Patrick, who found a poor globular cluster system, and they estimate this number of the total population. And they suggest that the globular clusters in these galaxies are very young. We obtain a GMOS field on this galaxy and a comparison one. The comparison field is here, the science field is here, and you can see that we detect the globular cluster systems of this galaxy, and it looks very, very poor. We have just 150 globular cluster candidates in this galaxy, and we know that the previous study of these globular clusters was strongly affected by the contamination, and probably that the photometry was not deep enough to study this galaxy. Okay, the color distribution of the globular clusters show that we have the clear peak of the blue globular cluster, but we not detect the red globular cluster. So these galaxies look very deficient in globular cluster, but especially deficient in red globular clusters. The numbers are low. We cannot say nothing more for the moment. We try to analyze the globular cluster luminosity function. Obviously, here there is no Gaussian, so we can obtain the turnover. But if we assume that this galaxy is located at 30 megaparsec, and if there are some classic globular clusters there, we can estimate a number of possible classical globular clusters. The number is 300. That is very, very low for a massive galaxy. So the specific frequency is 0.5. Okay, last question is, you know that most of the massive type galaxies have hot halos detected in X-ray. So this galaxy have hot halos. We analyze the Chandra data, and this is the plot for NGC 7000, and you can see that in the spectrum we obtain the component of the hot halo. Yes, and the parameter for the best fit. The other galaxy, 5018, is the same. We detect the hot halo here. So the three galaxies are detected in X-ray. The dimmer is the first one, 4382, but all have some hot halo. And interestingly, Smith et al. Recently found that these two galaxies have this value very low, very high, sorry, and is typical for red and dead galaxies. So these galaxies seem to red and dead in this aspect. Okay, this is a summary of our result. Is the most important are the two last one, and I discover now that there is problem with the grammatical here, sorry, but the conclusion is it is possible that some of the progenitor of NGC 7000 and NGC 4382 were formed in the two-phase process, but it's not possible that the 5018 was formed through the two-phase process. Thank you.
Thank you, Fabo. Just in time. Do we have any questions? The audience, yes.
Hello, Brian Miller from Gemini. Very nice talk. Have you seen any differences in the kinematics between the different globular cluster populations?
We have a spectra just for the first galaxy, and yes, there is a difference. Is for another talk, and I'm sorry, I forgot to say that the result about these galaxies was published recently. So yes, and
Great, great talk. Could you go back one slide, I think? Yeah, this will do. So looking at these plots and similar plots that you've shown, you have really good fits for, 2 keV and less. What's going on after that?
you said you talk about that.
Yeah, because I mean, like, you have
Yes, for me, it's not important. I just want to take off that component. But Victoria, she's our specialist. For global cluster, it's just important the first. Right.
Never mind. X-ray. That galaxy is very faint in hard X-ray. If you decompose the emission in the softer band and in the harder band, you will see that the most of the emission comes from the soft band. So the broadband spectra shows that this is a very noisy. I forgot the word. And the hard X-ray band has very poor signal to noise. very few photons detected, and you will see the error bars are huge. So the problem there is it's just faint.
Do you have any more questions from the audience?
We have in Slack.
Hello, I'm Song from University. Very nice talk. I just wonder, you assume that very blue and very red globular cluster are very young. I understand that blue is very young, but do you think that for the red one there's
No.
extinction or?
No, I talk about the red and the very blue. This one and this one, because if the globular cluster are younger, they are bluer.
You mean?
And the same here.
Yeah.
But we can't say anything because we have the age and metallicity degeneration. We need some spectra to know what is happening here, or very good near infrared data.
So how about the very red one? So you.
And the very red ones are this one.
Yes.
In several, sorry.
Yeah, I mean, do you have any opinion of what is very red one?
Yes, that cluster are usually found here. Yes, and was studied in some near S0 galaxies, and they are faint cluster, much more like to open clusters. Not exactly globular clusters.
Okay, thank you.
And we have one last question from Slack, I guess.
So Joel Rediger is asking, have you looked at cosmological simulations to see how common are galaxies like the ones you have observed?
Okay, this is the next steps. No.
Okay.
Okay.
So let's thank Fabio again. Thank you. Gracias, Fabio. And now we're going to move on to Zoom. We have some virtual talks, starting with Ignacio Gargiulo, also from La Plata. He will discuss unveiling the origin of the bulge of M81 with spectroscopic observations and the TNG50 simulation.
Well, I'm in control now, right? Yes. Hello to everyone. My name is Ignacio Gargiulo. I'm also based in the Institute of Astrophysics in La Plata. Like Fabio, we are collaborating with several members of the Argentinian Gemini office, and also collaborating with the Galaxy Formation Group in the University of La Serena in Chile. And today I'm going to talk mainly about how the stellar halos of galaxies can help us to understand the formation of inner regions of galaxies, combining observations with what we predict from the high-resolution cosmological aerodynamical simulations. And in particular, I show you an example of our approach and why we think that an archetypal, classical, and massive bulge like the one in M81 may not be the result of merger activity. This is ongoing work, so the conclusions will remain open, but I hope you can get a good grasp on what we are trying to do. So get started. I wanted to give a short background on what people call bulges. The nomenclature in the field can be very confusing sometimes, and maybe it has no sense to talk generally about bulges because, well, inner regions of galaxies can be of many different natures. And the main view is what a bulge is in very general sense, a structure that bulges out of the disk in the central regions of a galaxy. And so a subgroup of them that morphologically show no features, like M81, are in general more pressure supported or contain all stellar populations are called classical bulges. These are usually related to formation mechanisms like mergers or violent gas instabilities or at high redshift. And inner regions of galaxies are very diverse, so people start calling bulges to every light concentration in the central regions of the galaxies. And when studies of the structure of nearby galaxies started to reveal this complex nature, they added the pseudo-bulge classification, or disk-like bulge. They seem to be formed out of the same disk or the bar, and well, that's why they are so called pseudo-bulges. And these usually present different types of features like nuclear disk, dust lanes and everything. And these inner regions are usually connected to secular formation mechanisms, right? And this pseudo-ash classification also contains sometimes the boxy peanuts, like our old Milky Way, that are a very different type of structure, resulting from vertical instabilization of bars. And obviously, there are some of galaxies that are considered bulgeless, like M101. So, but irrespective of the morphology of a central mass concentration in a galaxy, all of them will produce this bump in the central regions of the surface brightness profiles. And we can also define what is called usually a photometric bulge. And now I will introduce you some very basic characteristics of the simulations, hydrodynamical simulations that we use, and how we characterize these inner regions of galaxies or bulges. And for some years now, we have used some of the state-of-the-art cosmological hydrodynamical simulations to study bulge formation. This in the left, this diagram on the left, shows the simulations of the literature with baryonic mass elements. In the y-axis, the baryonic mass element resolution, and the x-axis, the number of galaxies above a given threshold, which is basically the size of the simulation here in the top axis. And in the top left part of this diagram, we can find what is called the resimulation regime, with smaller samples of resimulated galaxies with large resolutions. While going to the right, we can find the cosmological boxes with tens of megaparsec size, for which the resolution becomes much more expensive computationally, so they have less resolution. In 2019, we studied the bulges of 30 simulated Milky Way mass galaxies at the moment, and of the Auriga collaboration, and found that their properties were more akin to pseudo-bulges. And recently we used this TNG50 simulation, which is a cosmological box, and was run with the same code, AREPO, that Auriga simulations, and only with a few changes in the physical model. So this allowed to multiply the amount of galaxies in our sample by 10, and only resigning a factor of 2 in resolution. And I'll be showing mostly these results. So the sample, we select these Milky Way M31-like galaxies in the mass range indicated here in the slide. The diskiness is quantified by the minor to major axis ratio of the stellar moment of inertia tensor. And we got 287 galaxies with the mass distribution shown in the plot, and in gray, where these arrows are the mass estimates for the Milky Way M31 for different authors. And well, this is a bunch of the whole sample, but we can notice here the large diversity of galaxies with many detailed features due to the resolution power of these simulations. So we have a great diversity with a high resolution. And one of the ways that we use to parameterize these bulges is by decomposing the surface brightness profile in the visual band of all galaxies in our sample. When we talk about photometric bulges, we assume that a radial surface brightness profile of this galaxy can be decomposed in different structures, in a linear combination of different structures. And the bulge is usually represented by the Sersic profile, and the disk is represented usually by an exponential, right? We assume only 2 components to do this, and we mask all the features in the surface brightness profiles that, like bars or strong spiral bars. Well, this plot showcases all the diversity of surface brightness profile that we got, and around 17 of them have high Sersic index, above 2. And we also characterize the sample with the bulge to total ratio. The distribution we got is skewed toward lower values of bulge to total, which is a pretty good result in hydrodynamic simulations, because overcooling usually produced bulges that were too large in the past. So, but we also characterize bulges in a second way, more oriented to simulations, because these simulations give us a wealth of information about the stellar particles. So we are also interested in the origin of kinematically defined bulges, and how these relate with the photometric bulges, right? And we define the kinematic bulge with an usual definition among simulators. That is, first we separate stellar particles that have circular or near to circular orbits, which we consider part of the disk, from the rest, by means of this parameter, the circularity parameter. for each particle, we divide the angular momentum component perpendicular to the disk with the angular momentum of a particle with the same initial energy, but in circular orbit. So the maximum angular momentum. And this is a typical distribution of circularities for a simulated disk galaxy. And we use a threshold of 0.7. And secondly, we establish a spatial cut around the central region of the galaxy. So all the stellar particles inside these two effective radii of the Cersei component with circularities below 0.7 are part of the kinematic bulge. But we always have to keep in mind that photometric bulges are very different from kinematic bulges. When we plot the bulge to total radius from different definitions, they are not correlated as expected. The most important use of this definition is that it allows us to find which of these bulge particles form in situ and which form ex situ. And we can use this information to measure the impact of stellar rich mergers in the formation of bulges. So in this plot, we can see what in the galaxy formation community we call the merger tree. Here in the left, you have the main branch progenitor. And in the right, you have all these points that are the satellite galaxies that at each redshift merge with the main progenitor, and we have all this information in the simulation, so we can find which particles form in these satellites, and we call them ex situ particles. So we found in our work in 2019 that with the Auriga simulations, most galaxies have a negligible or very low ex situ fractions in the kinematic bulge. And in the right panel, we see that in the Illustris TNG sample this year, we confirmed this result. And the median value is very close to the one in the Auriga sample, but well, mostly the in situ formation of the prevalence of the in situ formation of bulges is a robust result between two slightly different simulations. But again, the importance of this quantity is to measure the impact of a stellar rich merger in the formation of a bulge, right? So we also studied the influence of galactic bars on bulge formation. And well, we do this in a pretty conventional way. We compute the strength of bars by means of Fourier mode analysis in a pretty conventional way. We define radial annuli in the phase-on projection of galaxies and compute these complex Fourier coefficients to quantify the azimuthal patterns in the mass distribution with these n-fold symmetries. And the second mode corresponds to a bisymmetrical signal, such as a bar. So we use the bar phase angle to determine when this bar ends and spiral structures begins. So the bar strength finally is the mass weighted mean of the amplitude of the second Fourier mode within the bar region. And we looked into the cumulative fraction of galaxies with bars at different redshifts. We found that stronger than a given amplitude, right? So we found that at every redshift, the galaxies with low Cersei index have a higher fraction of bars. But more importantly for our discussion here is that in the lower panels, we see that across all redshifts, galaxies in beams with higher bulge to total radius show a larger fraction of bars than galaxies with less luminous bulges. So basically, bars are contributing to the build-up of these inner regions. And we define a parameter that measures the longevity of the bar or the duration of the bar, because this is a cumulative process that we use to also to measure the importance of this mechanism of formation in the formation of bulges. But the important question is if we can disentangle the bulge formation mechanisms only by observing bulges, because a merger that forms stars in the central region of the galaxy basically has or may have the same result as stars forming due to a bar, depending the timing of the merger and everything. So can we disentangle this? We think that we can. we think that it's possible using this diagram that we call the stellar halo Bulge mass diagram or Bulge mass stellar halo mass diagram. It was presented by Bell Monachesi in 2017. And with this and the help of prediction from our simulations, we think that we can do this. Well, in black, these are indicated the classical bulges, in red the pseudo bulges. And the stellar halo mass estimates are mostly from the GHOST survey, with the Hubble Space Telescope, where they do RGB star counts in the extended diffuse component at galactocentric distances from 10 to more than 40 kiloparsecs along the minor axis and further than 20 kiloparsecs along the major axis to avoid the disk. So the total stellar halo mass is then estimated as 3 times the aperture stellar halo mass. And this is based also in the profiles of ex situ stars in simulations, this fact. And it's commonly accepted and revealed by the study of stellar stream. For example, the stellar halos of galaxies like our own or M81 are formed by the debris of satellite galaxies in falling to the host galaxy that are stripped from the satellites by tidal forces. So the main idea behind this diagram is that galaxies that form their bulges due to merger activity should show a correlation between the bulge mass and the stellar halo mass. So the gray band shows this one-to-one correlation for reference. And we see that there is a large dispersion, so bulge mass seems to be built up by other processes other than stellar-rich mergers, in many cases at least. So we studied the behavior of simulated galaxies in this bulge mass stellar halo mass diagram with the Auriga sample in 2019. We found that there is a large dispersion in the simulated galaxies using photometric bulge mass and kinematic bulge mass decompositions. And this year we are working with the TNG50 sample. And you can see that there is also a large dispersion, indicating that star-rich mergers are not the only process in the simulation that grew bulges. So color-coded are these ex situ fractions that I mentioned of stars in the kinematic bulge. And you can see that close galaxies with bulges with larger ex situ fractions lie close to this one-to-one line reference, while galaxies that hold bulges with lower ex situ fractions are more apart. So the first mechanisms that we try to measure as a contributor of these galaxies with low ex situ fractions is the bulge formation through bars, and we use this parameter, the duration of the bar, the color coding here, and we show in the left the kinematic bulge mass, in the left the photometric bulge mass, and we found a very strong correlation when we use kinematic bulge mass with the duration of the bar, because basically all the stars in bar orbits inside the bulge region are not circular, so we are getting a lot of bar stars, and that obviously are more related to the formation by bars. But when we move to photometric bulge masses in the simulation, this correlation washes out. So we have to try more processes. Now we are in this process. And we can see that in particular for simulated galaxies near the observational point of M81, the bar evolution is not important in the bulge mass growth. So still other mechanisms are needed. We are now studying the radial migration due to spiral arms, considering that M81 is a grand spiral design galaxy and has very strong arms. We may these radial migration mechanisms may have something to do. We also studying the compaction. And well, oh, it doesn't change the here. Well, this is another way to see
Ignacio,
how this. Yes.
You should be finishing in a few moments. Okay.
Okay. Another way to see that the galaxy M81 has still infalling satellites that will form a massive bulge, but now the bulge is the stellar halo is very low massive. So what we are trying to do with observations, basically, clearly I'm more from the simulation side. So questions about the observations, please do them in the Slack channel, please. And some professionals from the Gemini observatory office in Argentina will be answering. And well, we have this configuration for the observation, 4 long slits in the central region of AMT1. And we want to take these profiles of kinematic quantities like radial velocity, dispersion velocity, and everything, and try to compare them to results in the simulations, because obviously the simulations, although very detailed and everything, have a lot of oversimplifications in the physical processes and resolution problems. So we wanted to combine this with the observation with spectroscopic observations to find some connection between simulations and observations that can help us understand how this bulge was formed. That according to our simulations, it was probably not formed by immersers.
Ignacio, can you go to the conclusions, please, so people can see it later, perhaps? Thank you.
This is the summary and the future directions of our work. But thanks already.
Okay, thank
Thank
you.
you.
Do you have questions on Slack?
Not yet.
We have time for one quick question if someone has. We have one there.
Hi, Ignacio. I'm Karim Menendez del Mestre from Rio de Janeiro. It was very interesting work. I wanted to ask you, I'm trying to wrap my head around the fact that you say that galaxies with strong bars do not have a high fraction of ex-situ stars in their bulges. I'm trying to, how do you think about this in terms when we think about the creation of pseudo-bulges, how bars will actually help transforming classical bulges into pseudo-bulges? I would expect that there would be more ex-situ, stars that are not born in the bulges in strong bars. How should we think about this?
I think that there are several works indicating that there is like a twofold causality of that. For one side, bars contribute to form mass in the inner regions of galaxies by making the gas lose angular momentum. They can also, near the core rotation, they can drive stars to inner regions and make them lose angular momentum too. So this is one causality path. And the other one is that when you have already a strong spherical concentration or a strong classical bulge, the way you want to call it, from the beginnings, you delay the formation of a bar. So, or even you can prevent the formation of a bar if you have a strong concentration of mass from the early epoch. So you have to see each case separately to know what happened, but that's why we found, I think, a very not strong, but very markedly marked bimodality in that sense.
Okay, so
Thanks.
thank
I
you.
will know you.
We can continue the discussion on Slack if you want. We're out of time, so we have to move on. Thank you, Ignacio, very much.
Thank you.
And now we're going to move on to Veno Kalari from Gemini and R136, who will talk about births and deaths of stars in the Magellanic Clouds with Zorro.
Sorry, I can't push the slides. Yeah. Hi, everyone. I'm Venu, and I'm an assistant scientist at Gemini South. I would like to begin to thank the organizers for this opportunity, and also to apologize in some small fashion because of the ambiguous nature of my title and abstract. In my defense, when we submitted this abstract, it was because we had just received Zorro data of R136, and we weren't sure we could process and release it in time for the talk, but we have. And I think the data looks spectacular, but I think the audience will be the real judge of how the data look. our story begins on a summer night around a year ago at Cerro Pachon. We used Zorro, which is located inside the GCAL unit, the speckle imager that covers around 2 arc-second field of view, to image the Large Magellanic Cloud. Now, the Large Magellanic Cloud is a dwarf galaxy around 50 kiloparsecs away, at around half a solar metallicity. Like many dwarf galaxies, it doesn't have a very active center of star formation, but there is a lot of star formation happening within it. And there is especially a lot of active star formation going on in the 30 Doradus region, which can be seen at the top center of this image. And that is where our target lies. Now, 30 Doradus, and within it lies the starburst cluster R136, is the closest representative of more distant, high redshifted starburst clusters, or maybe in this, since the last 2 weeks, we've probably called this medium redshift distant galaxies. We see these similar starburst clusters. Now, this whole region, this whole beautiful star-forming region, is powered by around 100 O stars and a few dozen or so Wolf-Rayet stars, which are ionizing the molecular clouds around them. So they can so these create these beautiful arcs that you see in the image, but they also create an immense amount of feedback on the molecular cloud and into the general environment as we speak. Now, at the very heart of 30 Doradus lies the R136 starburst cluster, which I was talking about. And so we zoomed in from a 4-meter telescope image into a Hubble image where you can see R136, the very center. There's active star formation around it, but also in the very core as well. But that's not what we're interested in. We're interested in R136 and the births and deaths of stars within it. So R136, as I've pointed out, contains around 50 to 100 O stars, depending on the radius you use. And in the very central cluster, which is zoomed in here, there's around 50 O stars within a couple of arc seconds. So it's very incredibly dense and very incredibly luminous. So it has around something like 10 to the power 51 photons per second ionizing the clouds around it. And because of this issue, because of the very high dense nature of this issue of the cluster, because of this, you can't particularly resolve the central core. And this creates an issue because you can't resolve the very central stars that are creating this whole region, because you can almost see with the naked eye. And I try to highlight this issue a bit more by showing you a 2 arc-second field of view in this central cutout, which can be seen here, which hopefully is visible much better to the audience than to me. And so to resolve the very central core, which contains around 50 O stars, you need a resolution of, say, less than 40 milliarc seconds, which is probably the limit to which we can actually see. And the issue in particular is that if you can't resolve the central stars, you can't get their luminosity. And if you can't get their luminosity, you can't estimate their mass very accurately. And you need to know their mass, because mass is the principal factor determining the evolution of the star. And also you need to know the mass to put into a whole host of other things, and also the feedback that is creating this whole region that we see. So the question is probably that if you can't resolve these stars with current instrumentation, do we have to wait for, say, a 30-meter telescope to come and resolve the issues? And as this talk might tell you, it's clearly not, because you can with Zorro. It's stuck. So you can't actually. You can. So you can with Zorro. So this is 2 arc seconds zoomed in to the very first image I showed you. So these stars are responsible for creating that very beautiful, primarily responsible for creating the very beautiful star forming region you see. So the resolution of this image is something better than between 30 to 40 milliarcseconds. And these stars have a limiting magnitude of around 16, so they contain almost all the O stars because of the distance of the large magnitude. They contain almost all the, and the extinction, they contain almost all those stars known within this region. And you can see the scale bar here of in the bottom right of 0.5 arcseconds. So if you had that resolution, the central core would completely be unresolved. And marked in this image, you see the stars A1, A2, and A3. And these are very important stars to mankind because they are three of the most massive stars known to us. They're of the spectral type W and H. So they're basically Wolf-Rayet stars. These are so massive and so young that they're still fusing hydrogen inside their core. The N stands for nitrogen, which you can see in the atmosphere, along with some helium. This is due to rotational mixing within the star, but also their mass loss. And also the reason why they were called R136A is because when first speckle imaging was taken of this region, the central core was visible as one object, which is shown as R136A. So you can see how much we've come in leaps and bounds. That's speckle imaging taken in the mid-1980s at LaCie, and this is speckle imaging taken a year ago at Gemini. So we've come in leaps and bounds, and we can really resolve the core. And you can really see this improvement in angular resolution in comparing with other telescopes. So there lies to the left Hubble Space Telescope images in the UV and the optical, but also infrared images using multi-conjugate adaptive optics in the top center, but also the sphere instrument at the VLT in both in K-band, and also in the top left, there is a Muse AO image of the same region. You can say that Zorro is probably comparable or better when you actually look at the resolution, at the measured resolution on the image of the central cutout of the cluster. And you can really resolve A1 from A2 and also A3 from its new companion, which we've just identified using the Zorro imaging, but also A1 from a close by star number 9. So before I dive into why this is actually quite important and why I'm going on about it, we'll go back a little bit to see how massive these stars are. And these stars are extremely massive. So conventionally, based on statistical arguments and also empirical measurements in the Arches cluster in the galactic center and also R136, people have suggested a 150 solar mass limit for the upper end of the stellar initial mass function. Now, Crowther in 2010, using AO IFU spectra and also HST imaging, found that these stars in the very center, or claimed that these stars in the very center of R136 had masses of 300 for A1 and around 200 for A2 and A3. And they followed it up with Hubble SDIS spectroscopy in the UV, and they corroborated that result. And so the HRD of these stars looks something like this. So in the black are the results from Bessel-Lehner, and also in gray are the results from Crowther for A1, A2, and A3. So these stars are extremely massive, all about 150 solar masses. The stellar mass is written there is the stellar initial mass. And they are sort of go against conventional wisdom for how massive stars can go, at least in the nearby universe. But you might have thought of a flaw in the images, because I told you that they used Hubble Space Telescope primarily in 2010, but also they used spare imaging in 2020 to measure the luminosities of the stars. But you can say that the imaging didn't particularly resolve the star 9 from A1, but also A1 from A2 and A3 from its companion. So that meant that actually when we measured the luminosity of Zorro, the luminosity we measured was much lower, or a bit lower. You can visualize that on the SED here. So these are SEDs of A1, A2, and A3. And in red, we plot the Zorro magnitudes, and in blue, we plot the HST and infrared magnitudes. And so this magnitude difference of a few tenths of magnitude actually creates quite a lot different, feeds into a lot of difference in the actual luminosity of the star. And so it turns the HRD, which looks like this, into something like this. So here we have A1, A2, and A3, quite a bit lower than was measured in the literature. And how lower? Well, A1 went from 300 to 250 solar masses from the literature to around slightly less than 200 solar masses. And A2 and A3 sat around 150 solar masses. So we actually have just one star, which is above the canonical 150 solar mass limit. And so what does that actually mean? What are big results? Firstly, the most massive star known, R136A1, is actually not that massive. And I say not that massive in italics because I mean it in a relative sense. It is still the most massive star known, and it is larger than the canonical stellar mass. The other results, since I'm fast running out of time, we'll skim through them. The first one is the initial mass function. So the IMF is a probability density function. And so you have a lower mass limit which is determined by where the core stuff can fuse hydrogen, and also an upper mass limit, which was based on statistical arguments, but also empirical arguments in the nearby universe. The statistical arguments are based on the radiation pressure impairing a star growing any larger, which is around 1,000 solar masses, which is thought to be in the early universe. And in the nearby universe, it was canonically thought to be 150 solar masses. So the result that there was a 300 solar mass star in the nearby universe shifted the upper limit of the IMF considerably. And even though there's a small shift in mass, there's an extremely large shift in the amount of luminosity outputted, because luminosity scales to the power of 3 or higher at this mass end. So there's a lot more luminosity and considerably a lot more mass that's being seen. The most important thing, I think, is the fact that it sort of shows that maybe pair instability supernovae might exist. So pair instability supernovae are hypothesized to be the end product of 150 to 300 solar mass stars. And their importance can't be underestimated, because a single 300 solar mass parent star exploding as a pair instability supernovae releases more metals into the ISM than the complete IMF below it. So these stars are extremely important to understand the evolution of metals. And the hypothesis that these stars greater than 150 solar masses, even the local universe, exist, meant that, okay, we will find pair instability supernovae in the more distant universe. There were other results that do not match the explanation that they exist, but this is the fact that they were 300 solar mass stars suggested that they do, but lowering the upper mass limit lowers the probability that they actually exist. And finally, feedback. As I discussed, a 300 solar mass star, if you assume a certain IMF slope, say minus 1.95, which is considered okay for 30 erratas, gives out more neutron stars, gives out more neutron star mergers, more black holes than predicted, using the canonical upper mass limit and the canonical IMF. So knowing this upper mass limit is extremely important to predict how many neutron star mergers you can see, how many black holes, all these exotic events that they need a well quantified IMF and also a well quantified upper stellar mass limit to predict. Finally, acknowledgements. I've not gone too in depth into science here, because I thought for the Gemini science meeting it's much more useful for the audience to see a lot more about the data. But if you want to talk about the science, please feel free to email me, message me in the Slack. At GSM, please talk to Ricardo if you're interested in using Zoro. Elliot Horsch contributed significantly to the data reduction and understanding of the data, and he's the chair of the SOC, so please feel free to talk to him about that. Our paper is in press, it's on astrometry, so feel free to have a look at that. And finally, I will end with a review. Thank you so much for your time.
Thank you very much. There was some beautiful data that you showed. That was exciting. Do we have any questions? Sorry, any questions from the, yeah, we have one there.
Hi, Venu. Thanks for sharing this beautiful presentation, and I really appreciated those zooms from the big sky to the core of R136. So in the work of Crowther, I think the point there, well, the work is very model dependent and assumption dependent. The main conclusion was the masses are not 80 and they're not 1,000. So they came up with 300 saying, yeah, more or less. Then you come with those beautiful Zorro data. And so you seem to be playing in the same range of masses. So my question is, from your appreciation of all the work you did, how much more accurately do you think you have those masses down? Also considering that we have no Keplerian motions, because those don't seem to be binaries, unfortunately. So all we have are luminosities and our very poor understanding of how this relates to the masses.
Yeah, so I don't think we've quantified it in a better range than Crowther at all. That is true. But I think what we have done is resolve the stars in the core. So I think our final result, the take-home result, is probably not the fact that these stars are, say, 100 solar mass lower, and that's written in stone. But I think that we can resolve these individual stars. I'm sure JWST or a bigger telescope will come and resolve it even better. But the actual mass estimate, I mean, it couldn't be. We did some back of the hand calculations based on the central density of the star, central density of the cluster, to see what's the probability of being a binary. And it's not negligible. It's more than 30 to 50% for both A1 and A3. So that also can't be ruled out, but obviously we can't do it with the current data. We can't check if it's actually a very wide orbit binary. I mean, it's unlikely to be a wide orbit binary at these masses, but yeah, to answer your question, we haven't found a mass value that's written in stone. I think that's, yeah.
Well, still, I would be happy to bet a bottle of your favorite thing that it's already merged and it's a single star. Thank you.
Janice, do you have a question?
Hi, Venu. This is Janice. Very, very nice result. And as a person who studies high mass star formation, and this is a really impactful result that will be, I'm sure, the topic of many conversations in our field. My question was actually related. And of course, understanding or constraining the actual masses is very model dependent. But as you said, really the result here is resolving multiple objects and then understanding, having a better constraint on the luminosity, just the observable parameters coming from Zorro. And so doubles in the details. Even with that, there are systematics, 0-point offsets to see what the difference is between your photometry is and the existing photometry. So I just wonder if you could comment on I mean, you had pretty large error bars on the model plots, but in terms of the observable parameters, if there are any issues there that, could be the subject of debate.
Yeah, I think that's the kind of runs, because Zorro is not really built, well, a spectral imaging is not really built for doing this kind of analysis. So I think, I don't know of any paper, maybe Ricardo or Elliot can correct me, but to measure the actual magnitudes, we did we measured at the same air mass a couple of standards, and based on that we got the magnitudes. But that's why the error bars, especially on the blue, are higher. But this is as well a very unconventional technique to get photometry. So I would be looking forward to JWST imaging, I guess. I mean, it won't get magnitude in this wavelengths, but it would be good to compare it to see the slope of the SED at least. There are a lot of systematics. I think we've tried to answer them more in detail in our paper and to describe it more. But yeah, I think maybe this doesn't fully answer your question, but
Yeah, we
I
can
think there's
continue
not
talking
been
more.
Yeah.
sufficient work done calibrating photometry from a speckle imager at this level to say more about the systematics. Yeah.
Okay,
I
thank
think-
you, and congratulations again on a great
I
result.
think we have to move on. We also have a question, I think it's by Joe Rodinger on Slack. So I encourage you to just to continue the discussion online, and congratulations. That was some beautiful data that you showed there. So let's thank Venue again. And the next talk will be, I'm sorry, I lost myself here. We have our next talk by Kyunam Kim from University of Cincinnati on the phase space since Z of 1, a kinematic view of environmental dependence of star formation from SPT clusters using the Gemini multi-object spectrograph.
Okay. Hi, everyone. Can you hear me? Uh-oh.
Yes.
Yes, yeah. Oh, the slides, yeah, just moved away. So hi, everyone. I'm Kuno Kim. I'm a postdoctoral fellow at University of Cincinnati. I'm working with Matt Bailiff, who might be present on site for the meeting. Today, I'm going to talk about how the galaxies star formation have changed in galaxy cluster environments since infall at high redshifts, and for which we update the existing picture by using an advanced kinematic measure. And as I will show you later in this talk, this analysis highly leveraged the efficient capacity of Gemini GMOS spectroscopic observations for a bunch of high redshift cluster galaxies. Oh, sorry. Yeah, as a brief background, it's been known that the level of star formation of galaxies is largely determined by two main parameters. One is galaxy's stellar mass, and the other one is galaxy's environment, i.e., where the galaxies reside. And this figure demonstrates how the galaxy's stellar mass and the environment is related to the fraction of red and dead quiescent galaxies, star formation quiescent galaxies. And in particular, at given stellar mass, it's clearly shown that the fraction of quiescent galaxies increases with denser environment. So there is a higher fraction of quiescent galaxies in denser environment compared to the isolated field galaxies. This would suggest that the denser environment suppresses star formation of galaxies. And this environmentally induced quenching effect is also seen even within galaxy clusters. As the largest unit of gravitationally bound systems in the universe, galaxy clusters are characterized by unique features such as X-ray emitting hot intracluster medium. And by using the cluster-centric radius, the distance from the cluster center and to the galaxy, it's been shown that the fraction of star-forming galaxies in and out around the cluster environment systematically decreases as we move from the outer parts of the cluster towards the cluster center. we update this environmental star formation environmentally induced star formation process by using not only the cluster-centric distance, but also the orbital motion of cluster galaxies. And also we update this known environmental quenching effect by not just using the fraction of star forming and quiescent galaxies, but rather using a direct indicator of stellar age, as we will as I'll show in the later slide, another spectroscopic parameter. And the idea is shown here in this cartoon. And the idea is that we trace, typically, galaxies infall in the from the initial infall of galaxies can pass the pericenter and backsplashed and ultimately get virialized in the cluster gravitational potentials. And by using the cluster centric radius and the peculiar motion, we can trace the galaxy's motion in this diagram, which also known as the cluster phase space diagram. And if we observe these orbital trajectories of infalling galaxies through a telescope, we can obtain the 2D version of projected phase space, where we are using the projected cluster centric radius and the line of sight peculiar velocity. So we can map the cluster galaxies infall time, in this diagram, and then use how the level of star formation of cluster galaxies have changed since their infall into the host clusters. And this phase space diagram has also been found effective in cluster simulations, where individual infall time steps can be directly traced. And this figure shows the simulated cluster galaxies with different infall redshift. And different color indicates different infall redshift, and clearly shown that the early accreted cluster galaxies tend to populate in this distinct region compared to those recently accreted blue dotted galaxies. Another simulation shows the consistent trend in that galaxies in the galaxy's location in the phase space can be mapped with their time since infall. Here, the red dotted galaxies are the ancient early infallers, whereas the blue dotted galaxies are the recently accreted galaxy populations. And by further using these trumpet-shaped curves, we can largely separate galaxies into different infall time groups. And for us to use the phase space diagram, we've constructed one of the largest spectroscopically confirmed galaxy cluster catalogs obtained from the SPT, South Pole Telescope, and ACT, Atacama Telescope cluster surveys over a wide range of redshift. The black dotted data points are our sample clusters over a redshift range, and by using from the optical imaging follow-up, we obtain the individual galaxies I-band luminosity, for which we will use as a proxy for stellar mass. And from the spectroscopic follow-up, we were able to measure the accurate cluster membership and the age-sensitive 4000 break spectral feature as shown with these red vertical lines. And we were able to obtain many of cluster member galaxies spectroscopy from the Gemini GMOS spectroscopic observations. And for that, this work was highly leveraged the Gemini GMOS spectroscopy. And this is the phase space diagram of our sample clusters. White dots are the low redshift galaxy subsamples, whereas the gray clusters are the high redshift subsamples. And also using the same trumpet-shaped region criteria, we classified galaxies into 3 different info groups. The galaxies that are accreted early being located this pink central innermost region, and the intermediate info galaxies being the orange, and the outer, the recently accreted populations in the blue colored region. And these regions are qualitatively tracing the likely info time as we've seen in the cartoon figure in the slide. And this is our main result. From the phase space, we infer their mean info time, and then relate this info time proxy parameter with the galaxy's age-sensitive spectra 4000 break. And what we found is a gradual increase of 4000 break with this info time proxy. The different colored field diamonds are the mean 4000 break strengths of different info region. And the black, the straight line is the linear fit to the all individual data points. And we see that there is a gradual increase of 4000 break of galaxies with this info time proxy. This would suggest that the galaxies that spend longer time in cluster environments tend to show a larger 4000 break, which means the older stellar population age, which likely due to a longer exposure to environmental effects such as ram pressure, gas stripping, and strangulation. And based on the stellar population modeling, this increase from the 4000 increase between the recently info groups and the early info groups correspond to about 0.7 gigayear older mean age. And this gradual increase of 4000 break with info time proxy is found even at low redshift subsamples as well as high redshift subsamples. And we checked this info time averaged environmental quenching trend between for different galaxy luminosity subsamples where we found that this environmental quenching trend is found regardless of galaxy's luminosity. As shown here, the orange are the bright, more massive galaxy subsamples, whereas the gray-blue is the faint, low-mass subsample galaxies. And we see that both luminosity bins show the gradual increase of 4000 break with info time proxy. And this would mean that galaxies experience environmental quenching effects since info, regardless of their luminosity and mass. And this figure further clearly shows that we see the environmental quenching effect at any galaxy luminosity, where the x-axis is the galaxy luminosity and y-axis is the galaxy's infall time proxy. And at fixed luminosity, it's clearly shown that the color, the mean 4,000 strength is increasing with longer exposure, a longer time since infall, where we derive this environmental effect by using a kinematically derived parameter. And lastly, we checked that we checked our environmental quenching trend is found at all redshift as well as all luminosity beams, where the left panel shows the two redshift beams for the same trend. The blue is the low redshift galaxies and the red is the high redshift galaxies. And we still see that their 4,000 strength increases with longer exposure, longer time since infall. And this middle panel is for the faint sub L-star galaxies, and consistent with the left panel, we see that galaxies 4,000 strength is increasing with infall time. And the right panel is the bright super L-star subsamples. And these three panels all indicate then that galaxies experience environmentally quenching effect since infall at all redshift and at all luminosity beams. And this is our summary. And one key takeaway is that we found that galaxies experience a gradual decline of star formation after they fall into cluster environments, which would indicate that longer exposure to environmental effects such as RAM pressure stripping and gas strangulation. And the results have been submitted to FJ and are also posted on archive. So I'll stop here and happy to take questions.
Thank you very much, Piano.
Thank you.
Do we have any questions? Do we have one there? No. I actually have one question. This was very interesting. I like the data, and I was wondering if there's any correlation between the variation in ages that you see from early infall to recent infall. Do those timescales in variation of age correlate somehow to the dynamical timescales of the clusters themselves?
Yeah, that's you mean the dynamical timescale of clusters? You mean relaxation timescale, right?
Or something like that, or crossing timescale, something like that. How long the variation in ages of the galaxies correlate with how long they have been orbiting the clusters, or how long they have been interacting with the intercluster medium?
I see. Yeah. That's a good question. And we actually try to kind of directly map based on the cluster simulation results. And if we focus on since the cluster simulation is only done in down to low redshift only, and if we map it, this age increase is typically smaller than their actual time since infall.
Okay. That's interesting. I'll follow up on that. I'll definitely check your paper. Do you have any more questions maybe on Slack? Is there anything?
Thank you.
Nothing.
So if not, let's thank Yunho again. Thank you very much.
Yeah, thank you.
And we're gonna move on now to flash talks. So this is not in the original Yeah. So we would like to remind the virtual participants to stay for the virtual conference picture after the poster flash talks. This is going to be, we're going to have a series of 6 flash talks, if I can remember correctly, maybe. And after that, we're going to have the virtual virtual picture for everyone who is online on Zoom. So please remain online that we can take your picture. So can we please get the I think there's one in person. Can 5 minutes. Yeah. So can we get the one presenter for the
Good morning. My name is Joshua Roberson. I'm a PhD student from the University of Cincinnati, and I have been working with highly lensed high redshift galaxies, and more specifically, the issue of is it actually possible to teleport a dim high redshift galaxy from a much closer but dustier galaxy that is going to end up having a similar brightness when viewed from our perspective. And so I've been working with 5 different galaxies taken with like multiple images across multiple filters, including some GMOS imaging. And you can see here where in each case we see the galaxies brightly in a few filters before they drop out. And for the high redshift case, we're suspecting that this is a case of them being like Lyman bright galaxies where all of the light past a certain wavelength is being absorbed. And if we can find where that wavelength actually is, that will give us a good indicator of what the redshift of those galaxies are. And so we've been trying to piece that together from limited data points, and you can see up there the SED fits of the 2 high redshift galaxies, and like where in each of the spectra that we were able to model, there was a sudden, like a very sharp drop off that we were able to use to isolate the redshift. And the end result is that we're able to actually pretty robustly like separate the low redshift example, like the dusty low redshift examples from the high redshift examples, and this would put us at some of the brightest high redshift galaxies discovered to this point, and there's more details about how I do that on the poster, so thank you very much.
Thank you, Joshua. And let's move on to the videos now, I think.
Hi everyone, I am Winston Aro, undergraduate student at Universidad Católica del Norte in Chile. I present new high-resolution near-infrared spectroscopic information from the high-resolution E-green spectrum for event members of BBB CL001, a very atypical stellar cluster buried in the inner galaxy harboring the most metal-poor population among the known Milky Way globular clusters. I will present preliminary results from our E-green analysis for BBB CL001, providing chemical and kinematical information from the H and K band for the stars in the innermost region of BBB CL001. With this new observation, we confirm the extremely low metallicity nature of BBB CL001 and provide additional information for a wide gamut of chemical species accessible from the H and K band. We also provide enough information about the prevalence of the multipopulation phenomenon in BBB CL001. And I hope you have a good time at GSM. Bye-bye.
Hello everyone, my name is Minapotsi Yengece and I studied the ISW effect in interacting dark matter-dark energy models. Why do dark matter and dark energy contribute similar amounts to the universe's energy budget at this precise moment in cosmic history? This is an important question in cosmology. To address this problem in the interacting dark matter-dark energy models, the densities of the dark matter and dark energy do not evolve independently. In this work, we calculate the ISW, auto and cross power spectrum for a particular energy transfer term and compare it with the corresponding result obtained from the lambda CDM model. For more details, please check our poster.
and stellar populations are your kind of thing, I invite you to come visit my virtual poster. The poster describes the status of a multi-year campaign with the GMOS instrument to obtain blue optical spectroscopy of dwarf galaxies in the Virgo cluster. The main question that we're trying to tackle in this campaign is whether the passive dwarfs we see in Virgo today are consistent with having been produced by simple ram pressure stripping of progenitor systems that were gas-rich and had tepid star formation histories. The results that we've obtained so far indicate that such an explanation probably doesn't work for a significant minority of the population. Specifically, when we look at the ages and alpha abundances of our targets, we find that those that sit within the central regions of the cluster tend to have stars which are both old and alpha enhanced, which indicates to us that they likely formed their stars a long time ago and quite rapidly. If this work sounds of interest to you, please visit my poster. Afterwards, if you have questions or comments, by all means, send me an email at the address that's provided in the poster. Thank you.
Hi everybody, my name is Bruno Bortoli. I'm working at the Universidad de La Plata in Argentina. I'm currently in the last year of my PhD, and in this meeting I'm presenting a poster of a chemical analysis of the small Magellanic Cloud main body by means of spectroscopy of red giant stars belonging to stellar clusters. In this work, we use the instrument GMOS of Gemini. Well, if you have any question or any comment, you can write me to the contact email. Well, thank you. Have a nice meeting.
I'm Elisa, PhD student at Universidad Andrés Bello in Chile. In this work, I present you the first kinematic analysis of three globular clusters, BBB-CL 160, Patrick 126, and Patrick 99. We observed member stars with the high-resolution high-green spectrograph. Reconstructing their orbits for the first time, we found that Patrick 126 is a real bulge globular cluster, which probably survived with prograde orbits. BBB-CL 160 show very extreme kinematic. So is it a galactic or an accreted globular cluster? Patrick 99 star sample can be split into different radial velocity groups, but we do not exclude its cluster nature because other 9 stars are being observed. We wish that many more clusters will be observed during the next programs, and I hope seeing you in person next year. Enjoy this meeting. Bye.
And I think now we'll have the picture. Is that it?
Can the virtual attendees please turn on their cameras so we can take a screenshot, please?
And yes, and we
Thank
can have
you.
the coffee break as well and all the virtual.
Not yet. People is
So we're-
turning cameras on.
We're
Smile. Another one. Yeah, I am there too. Okay. Okay. Oh, wait. Okay. I think we have another one. Okay. Can you take another picture? Yeah, I see. Okay. Okay. Another smile. Hold it. Sorry. Yeah. Over there. Cheese. Okay. Thank you. No problem. Sorry, Janice, I didn't notice we were running out of time. I think I put the timer like later. Hi. No, this is your quencher. It's a little bit. Be careful. You need to survive. At least one more month. You need to stay here. Let me know how to do that. Yeah, okay. Tell me. Yeah, it's a little bit warm, my chair. So. Good. Of course. Oh. Oh, yes. Sorry. You virtual chair. Yeah. So yeah, how does it work? I guess I could follow.
Making a
Yeah.
picture.
So
Do you usually have higher drive?
no, I was before. Hi, I'm
Hi.
Clara.
Oh,
Martinez. So what you need to do is like 5 minutes warning
That's gonna be
and like the last minute warning, or like when they are finishing, you just start putting start like this.
The virtual speakers, they may not recognize.
Yeah, okay. You only need to take care of the virtual speakers. He's they're going to so here, yeah. So for example, the first song is mature. Yeah, the second and third are so they are yeah. He's the one that is going to give the warning.
So which one is the
First and fourth. Yeah.
and second and third? To now, here. To now, what? Yes. No, but no, wait. When do you start actually? The 11th, technically, because of the flight. Well, the line is yes.
Senate, when do we start? Just on time, like 10:50? Or a little bit later? 10:55. So 55. In 10 minutes. Oh, that's 11. Yeah.
Yeah. Right? So what to now is here and second view.
Yeah. And yeah, you're connected, no? Okay. And you, what I am doing is pinging in a Slack channel here. So and I am doing like every time instead of doing everything together because I think it's better because people, yeah. And then there is start. Well, the start. So here, option, annotate. Yeah. And if you want to remove it, sometimes you are checking the class and you didn't notice that that's going like this, for example. What is going to happen is you're still there, you know? So you need to clear everything. And if you close this, you can do things. Okay. Yes. Yeah. Yeah, I was doing this like here and all this stuff. So the people is knowing we are there, but yeah. Yay, no problem.
And then virtual.
I got oriented. Yeah, thank you. Yeah, so.
Okay.
Yeah, let's see. Okay, so it's time to start this session. So welcome to Black Hole Asian Quasars 2 session. I'm Chong-Hak Woo from Seoul National University. I'm going to be chairing this session along with Haewon-seo as a virtual chair. So we have 4 talks in this session and 2 talks are invited, which are the 20-minute talks. So I encourage you to leave a question in Slack, so during the question session or even after, you could interact with the speakers. So the first talk will be given by Shin Liu. It's a virtual talk. The title is a vodka, astrometry for off-nucleus and dual subkiloparsec AGN. Okay, so whenever you are ready, you can start.
Yeah, thank you. Can you hear me okay?
Yes.
Great. So thank you everyone for coming. Today, I'm very excited to tell you about our ongoing project called VODCA, which stands for astrometry for off-nucleus and dual sub-kiloparsec and kiloparsec AGN. I'm going to be focusing on the dual population, but our technique is also useful for searching for off-nuclear targets. I wanted to thank my collaborators and in particular, those early career researchers being highlighted in yellow here. So this talk is gonna highlight the work being enabled by mainly by 2 Gemini instruments, so GMOS and GNRS. And at the end, I'll also briefly mention the exciting prospect with Alopic, the speckle imager. So we wanted to thank our the amazing scientists and our support astronomers at Gemini who really help us, make the observations possible. So I understand this is a really diverse audience. So I wanted to start my talk by providing you with a bit of a background. So why do we want to study dual binary AGN, or more generally supermassive black holes? As a reminder, in our own backyard, our own Milky Way galaxy is in a direct collision course with our closest neighbor Andromeda. So we are, personally relevant with this kind of cosmic interplay. And in fact, galaxy mergers have long been thought to drive strong gas inflows, producing either one or maybe two active supermassive black holes, inducing perhaps also feedback to influence the host galaxy evolution. So the dual or binary population really provides a direct tracer of the hierarchical galaxy and supermassive black hole formation. In addition, if we focus on small scales, meaning kiloparsecs or sub-kiloparsec scale, it actually provides us with another indirect tool for understanding the particle nature of dark matter. And this is because the particle nature of dark matter directly influence the dynamic of friction, which will drive the further evolution of a pair of supermassive black hole. So in some models, alternative models to the cold dark matter, instead of promoting dynamic of friction, they could actually prevent further dynamic of friction, so producing a lot of stalled supermassive black hole pairs on sub-kiloparsec scales. So in order to test this, we really need to go down to this kiloparsec, sub-kiloparsec-ish population and really understand their statistics. And last but not least, I don't perhaps need to tell you that they are also of interest to the very exciting emerging new field of gravitational wave astronomy. But you may wonder, we already have LIGO sources. Why do we want to understand or study the supermassive cousins? And this is because unlike most, if not all, LIGO stellar mass black hole binaries, most of the supermassive black hole binaries are expected to occur in gas-rich environment. And this offers a great opportunity for multi-messenger astronomy, and not just post the fact observation, but because of the longer evolution timescale, you can actually get a really early forewarning of the event happening, which means that you can get your favorite particle detector, EM observatories ready long before the final coalescence actually happens. So it provides a really exciting opportunity for really comprehensive multi-messenger astrophysics. So thanks to most recently, mostly due to the event of big surveys, there has been great progress being made in the observational searches of dual and binary AGNs, which are taken as tracers of dual and binary supermassive black holes. So here on this cartoon illustration, I'm showing you some example known systems or candidates in the parameter space of binary separation as a function of redshift. And if you notice, the separation spans several orders of magnitude, going from milliparsec to subparsec to all the way to kiloparsec to 100 kiloparsec scales. And this is because we want to paint a really coherent picture of the full evolution of a pair of supermassive black holes following a galaxy merger. And you may notice that there are glaring gaps in this diagrams. And so firstly, these objects shown at the bottom right, they are candidates. So they're basically sub-parsec candidates that are selected from indirect approaches, perhaps not available for direct confirmation, before gravitational wave detection. And what we would like to focus on are the population on the upper left, which really represent those that are directly confirmed systems. So if I make a similar plot by showing you, almost all the known so-called dual AGNs in the literature. So here is that plot showing on the right. You can see that although there are many dual AGNs, which are the really low luminosity counterpart of dual quasars, there are really only a handful of cases, at redshift 1 to 3-ish, around redshift 2, which is the cosmic noon, representing the peak of both quasar space density and cosmic star formation. So in order to really understand this peak supermassive black hole and star formation epoch in the universe, we really want to go to higher redshift. And so at larger scales, which means larger than 10 kiloparsec scales, there are many of these wide separation quasar pairs, but we really don't know if they are already in gravitational interaction with each other yet. So they may or may not be merging as of yet. So bottom line is that there is a glaring gap at high redshift and small separation, which we would like to fill with the Vodka project. And finally, this last plot just zoom in on the cosmic noon, showing you the really handful of candidates of dual quasars, which really represent the really highly accreting merging systems that may more likely to be directly associated with mergers. And I'm gonna return back to this figure later, but in this talk, I'm gonna be highlighting this new work, which represent the first confirmed case of a kiloparsec scale dual quasar at cosmic noon with confirmed galaxy merger. Okay, so but before telling you the details, I just wanted to say a few words about the many methods that are available to detect these systems across a whole different scales, and we draw a lot of inspiration from the stellar binary and exoplanet community. And in particular, there is the astrometry technique, which proves not to be so useful for exoplanet, but it turns out is very useful for us. I won't go through the details, but just to give you a context of the techniques that are available. And in particular, this new technique, which we called vastrometry, which stands for variability-induced astrometry jitter. So it goes like very similar to viewing a railroad crossing sign from the distance. So notice that if you have two quasars on kiloparsec scales, so the quasars themselves are not moving, but because of the variability, perhaps due to thermal instabilities in their accretion disk, it produces this apparent shift in their unresolved light center, which we can use actually as a detection signal. Using this technique, we use Gaia astrometry, which really offers you a almost full sky survey of bright quasars. Here I'm showing you some examples of ground-based seeing limited images of some of the astrometry selected kiloparsec scale dual quasar candidates. Now, in order to really test whether they are due to two or multiple sources, so really need high resolution follow-up, and we obtained dual band Hubble images, and indeed in more than half of the sample, you find two or even multiple sources verifying that indeed this variability-induced astrometry jitter technique is working. And using the information, we can by and large reject some obvious stellar interlopers, for instance. But this is not the end of the story. And this is because in a lot of these candidates, so there's a long-standing debate about the nature of these dual quasar candidates, because you can have instead just lens images of a single quasar by a foreground galaxy, for instance. So what really is crucial is deep, high-resolution near-infrared imaging. And here I'm showing you an example of the first case of a confirmed dual quasar separated by about 4 kiloparsecs at cosmic noon, in which you can actually detect both tidal tails indicative of direct gravitational interaction, as well as extended host galaxies. And this is really conclusive evidence in favor of the merger hypothesis, and ruling out the lensing scenario. On the bottom, we also have CAG-AO imaging, which is better in terms of the resolving power, but HST infrared imaging is better for its more stable PSF, and the fainter, the deeper the surface brightness limit that it allows us to get. So that these two are really complementary to each other. And finally, to put this discovery into context again, so in contrast, all of the handful of dual quasar candidates below 10 kiloparsecs, they are either the so-called near identical quasars, which are most likely still lensed quasars instead of merging quasar pairs, or there are also cases where you see some noticeable differences in their spectral features, but they're still controversial as perhaps projected quasar pairs at large separations that are not actually merged yet. So none of these previous candidates actually has this confirmed merger signature. Okay, so finally going on to the the really highlight of this system is with Gemini spectroscopy, both in the optical and infrared, we are able to measure really key physical quantities for both the host galaxy and the supermassive black hole, and it's a very massive system, almost equal mass merger, hosted by a very, very massive galaxy merger at cosmic noon. And we also have Hubble STIS spectrum, but Gemini is really better in terms of the signal to noise that it offers, whereas Hubble obviously is better for really conclusively resolving the close double cores. So again, these two are really complementary. And moving along, so this is almost my final slide. We also have multi-wavelength confirmation, and both in the X-rays and in the radio to study their accretion properties. And we also have in future James Webb and ALMA observations approved to understand the more detailed host galaxy star and gas contents and kinematics in future. So stay tuned for more results. So this is my summary slide. I wanted to leave you with something to look forward to. So in summary, so Gemini spectroscopy is very, very useful for spatially resolved follow-up for the larger sample of our Volga candidates. And this is, only possible because of the really high efficiency and fast turnaround, and for us to be able to build up a large enough sample to understand the statistics in order to compare with theoretical models. And finally, I wanted to also mention that so this here is an example of a dual quasar candidates in our sample, which has a separation of 0.5 arcsecond. So it's not actually pushing the limit, but it's very faint. It's a target of only R of 19 magnitude. So it's the faintest ever image targets for a low peak. So and it's very exciting prospect for perhaps observing more of these interesting candidates to really find either dual or lens quasars. So I will stop here and take questions.
Okay, thank you, Xin. So we have just time for just maybe one or two short questions. Is there any question from Slack?
No, there's no question. I have a question.
Sure.
So I'm wondering about this obscuration properties of dual agents. So it seems like they do both show broad lines in their spectra. So do you think, but I thought that they are kind of obscured because they're merging. So do you have any idea about these obscuration properties for these dual agents?
Yeah, wonderful question. Thank you. So indeed, in mergers, and in particular gas-rich mergers at high redshift, you would expect a lot of obscuration, perhaps, not just near the nuclear region, but also in the host galaxy of the merger. But in our case, because of the sample selection, we are strongly biased against the obscure population because we require them to be unobscured as a starting point so that we can have the variability in their continuum emission, which means that they are unobscured AGN by definition. So this is indeed one of the limitations of the technique. So in order to get to the really intrinsic population of both obscured and unobscured population, you would need to correct for that unobscured AGN population fraction.
Okay, thank you.
Okay, thank you. I think we need to move on. So thanks the speaker one more time. And the next talk is an invited talk by Jonelle Walsh from Texas A&M. And she will talk about the supermassive black hole galaxy connection. And I will give you 5-minute warning before.
Perfect, thanks. No, it's okay. Great. Thank you. Yeah, so I'm going to be talking about nearby galaxies and their central black holes, and our efforts to try to understand how they co-evolve. In particular, I'll be discussing a large program using Gemini NIFs assisted by adaptive optics. So supermassive black holes reside at the centers of essentially every massive galaxy. And of course, we now have very strong evidence for the presence of supermassive black holes. The best dynamical evidence we have comes from our own galaxy, where we can track the paths of individual stars as they orbit about the black hole. But beyond the Milky Way, black holes have been dynamically detected in about 100 galaxies to date. And from those detections, we've learned that the masses of black holes correlate with the large-scale bulge properties of the galaxy. So two of the more well-studied relations are between the black hole mass and the stellar velocity dispersion, that's m sigma, and the black hole mass and bulge luminosity, that's ml. So these relationships suggest that somehow black holes and galaxies grow in tandem. However, the local black hole mass census is highly incomplete. And that's particularly true for low mass black holes, below about a few times 10 to the 7 solar masses, and for high mass black holes above about a few times 10 to the 9 solar masses. So this leaves major questions regarding the distribution of black hole masses with host galaxy properties. With the present measurements, things like the slope, the intrinsic scatter, and even the shape of the correlations for low and high mass black holes are not well established. Also, as we begin to study a wider range of galaxies, we find surprises in the scaling relations. For example, recent progress detecting high mass black holes in brightest cluster galaxies hint that these objects could lie above m sigma, but there's still too few available measurements to firmly characterize the scaling relations at the high mass end. And the uncertainties are equally severe at the other end, where spiral galaxies with low mass black holes exhibit large scatter below both the m sigma and ml relationships. In addition, we still don't have a good understanding of the primary physical mechanisms that are driving these empirical correlations, and there's plenty of fundamental questions that remain unanswered. For example, do black holes and galaxies grow in lockstep with one another over time, or does the growth of one precede that of the other? So in order to answer those kind of questions, we really do need more black hole mass measurements, especially at the extremes of the black hole mass scale and over a wider range of galaxies that have undergone different evolutionary histories. So in order to obtain robust black hole mass measurements, we need high angular resolution observations that probe the innermost regions of galaxies where the gravitational potential from the black hole dominates. So that region is the black hole's sphere of influence, and its size is pretty small. So for a typical supermassive black hole with a mass of about 10 to the 8 solar masses, the black hole's sphere of influence is roughly tens of parsecs. So therefore, we're really limited to studying only the nearby galaxies with the current observational facilities. So in the past, HST, with its angular resolution, has played a fundamental role in detecting black holes over the past about 25 years. But more recently, progress has been made using adaptive optics, AO, on large ground-based telescopes. So AO can deliver similar angular resolutions as HST, but it has the advantage of being used with a larger telescope, and it operates in the near infrared. So galaxies that were previously pretty tough to observe with HST because they were a little too faint or a little too dusty can be studied in great detail with AO on large telescopes. So given the extensive observational efforts that are needed for just a single black hole mass determination, the approach that has been used for years is to measure one or a few black holes at a time. But what we also need to do, and in order to advance the field, is examine larger samples with homogeneous data sets. And so we're carrying out a large black hole program at Gemini North. So we're going to be measuring black hole masses using stellar dynamical modeling methods in 31 galaxies using AO-assisted NIFs. So the goal of this program is to obtain a more complete census of local black holes in a wider range of galaxies. So here I'm showing a plot of the galaxy K-band luminosity and size, the effective radius. The green dots show the published dynamical black hole mass measurements that have been made, And for comparison, the gray contours are showing the nearby galaxy population. So the point here is that those green points are not representative of the local galaxy population. So at a given luminosity, galaxies with smaller sizes have been preferentially targeted. They just happen to be the easiest to observe and model. But it's really important to sample this luminosity or equivalently mass size parameter space. So as you move away from these points in this direction, a whole bunch of different galaxy properties vary. Things like the stellar velocity dispersions, the mass to light ratios, the bulge fractions, the gas content, the stellar populations, and morphology. Also, galaxies that grow in different ways end up on different regions of this plot. So clearly, we need to do a better job of sampling this important parameter space if we want to get at what the true distribution of black hole masses are with host galaxy properties and try to really understand what role black holes play in galaxy evolution. So here in red are the galaxies in our sample. The red numbers correspond to the images that are shown around the plot. The red crosses are also in our sample. There's just no image being shown. So our sample significantly increases coverage of this important parameter space without sampling that already well-populated region within the dotted oval. So our sample spans a wide range of properties by design. For example, the stellar velocity dispersions range from 60 to 300 kilometers per second. We also have a number of spiral galaxies in our sample. We'll nearly double the number of black hole mass measurements that have been made in spiral galaxies, which is a regime that largely has not been tackled with stellar dynamical modeling techniques. So far we have completed observations with NIFs for 12 galaxies, and those 12 galaxies already enhance the diversity of black hole hosts. So we've observed the largest, most luminous galaxy in the sample, as well as lower luminosity galaxies at different effective radii. And so here I'm just showing some example spectra from NIFs for the most recent 6 galaxies that we finished observing. So this is at the nucleus and then about an arc second away. And so the data quality really are excellent. So from those absorption features, we measure the velocity distribution of the stars along our line of sight. And we characterize that distribution by the center, the velocity, the spread, the velocity dispersion, and then asymmetric and symmetric deviations from a Gaussian, like H3 and H4, or even beyond. And so that's what I'm showing here for 2 example galaxies. So these are maps of the velocity, and we see that both of these galaxies are rotating. These are maps of the velocity dispersion, and we see this nice sharp rise in the velocity dispersion as you move in toward the nucleus, reaching values of about 375 and about 56 kilometers per second at the center. So again, you can see that we do have this wide range of galaxies. We also have some interesting cases. So in the case of this galaxy, the velocity dispersion drops at the center. So that could be an indication of a non-detection of a black hole, which would still be interesting because that would suggest that this galaxy lies well below both the current M sigma and ML relationships. But this could also be the result of a distinct dynamically cold component of stars at the nucleus as well. And so our dynamical models will be able to distinguish between those 2 scenarios. So in addition to the NIFS observations, we also have now completed HST observations for all 31 galaxies in 3 filters with WIFC3. And we've also finished obtaining large-scale data as well. So we have IFU data with LRS2 on the Hobby Eberly telescope, and then even wider field IFUs, Virus P and Virus W on the 2.7 meter telescope at McDonald. So what we're doing is constructing these orbit-based dynamical models. The main idea is that the galaxy's gravitational potential consists of contributions from the black hole, stars, and dark matter. The stellar potential is determined from, say, an HST image. We deproject it, assuming a V-ring orientation and a mass to light ratio. And then we set up a representative orbital library, and we integrate orbits in that potential. We assign weights to the orbits such that the superposition best reproduces the observed kinematics from the spectroscopy and then the brightness from the image. And then we just calculate a whole bunch of different models varying the parameters of interest, like the black hole mass, and we're looking for the model that most closely matches the data. So here's an example for that first galaxy that I showed before, PGC 12557. And this plot kind of summarizes the modeling results. So these are contours of chi-squared as a function of black hole mass and H-band mass to light ratio. So ultimately, we're finding a black hole mass of 2.3 times 10 to the 9 solar masses. And then this is a comparison between the observed NIFS observations and larger scale LS2 observations in black and then best fit model in green. So the model is doing an excellent job of matching the data. So here we actually ran 4 independent orbit-based modeling codes that our team has access to. So they all operate, in that same general way that I described, but the details and the implementation are different. And so the good news is that we are getting consistent black hole masses, and it's also a decent way to try to get an estimate of possible systematic uncertainties too. Okay, so for this galaxy, it hosts a very massive black hole, and it's consistent with M sigma, but is a positive outlier from ML. And that's even when conservatively using the galaxy's total luminosity. So this galaxy is actually similar to a few other galaxies in the literature that I'm showing here in red. So all of these galaxies are nearby early type galaxies that are actually compact. So they do have small sizes, effective radii of 1 to 3 kiloparsecs, for their K-band luminosities of about 10 to the 11 solar luminosities. So that corresponds to stellar masses of about 10 to the 11 solar masses. And they have high central stellar velocities versions. So all of these galaxies host very massive black holes, but they're very different from the kinds of galaxies you would actually expect to find at the upper end of the black hole galaxy relations. So for example, here I'm showing some of the galaxies in the Perseus cluster. So NGC 1275 is the brightest galaxy of the cluster, and it's exactly the kind of galaxy that you would expect to find at the upper end of the black hole galaxy relations. So galaxies like this are large in size, typically effective radii of 10 kiloparsecs or more. They're often dispersion-supported galaxies, showing little to no rotation. So that's in sharp contrast to NGC 1277, which is located nearby, and it's an example of one of those compact galaxies. So as you can see, it looks very different from this galaxy. It is small and flattened and rapidly rotating. And instead, it looks quite similar to the typical redshift 2 massive quiescent galaxies, the so-called red nuggets. So these nearby compact galaxies look very similar to the redshift 2 red nuggets, and so they could be relics. So the redshift 2 red nuggets are thought to grow in size and mildly in mass through a series of mergers to produce the typical massive early type galaxy of today. So these local compact galaxies appear to have taken a different evolutionary pathway, one in which they didn't experience those same amount of mergers to build up the outskirts of their galaxies. If true, then these compact galaxies like NGC 1277 and PGC 12557 could reflect a previous time when the local ML relationship did not apply. Galaxies contained overmassive black holes, and it was the growth of the host galaxy that had yet to catch up. So it could suggest that black hole growth precedes that of the host galaxy. Another possibility, though, is that we simply don't have enough measurements at the upper end of the black hole scaling relations. So as I mentioned before, the form, the intrinsic scatter, all of that stuff is not well established at the high mass end. So these compact galaxies could lie in a tails of a distribution between black hole masses and host galaxy properties that have yet to be fully fleshed out. Okay, so that was an example of a stellar dynamical black hole mass measurement from the large program. And the large program was designed to do that kind of work. But in some cases, we're also seeing very prominent near-infrared emission lines. And so NGC 4111 is an example of that. So this I also mentioned earlier too. So this is a nearby galaxy that's an early type galaxy and it's edge on, and it has this dusty polar ring here. So this galaxy in the NIFS data has H2 emission lines, and this warm molecular gas is embedded in that dusty polar ring. Now, there's also previously published stellar and ionized, so oxygen-3 gas kinematics from CERN through the Atlas 3D survey. So the NIST data probe the innermost regions out to about 100 parsecs, and then the CERN data are larger scale that go out to about 1.5 kiloparsecs. So I already showed you these small scale NIST stellar kinematics. Again, the galaxy is rotating and there's a velocity dispersion drop at the center. The larger scale CERN stellar kinematics shows similar features too. If we look at the H2 kinematics from NIFS, so this is the velocity field, we see that it's counter-rotating with respect to the stars. So this is a map of the flux distribution for H2. So this side of the distribution is the brightest to the northwest, and we're taking that to be the near side of the gas distribution. So this near side is red shifted, whereas the far side is blue shifted, suggesting inflow. And then if we look at the larger scale oxygen-3 kinematics, the velocity field just looks different. So there's a kinematic twist here. And even if you were to try to pull out a global position angle, it doesn't align with any of the principal axes for NGC 4111. It's not aligned with the photometric major axis or the major axis from the stars. So basically, it's in this unstable configuration. So we examined the CERN kinematics a little bit further, applying kinemametry. So this is again that observed velocity map for oxygen-3. And so we're finding that this is actually a result of the superposition of two components. One that is rotating in the equatorial plane of the galaxy, and then one that's rotating in the dusty polar ring. And if we add this up and compare it to our observations, these are the residuals. And so this is supposed to represent the non-circular motions that are present in the dusty polar ring. And we see this kind of hints of a spiral-like structure, also suggesting potential inflow and connecting to the smaller scale H2 kinematics from NIFS. So with this analysis, we propose that this dusty polar ring originates from the capture of a dwarf galaxy. And again, that CERN ionized gas kinematics is the superposition of two components, one that's rotating in the main plane of the galaxy and one that is in the dusty polar ring. We do see the residual non-circular motions in the polar ring has this spiral-like structure, suggesting potential inflow that also potentially connects to the NIFS inflowing gas. So the H2 gas kinematics from NIFS, again, suggests inflow because the near side of the gas distribution is red shifted and then the far side is blue shifted. But some of this inflowing gas may be settling into the galaxy plane and forming new stars, which would result in that velocity dispersion drop at the center. But some of that gas does seem to be reaching the nucleus, triggering a low luminosity AGN. So yeah, this is just an example of how, the large program is focused on those stellar dynamical black hole mass measurements. But with the high quality NIFS data, we can also examine any emission lines and try to learn about black hole feeding and feedback. So very briefly, I want to end with kind of looking forward and giving an example of the potential impact with the James Webb Space Telescope. So we have a JWST program to study the very famous black hole in M87. So M87 has been the subject of a number of black hole mass measurements using both stellar and gas dynamical modeling techniques. So over the years, of course, the modeling methods and the data have improved dramatically, but the most recent stellar and gas dynamical black hole mass measurements continue to disagree by a factor of 2. Of course, we also have this image from the Event Horizon Telescope, and that provides a third independent measurement of the black hole mass. So at face value, this agreement between the EHT result and the most recent stellar dynamical black hole mass measurements, is reassuring. It's a good validation of the stellar dynamical modeling technique, but it does deserve further scrutiny only because both of these methods relied on extensive numerical modeling and built-in simplifying assumptions. So the original, not the original, but the most recent stellar dynamical black hole mass measurement was done by fitting axisymmetric orbit-based models to Gemini NIFS data assisted by adaptive optics. There is room for improvement. So for example, the AGN dominates the inner region within about 0.3 arc seconds. And so the stellar absorption lines are completely diluted as a result. And so you can't actually make reliable stellar kinematic measurements very close to the center. So over here are the observations of the stellar velocity dispersion. And then that solid line is that best fit model from the most recent stellar dynamical black hole mass measurement. And so again, no measurements could be made within about 0.3 arc seconds, and then the model is unconstrained in that region. So with JWST and its very stable diffraction limited PSF and enhanced sensitivity and the need to not worry about residuals from skylines and telluric features, we can do a better job of measuring the stellar kinematics. We are also going to combine this data with new but already in hand large-scale IFU stellar kinematics, and we're going to apply a new triaxial orbit-based modeling approach. We're going to do a more comprehensive analysis of the error budget and include possible systematic effects like a potential mass to light ratio gradient. So yeah, JWST just provides this, exciting, timely opportunity to obtain a precise and accurate black hole mass measurement for M87, which is a key anchor to the black hole scaling relations. And since it looks like I am out of time here, I will just leave up my summary slide. Thanks.
Thank you. Okay, we have time for a couple of questions. So any question? The audience from Slack? No? So during you think about the question, I can give you a question. So 20 years ago, we thought that the M sigma relation is very tight with the intrinsic scatter less than maybe 0.3 dex. Now the sample size is substantially grossly increased, including your measurement, and now scatter seems to be very large. So I was wondering what you think, whether this is, if the scatter is very large, then the correlation may not guarantee causality. So I'm wondering what you think about this.
Yeah, so I think at this point, we can measure the intrinsic scatter based on what we have and the uncertainties that everyone is quoting on their black hole mass measurements. But I really think everyone's doing the best they can. But I think there are a lot of systematics that are not being considered. I think we're getting down to the point where we actually have really excellent data in a lot of cases, and the statistical uncertainties are actually quite small. So I think as a field, we need to do a better job of examining those potential systematic effects and quoting more realistic uncertainties on our black hole mass measurements. That obviously ties into, how you're going to measure your intrinsic scatter. And I think something else that's really important there is doing it both ways, like with M87, right? So, we're seeing a factor of 2 difference, even though it's been measured many, many times in both ways. So I think before you talk about which relation is more fundamental or which one is a causality, or I think those kind of questions, you can try, but I think it all boils down actually to the uncertainties that we're quoting.
Okay, thank you. I think we have a question.
Joel has a question on the Slack. Do you expect the new IFUs being commissioned on juniors will provide any improvement for this kind of work?
It's a great question. I'm sure lots of people here are wondering the same thing. Yeah, so no, I think in our case, we actually don't quite need the really high R, the spectral resolution. We're not trying to study like dwarf galaxies or anything like that. So I think there's room to use it, and I'd definitely be interested in exploring that. I am actually very happy with NIFS. So, it's worth taking a look at. But yeah, NIFS seems very well matched to what we want to do, given its pixel size and, the larger space, the larger coverage, the larger field of view, and we don't need that super high R for the high res mode of GMERS.
Okay, one more short question.
I was intrigued by the amount of difficulty in 4111.
The amount of, sorry, what was
difficulty or complexity you have velocity field. So if you would take the same care for your more regular galaxies where you maybe haven't even checked if they also have a complex structure, would that maybe contribute to the scatter in the relation?
Yeah, so you're right. There's plenty of complexity in the gas velocity fields for 4111. I would never try to measure a black hole mass using gas dynamics for that galaxy, given the reasons that you just said. It's very complex.
No, but I was referring to other galaxies, whether even if you don't have necessarily a hint that it might be like that, but if you look at the larger scale, indeed, that might be, the galaxy might be more complex than what you think, and you actually could decompose, and then all of a sudden mass measurements are different.
Yeah, I mean, yeah, that absolutely could happen. Often what people do for gas dynamics is actually focus on circumnuclear disks. So they really aren't studying gas on large spatial scales. They're really focused in at the center, because then maybe you do see circular rotation and it's easier to model instead of trying to do everything all the way out. That definitely things can get messy with gas. Yeah.
I think we have to move on. So let's thank the speaker one more time. The next talk will be given by Julia Charvector from Gemini Lab. She will be talking about the multi-phase view on agent feedback in the closed agent reference survey.
Sorry, that was the presentation for bothering.
Thank you, and thanks, John. For those of you who haven't seen my talk yesterday, so I'm Julia Scharrichter, I'm based at Gemini North, and today I have the pleasure to talk about a research project I've been involved in for the last several years, which is the Close AGN Reference Survey, or CARS, for which we have also an ongoing project to obtain NIFS follow-up data. So the previous talk was a very nice introduction, of course, also to the NIFS capabilities and somewhat the data I will show in this talk. So this talk is in collaboration with the CARS team, and I would just like to acknowledge the past PI Bernd Husemann, who has been leading the project for many years while at the MPIA, and our current PI, Rebecca McElroy, who is based in Australia. So the primary objective of the CARS survey is to really look into the details of AGN feedback by using a multi-wavelength approach and also a spatially resolved approach using IFU data. And since it's a bit more of a broader audience, I thought I'll spend a few very basic words on what actually AGN feedback is. It's basically the cycle you have in a galaxy driven by accretion from the galaxy onto the supermassive black hole, which could then trigger star formation, grow the black hole, but also ignite an AGN, for example, basically through the conversion of mass into energy. And this energy release in turn can have an effect back on the host galaxy, and the primary processes discussed here are photoionization and heating of the interstellar medium in the galaxy. Feedback can also happen through radiation pressure-driven winds and outflows from the AGN, or through mechanical feedback from jets launched by the AGN. And AGN feedback has become a very integral part of our nowadays understanding of galaxy evolution. However, the observational details of how such feedback works are still controversial, especially on the observational side. And there are some open questions I'm listing here, which are also part of what the CARS survey tries to tackle, which include, for example, over which temporal and spatial scales do such feedback processes operate? Second question is, do AGN suppress star formation in the host galaxies, which has been suggested theoretically, but it's still observationally quite controversial. And the final question is also, how does AGN feedback actually couple to the multi-phase gas in these galaxies? And particularly, just looking at a single gas phase has been shown to not be sufficient to fully understand the impact of AGN feedback on a host galaxy. And there have been, of course, studies, for example, using multi-wavelength surveys to use multi-gas phases in the low redshift universe. The advantage of such studies, of course, is that there is sufficiently good spatial resolution to study really in detail the physics that's going on. However, such surveys are often limited to more lower luminosity AGN because they are studying the low redshift universe, which may not be fully representative of the conditions in the higher redshift universe, and also sometimes limited to a more specific AGN parameter space. On the contrary, looking at surveys in the higher redshift universe, you can probe the AGN luminosities that are more representative of the high redshift conditions where we expect major feedback to happen. However, of course, at higher redshift, the spatial resolution is somewhat more limited to really look into the physics in more detail. So CARS has been attempting to some extent to bridge this gap by looking into some of the most luminous unobscured AGN in the nearby universe. And specifically, the CARS sample has been selected from a parent sample of 99 unobscured AGNs, which are taken from the Hamburg ESO Bright Quasar survey. And these data were selected by using a redshift cut of 0.06. So these are really relatively nearby objects, but still quite luminous. And also we implied selection based on having already single dish CO data available for these targets based on a paper from Bertram et al. So the final CARS sample itself is a selection of 41 sources that were randomly taken from this parent sample of 99 sources. And you can see a gallery of these targets on the right, of the host galaxies on the right. And these data are primarily reconstructed images from Muse data cubes, and a few of these images are also taken from pan-stars. So I've already mentioned Muse has been at the core of the CARS survey, Muse at VLT. Specifically, the backbone of the CARS survey is the optical integral field spectroscopy, which was for most of these targets obtained with Muse at the VLT. And for 4 targets that were also added from observations with PMAS at Palo Alto and VMOS at the VLT. And of course, since I'm talking about the multi-wavelength follow-up, there has also been a larger campaign to follow up sources with the VLA, ALMA, Sophia, Chandra, and MITS at Gemini, which is the part I will talk more about in a bit. And I should also mention that the spatial resolution, just for reference, of the optical IFU spectroscopy is somewhat variable by target, but in the very best cases, we achieved spatial resolutions of 0.4 arcseconds. And in the very worst cases, I think that's one of the PMAS data sets, we achieved spatial resolution of 1.7 arcseconds. So most of the data are somewhere around 0.6 to 1.2 arcseconds. And these were obtained with the Muse wide field mode. So, and before coming to NIFS data, I just want to briefly advertise also the CARS first data release, which happened recently. You can access that under this link here. The first data release includes the optical IFU cubes, plus some higher level data products, which were associated with 3 papers that were published with the data release. And I invite you to take a look at these, just showing a gallery of some of the plots included in the data release. One other aspect I wanted to mention is that the major goal of the CARS survey has been to employ an AGN host galaxy deblending technique on the optical IFU data. Which is, of course, important to study in more detail the host galaxies properties against the bright AGN. And this is done based on a PSF that can be traced in the cubes themselves by using, because these are unobscured AGN, by using the broadline emission from the broadline region of the AGN, which is intrinsically unresolved in these data, to probe the PSF and then perform an iterative host galaxy AGN deblending on this data cubes. And this is included in the data release. So now I will switch to the NIFS follow-up project and the primary goals. And again, thanks for the introduction in the previous talk.
the primary goals were to add basically another multi-phase gas tracer, which is the warm hot molecular gas traced via the H2 lines in the near-infrared K band. And this is gas which is basically at a few thousand kelvins. And then to combine this with other gas tracers, for example, we were also interested in the iron-2 emission, which can be a tracer of fast shocks. And to combine this also with the larger multi-wavelength data we have available through CARS, especially the MUSE and ALMA data and also VLA, to look for outflows in the multi-phase data. And finally, also we can take advantage of the reduced dust extinction in the near infrared to combine, for example, what we know about star formation from the MUSE H alpha data with information we may get from the hydrogen recombination lines in the near infrared data, especially in this case, Paschen beta and bracket gamma for the wavelengths we have been covering. So far we have 4 sources that were fully observed in the 2 bands we had requested, plus 2 sources that were are partially complete in the K bands. And I should also mention that, of course, we wanted to achieve reasonably high resolution. So for the K band, almost, I think, except one data set were observed with adaptive optics through Altair. In the J band, we had been relying on good natural seeing. For the Gemini term, it's IQ 20 in most of these cases. So that is complementary, but somewhat worse than the adaptive optics data we have obtained in the K band. So one very interesting target from the CARS survey, which had been actually followed up with NIFS with an FT program, and really shows the power of combining the multi-phase data we have within CARS, is this source HE1353, which in the MUSE data revealed a very extended ionization cone, which you can see in the green data in the 3-color image from MUSE on the left. The green color here traces the O3 emission. So this was anyway an interesting source because it's an unobscured AGN, but still seen in a relatively edge-on galaxy from our point of view, which means that there is quite likely some major effect from the AGN onto the host galaxy. So this ionization cone, based on our interpretation, is not an AGN outflow, but it's probably gas that was uplifted from the disk through star formation processes and then illuminated by the AGN. However, interestingly, we also see now looking at, if you can see that the VLA contours in blue overlaid on the ALMA image, you can see that there is an extension in the VLA contours, which may suggest an AGN jet. And we have been focusing into that region with NIFS, which is the field of view shown in yellow here. And the NIFS data, interestingly, shows that all of the emission lines we have been detecting, iron-2 was a bit faint to detect, but the bracket gamma, Paschen beta, and H2 lines show like 2 off-nuclear emission peaks, which are about 0.6 kiloparsecs from the nucleus. And interestingly, the southwestern peak particularly aligns with where we see this elongation in the radio contours. So there might be some jet-driven interaction scenario, which is further supported by the kinematics, which can be seen in the lower left, which shows that there is a gradient in kinematics through the southern emission peak, which might indicate some driving of gas through mechanical interaction with the radio jet. Now, combining the NIFS data with the multi-phase gas tracers, you can now see velocity dispersion maps for the O3 ionized gas from MUSE on the left, and for the cold molecular gas and CO120 from ALMA on the right, compared to where we saw the emission peaks in the warm molecular gas from NIFS. It's interesting to note that all of these, that these 2 other gas tracers show higher velocity dispersion in the same region, which really, and also not showing here, but they also have border line wings in this area, which really indicates that we see possibly a radio jet driving a fast outflow in the circumnuclear 1 kiloparsec region of this galaxy by interacting with the dense molecular gas in this host galaxy. So just for the last few minutes, I'll just take you through some of the work in progress with the other NIFS data, just to show you the NIFS data quality and what we are working on. This is another galaxy from the CAST survey that was followed up with NIFS HE2302. And you can see this is a rather disk-dominated galaxy, which has a disk rotation. So on the left, you see the H-alpha surface density, O3 surface density, gas velocity, and gas dispersion from MUSE. In the full MUSE field of view, which contains basically the whole galaxy in all of these cases. And now zooming into the center of the MUSE data, and I'm comparing this now again with the NIFS field of view we can get in the black square. You can see that NIFS now shows the center at a much better resolution. It's about a factor of 3 for the K-band data, which were obtained at a higher spatial resolution. And this shows that all of the lines we have been seeing here show some evidence of a nuclear spiral. And especially looking at the H2, the gas kinematics is somewhat matching what we see in MUSE. The gas velocity dispersion is relatively small, so probably this galaxy shows more like an accretion tracer through the H2. And I should mention that all of these NIFS data are somewhat preliminary in the sense that we are still working on a similar AGN host decomposition for these data, which should much enhance the contrast versus the nuclear PSF on what we see in the more extended gas distribution. A very different source is this source, HE0232, which is a very interesting ring-shaped galaxy, which is known to be a merger candidate with a double nucleus. And you can actually see the second nucleus next to the AGN in the MUSE image. It's about 3 arcsecond from the AGN center. And this galaxy has a very complex kinematics, especially if we zoom again into the center. You can see that, of course, in the double nuclear region, both the gas velocity and gas dispersion are very complex. And then again, I show here the preliminary NIFS data, where we see also very extended gas emission with a similarly complex kinematics. And the analysis together with the MUSE and VLA data is now, especially with respect to the kinematics, is now ongoing. So I'll just conclude by saying that the rest-frame near-infrared IFU observations of nearby AGN play an important role in really tracing the multi-phase gas in the vicinity of an AGN. And this is true for cars, but also there have been many studies using, for example, also Symphony, NIFS, and OSIRIS. And we have already preempted a little bit this discussion in the previous talk. I also wanted to mention that this will also be an important science case in the near-term future, of course, for the GENIUS high and low-resolution IFUs, and also in the longer term, coming back to my talk yesterday, for the capabilities Gemini North will offer with the new AO system, GNAO, and GEARMOS, which is also a near-infrared multi-object IFU. Thank you.
Thank you, Julia. Okay. Are there any questions from Slack? No. 1 minute. So I guess the CARS survey has a very good job on the PSF subtraction. And can you comment on the high Z IFU studies where it's very much more difficult to do PSF subtraction?
I think, well, the advantage we have in the CAST survey, of course, is that we have a very clear detection of the broad line region where we can really use this as a tracer of the point source through the cube itself. So I think this is, I mean, I'm not a very good expert in the high Z studies, but I think this is more of an issue for the high Z studies, especially if you don't have a PSF tracer in the cubes themselves. So you may need an PSF reference separately observed, which then complicates things compared to these pretty high signal to noise near data we have. So this is also, of course, an advantage, again, that we can really use the higher spatial resolution and the better contrast after AGN host subtraction to study the host galaxy gas near the AGN.
Thank you. Any other question? If not, then let's thank the speaker one more time. Thanks. So the next talk will be given by Chongpei Ma, which is going to be an online talk. She's from UC Berkeley, and she will talk about the massive survey, the GMOS-IFU study of the most massive galaxies and black holes in the local universe. So Helen will give you a 5-minute warning with the stars.
Great. Can you hear me okay?
Yes.
Okay, thank you. Yeah, so I would like to give a quick update on the status of the massive survey with an emphasis on supermassive black holes, since that's the theme of this section. And this survey was started really, was motivated by, let's see. Was motivated by about 10 years ago when we used Gemini GMOS along with wide field IFU data to find a black hole that was 3 times more massive than M87 at the center of a very big galaxy, well-known galaxy, NGC 4889, which is the brightest cluster galaxy at the center of the Coma cluster. And, you know, this is the most massive by stellar mass galaxy in the local volume. And Coma is the spectacular most massive cluster in the northern sky out to 100 megaparsecs. So it was not, in some ways, not too surprising, as we have heard, that big black holes live in big galaxies. So the environment wasn't so surprising for detection of such a big black hole. But it was hard to get data with enough sensitivity and modeling to actually detect a black hole. So after this discovery, a natural question was, you know, how many of these things are out there? What is the, you know, number density? And can we maybe get a mass function for black holes at a very massive end in the local universe? So that sort of motivated the start of the massive survey. I'm having some trouble advancing the slides.
In the practice.
Could you just help me?
Yeah, in the practice you clicked and then you were able to move.
Yeah, I tried, but okay. We'll see how far we get. Okay, so the massive survey is a detailed study of the 100 about most massive galaxies by stellar mass within this volume out to Coma. And very importantly, we targeted these galaxies using a mass limited survey. So it's volume limited, and we use K-band, 2 mass K-band magnitudes as a proxy for stellar masses. And so all the galaxies have stellar masses above 10 to the 11.5, and we target only early type galaxies. And the deck cut was -6 degrees, so it's mostly a northern sky survey. And we really want to study not just the supermassive black holes, but all mass components within these early type galaxies, stars, of course, and cold, warm, hot gas, dark matter halos, and the black holes. And we've involved many graduate students along the way, and in particular, we're very excited that we've trained more than 10 undergrads and high school students in getting their hands on analyzing IFU data and doing analysis and so on. And there are a few offshoots of the massive survey with emphasis on, for example, the HST photometry, where we targeted 35 galaxies within about 80 megaparsecs, for which we can obtain surface brightness fluctuation distances. The black hole measurements are only as good as the distances we can get, because we can only measure things angularly on the sky. So we need precise distances to convert anything into a physical number, such as the black hole mass. So this project was led by John Blakesley and Joe Jensen. And so along the way, we actually were able to actually get a new measurement, the most comprehensive measurement of the Hubble constant H0 using SBF technique. And also we were curious about a molecular gas and X-rays, hot halo we heard about, and also the initial mass function possibility of a steepening near the center of these massive galaxies. And so these are all different components of the massive survey led by various people. Okay, so why study nearby massive galaxies? Just very quickly, we have heard a lot about these objects. So they are the most evolved galaxies, and because they're most massive, they're at redshift 0 practically. So they carry, in some sense, the most amount of historical information of galaxy assembly. And they are obviously hosts of the most massive black holes. And we heard a lot about luminous quasars, and some of those should have descend into the quiescent counterparts today in massive galaxies. And these are sites of AGN feedbacks and IMF, as I mentioned, variations in the IMF spatially. And also, as we also heard from Xin Lu, that if they're in binaries, they are the loudest sources of low frequency gravitational waves. So these are potential hotspots on the sky. And why another galaxy survey? Haven't there been enough galaxy surveys? Well, you would think, right, these are the 100 most massive galaxies in our backyard, these 300-pound gorillas should have been studied very well by now. Well, interestingly, actually only about 2/3 of the massive galaxies are in the SDSS footprint. Our galaxies are chosen from the All-Sky Survey 2 mass. And spectroscopically, only 20% actually have SDSS spectra. And remember, SDSS is just a single fiber of 3 arc seconds, but we would like to have a really well spatially resolved IFU data to study the interior of each galaxy from sub arc seconds out to about 100 arc seconds. And we heard about Sauron Atlas 3D survey. So in that sense, for that survey, we are very complementary. They were also volume limited, but and they were studying early types, but their volume was 42 megaparsecs. So our volume is more than 10 times larger, and hence since we are targeting the 100 most massive galaxies, we are very complementary. In fact, there are only 6 overlapping galaxies in our 2 samples, and those are mostly in Virgo because many of their galaxies are in Virgo. And there are, of course, many exciting IFU surveys ongoing, but their samples are heterogeneous. Sometimes they impose size cuts and various selection cuts. We only select based on stellar mass. And also we are very multi-wavelength, and we are one of our essential science goals is to study black holes, and none of those surveys target black holes. Okay. And actually not all of the massive galaxies are BCGs, and they in fact live in a diverse range of environment. Okay, so I want to just focus on black holes for the rest of the talk, but I would like to just highlight, in case you're interested in other pieces of science from the massive survey, here's a list of the publications, and we have some of the ones I've mentioned, and I will from this point on just focus on the how we go about measuring black hole masses in our current results. And Janelle had already mentioned, but just as a cartoon version of the very messy data we have been collecting over the past 3 decades. So again, a central question we're asking is, are there things beyond M87? And yes, NGC 4889 was the first one discovered in the local universe, but the massive survey is meant to target this systematically. Okay, and indeed, NGC 1600 on the left was or is a massive survey galaxy, but it's not a very well-known galaxy in comparison to NGC 4889, but its stellar mass is high enough to be in the massive survey. And we got sufficient high signal to noise data from both GMOS and Mitchell spectrograph on McDonald telescope and McDonald Observatory, and that allowed us to find this 17 billion solar mass black hole, but in a sort of an event massive galaxy which does not live in a rich cluster. NGC 1600 is sort of a, is a galaxy group, but the second rank, the second next brightest galaxy is 3 times fainter than NGC 1600. So it has sort of the characteristic of a fossil group. It doesn't quite satisfy that particular criteria, those criteria people laid out, but the gap is very large. So one interesting question comparing these two very massive galaxy black holes is that they have comparable masses, but they live in quite different environment. So this again motivates further studies to see, is NGC 1600 just the tip of an iceberg? Because the halo mass, is much smaller than the coma cluster, so they should be more abundant. But so it could be a tip of an iceberg, or perhaps this is a very rare object because of maybe galaxy mergers or something that 1600 ate up its neighbors in its evolution history and hence grew to such a high mass black hole. We currently don't know the answer. More data are needed. Obviously, simulations are helpful for answering these questions. Okay, so we have heard about the velocity V, the velocity dispersion sigma, which are the bread and butter kinematics everybody measures. But as Janelle mentioned, for black hole measurements, it's critical to get the full shape of the velocity distributions of the line of sight stellar motions. And we really need the skewness, so we cannot assume Gaussian, but we would like to get a skewness, H3 shown here. Kurtosis, the boxiness, peakiness of the distribution for each spatial bin, H4. And in fact, here I'm showing you a GMOS data of the 5x7 arc seconds on the sky of this massive survey galaxy is a fast rotator, NGC 1453. In fact, the signal to noise is so high of about 100 that we're able to measure out to H8. Of course, when you get to the higher moments, the numbers are consistent with being 0, but we think it's quite critical not to truncate these velocity moments, but rather include them and constrain the stellar orbit models using these moments to avoid spurious behavior in the stellar models. And we discuss a lot of these details in our papers. Okay, and here are some of the real crucial ingredients we need for the spectroscopy. Okay. And GMOS really is incredible for providing us with the central stellar kinematics that are inputted into the stellar models. Okay, so before going further with the black holes, I would like to just showcase concentrating on sigma, the velocity dispersion, the second moment of the stellar. Again, these are all absorption line features. And here is a compilation of the 20 galaxies. And right now, we're just targeting 20 out of the 100 massive galaxy with GMOS and all necessary data for black hole measurements. And here you are seeing sigma profiles for 20 galaxies as a function of the radius from the center of each galaxy. But note that we have plotted the radius in logarithmic scales because we have our data encompasses 2.5 dex coverage. And the magenta is again from GMOS, and the green points are from the very wide field McDonald-Mitchell IFU. And I want to just showcase that we often like to assume, like, for example, in gravitational lensing studies, sometimes, right, we assume the sigma is an isothermal profile, i.e. flat, as a function of radius. You can see when you have very detailed IFU studies, nothing is flat. In fact, 40A74, this is the twin of 4089 in coma, has this very interesting rise at the outer part in sigma. And this could be that we're starting to feel the dark matter contributions there. Okay, so these are, there's a rich amount of information here just in sigma profiles. And let's look at just the first moment velocities. Okay, that's also critical. And here, again, I'm showing the GMOS velocity maps of 20 massive galaxies. One key discovery we had, or outcome of these 20 galaxies is that we are able to measure, as you can see, the velocity kinematic axis, the rotation axis. And you can see that the black indicates the photometric axis. So for some of them on top here, including NGC 1700 that we heard about, they are quite well aligned. On the other hand, at least half of them, the kinematic axis is not along the photometric major axis. That is to say, it's not rotating, the galaxy is not rotating about the minor axis of the photometry. And this is well known as a kinematic misalignment. And here we're showing the distribution of this misalignment angle. And one of the Sauron Alice 3D's main results was that early type galaxies are fast rotators and they're quite well aligned. Now that's for lower stellar mass early types. For our mass range, early type galaxies, you can see there's a long tail of misalignment, in fact, all the way to 90-degree misalignment, indicating that the galaxy is rotating actually about the major axis, so-called polar rotations. So this by itself is very interesting for galaxy assembly people to study, but one important implication of the misalignment is that these galaxies are triaxial in shape. Okay, but before I go on, I just want to highlight NGC 1700 that we heard about has a beautiful counter-rotating stellar core here in the GMOS V velocity map. You can see the outer part is blue-red here, but the very center has a red and blue. Okay, so following up on my comment just now, because absolute axisymmetric galaxy cannot produce kinematic misalignment from the photometric axis. So necessarily they have to be triaxial in shape, meaning, the three principal axes shouldn't be of the same length. So the implication for the black hole modeling is quite deep, because most of the earlier stellar dynamical results for the black hole measurements assume either spherical or axisymmetric gravitational potential. As Janelle mentioned, M87, the stellar dynamical measurement of 6 billion solar masses by Gebhardt et al. Assume axisymmetry. But what we have learned so far is for galaxies as massive as M87 or those in the massive survey, they're very probably going to be triaxial. So we have been spending probably the past 2-3 years really focusing on getting a more efficient Schwarzschild stellar orbit code to work. And we named this the TRIAS code, and it's based on the Remco van den Bosch 2008 code. And here just for some details for the implementations we have added to revamp the code. And triaxial orbits are much more expensive to compute because of these additional stellar orbits called boxed orbits we must integrate. So the whole modeling part for dynamical black hole measurements is becoming more expensive. Another key part is the search strategy, because now we are simultaneously modeling black hole mass, stellar mass to light ratio, dark matter parameters, and now we have 3 shape parameters, A, B, and C, to simultaneously search for. So we can no longer use grid searches, and we are doing Bayesian machine learning algorithms. We're introducing those to speed up the search. So I just want to showcase our 2 recent measurements, and we have targeted the 2 and only 2 very fast rotators in the massive survey. Among the 20 galaxies, we have complete data sets for dynamical measurements. And NGC 1453, as you saw, it has a rotation about 100 kilometers per second. So V over sigma is still, small, about 1/3, but it's a fast rotator by comparison. So here we were able to search in these parameter spaces, and you can see our final result, the corner plot. So we are able to determine the black hole mass is about 3 billion solar masses. So it sits on the M sigma relation. And also we are able to measure simultaneously the intrinsic triaxiality of the galaxy through short modeling. And here I want to just highlight, this is the P is the intermediate to the major axis ratio, and this Q is the minor to major axis ratio. So you can see it's 0.93, so it's slightly flattened, but the short to long axis ratio is flattened by quite a bit. Okay. So just a second example, another fast rotator, as you can see in our velocity maps here. Again, GMOS, beautiful data from GMOS. It's rotating at more than 100 kilometers per second in the core of this galaxy, and we combine this with the Mitchell data. And again, it's about 1.7 billion solar black hole, and we are able to measure the axis ratio. So I think it's very hard to determine the intrinsic shape of a galaxy, obviously. And this technique, through rich set of kinematic and photometric data and extensive dynamical orbit modeling, enable the determination of the intrinsic shapes in addition to these mass parameters. Okay, so I just want to just summarize our ongoing efforts here with the massive survey and beyond. So again, the TRIAS-CO we are introducing, we have also put in a master light gradients, spatial gradients. I'm happy to talk more about this privately. And these are various things we're working on the modeling theory part. Observationally, we still have 18 of the GMOS galaxies that are now slow rotators, and this is made triaxiality even more important here. And we're exploiting other high sensitivity IFUs and also comparing different dynamical tracers. And we're very excited about the M87 JWST data Janelle mentioned. So just a concluding thoughts, again, the sort of the takeaway messages here are that direct local dynamical black hole measurements, so I don't mean quasars or AGN, the width of the emission lines, but here is really detailed modeling. As you've seen, they are very difficult. It comes in one by one, but they really are the low rung of the black hole mass ladders, right? All the reverberation mapping, AGN, quasar, black hole mass estimators rely on calibrations. The virial coefficient has to be calibrated to local measurements. And the black hole world and the local universe have come a long way. The two well-known, best studied black holes have been known since pretty much the late 1970s. And as we heard, the 1990s were the glorious days of using HST slits to measure black holes. But now I think the past decade or so, we've moved to the large ground state based telescopes because of the high sensitivity we need. But combined with IFU and AAO, we're making good progress. But don't forget the modeling part needs to be to catch up with the fantastic data. And that's what we've been working on. And again, I just want to mention excitingly, if these black holes are in binaries, they could be hotspots for low frequency gravitational waves. And if they have some millimeter emissions, unfortunately, NGC 1600 doesn't. They are much larger than M87, some of them, right? But they're about equally more distant. So they could become good candidates for the next generation Event Horizon telescope, which currently can only target Sagittarius A star and M87. Okay, thank you very much.
Okay, thank you. Okay, thank you for the very interesting invited talk. So we have time for maybe one or two questions. Do you have any Slack?
Joel has a questions. What do you see in the matrix IFU kinematic maps for the galaxies that have no identifiable kinematic axis in the GMOS data?
Right, so there are two of them at the bottom, and really they just have no detectable coherent rotations. The V is so low, it's consistent with noise. If you don't have a rotation, you can't determine the axis. So there are two of them at the bottom.
Any other question? How much change in the black hole mass do you see if you apply triaxiality instead of the axisymmetric potential? Have you done any experiment?
That's a very, very important question. And I think it's going to depend on the galaxies. And so we have a big program going on comparing, for example, GEMS measurement, the genes anisotropy modeling versus axisymmetric short-shell modeling versus triaxial modeling. So refer to, for example, the latest 2693 paper, we have comparison. I mean, they can differ somewhat. I don't think they systematically go one way or the other. I don't think we have enough galaxies right now, to say, for example, triaxial always gives you higher or lower black hole number compared to axisymmetric. And but they can differ by some tens of percent. And we're working on the M87 black hole measurement, and we will let you know.
Okay, thank you. So I think that we need to end this session. Let's thank the speaker one more time, and I will give my mic.
Okay, just the usual reminder, if you have a talk in the final session, just to please come up and test your slides before you leave for lunch. And Suresh, if you're here, if you could come up. And then the folks who will be participating in the final panel discussion will be organizing outside. We'll go from there for lunch, and Jen will be waiting out there, and we'll organize people. Okay, have a great lunch. Question about when to come back. Yeah, it would be 1:30. 1 hour.
Very nice. I think I have a question for you about the collaboration.
Yes.
Is anybody already claimed or starting to work on star cluster populations?
No. I mean, you're welcome. Yeah. No, I mean, I feel bad. I definitely have. I mean, we just have.
Yeah.
So yeah, no, definitely no. Right now, all the parts kind of. And they said. She actually.
Okay. Because it would be like obvious contribution. And it would be interesting because like we have all the HST data.
Right. Yeah.
When
All
you
of
get the
that.
star clusters, you can compare like total halo mass, star clusters, get models. And
Yeah.
that'd be super cool.
Absolutely, yeah. And I mean, if you, that's you put us to the
I would have to check. I was wondering that myself. I need to go through my email.
Yeah, I mean, we set up a Google Drive, and I thought everyone had access, but it's possible. But so I can just,
Sure.
there's just not a.
Yeah, I think I was looking at what was shared. I didn't find it, but yeah, send it to me again or check if I'm there. I'll dig into it a bit like that.
So besides the HST images,
We have wider field imaging.
so we so one of my docs kind of went through basically like broke down and made a documentation of all the public wide field stuff, but we didn't have it.
Yeah, so okay, there might be something to look at, but HST data is the place to start. All right, excellent. Okay. So if you want to combine it, you may want to have a fine correction which is low by. These are like. Sorry. So. Then you extension have force. Or the extension one. Okay. Okay. It's on. And then what is it? It's on survey. Got it.
Brilliant.
I'll let you know.
Thank you.
But I did on the one. Oh, you did one. Okay. Already. It's just that if you want to. It's gonna be one by one. Okay, let me see if I can. Okay. I can. Are these files your? They are on the Google Drive. Okay. What I can do is try. Okay. Yeah, so the SP underscore blah. So it gives you a kind of additional. Okay, so let's say. Okay, that should be doable. Yes, there we go. Then I think that we always have, right? Well, yeah, just one and then. So just to show you, I have a quick view, one of the SP questions. Yeah. And you can see that overall for the pure flux, slope of the flux, it's doing a good job. All the others kind of make sense. As for the detail, if I could zoom in, I cannot just yeah. But if I could zoom in, and you want to do a refined adjustment of the orders, you may want to make sure that all the orders are completely straight before you combine them, that they really go on top of each other. That I didn't do very accurately. Yeah. So that's why either you take it from the like that, and then you can do that little adjustment, or you take them from the fifth file, and that's is more involving because of the full normalization. Okay, the dark file is just very connection class, right? Yes. Okay. There's no other. Yeah, it goes down from the yeah. Okay, yeah, I can try that. So, if you have any weird things happening, yeah. Thank you. Of course, no, really, my pleasure. I have another. So, I need to submit a proposal, and it got only done 3. So I submitted phase 2, and now one of the PI is done a sort of selection using Galactic. So he got the new selection after the phase 2. Sure. So what I did, I submitted the previous selection, which is good. But then he wants to change the view or maybe for the targets. So here I'm showing right the red are for the first selection, the one in phase 2. The blue are the other color are the new selection. So the second is pricing now. Yeah. It's the definition that each together. Yeah. These are some observers talking. Yeah. The word right ascension is only known to half of the astronomical community. Yeah. Oh, don't you think? That's
That's the true distinction. If you can explain what is right essentially. Well, you should make a survey.
Whatever the students do with the professor doing theory that decided to give it a try with a telescope and ask for a project in the property here, word Montreal. They didn't.
But sometimes it happens on parallel things are behind the moon. How unlucky do you need to be?
Oh, yes, that's right. Yeah, so you can change target. There's no problem with that. The way to go is to send an email to practical, kind of science operation. And he's the one who has the authority to approve changes.
Okay. So yeah, and is there any like graces will be mounted in September? Yeah. I always do like in a couple of weeks.
Yeah,
so there's no problem. The targets are more or less
yeah. So what they check,
similar magnitudes.
Yeah. So what? Yeah, those are good points. What check is the RA is going to be competing with other targets themselves. Has been requested by other programs and involved. It's very unlike.
Yeah.
It's almost a guarantee that people.
Yeah.
But you cannot just add in your target without it.
What I know is that at that rate extension, there is a huge pressure. That was the feedback that I got from the panel. So a lot of people were.
Yeah, that is correct.
I don't know why.
This one.
Like the rate extension will be hours.
Yeah. I used to know them better. It's not there. Oh. Where is it? Okay. Oh. Okay, so demand with a loss completion rate. See. Oh. It's not there. Let's go under. Well, trying to remember where the popularity of the RA is. So, but the main if you already have and comparable are close time, then
yeah, it's same magnitude, same stellar parameters. Yeah.
Oh, I think I found it. Oh.
Principle for me, making out the global monster.
Look at that. Okay, that will work. So the better the worse.
The rate of 3.
Under those conditions, which are event conditions, if you worsen the conditions So, you remember the conditions that you are?
Right. Yeah, similar to
That's hard to get in.
yeah. Yeah. So
It's a lot
and
asking.
over, yeah.
Yeah.
Well,
Okay.
there's some good, but thank you so much. I will look into the data just to combine or
Yeah.
without some problems. I will download later. The link will not expire, right? The link.
It should not expire.
Okay, but I mean not in 1 hour.
No,
right?
not in a month. Maybe not even ever. We have infinite Google space.
So in principle, I could also do a fast turnaround, right? Like if I want other targets.
Sure.
Yeah.
Absolutely. There's another year of graces, so it's your chance.
Really?
Yes.
I thought we're going to be mounted like on this last semester. Like this will be like the very last semester.
Maybe, yeah, the last or the one before last. So
okay.
Yeah. So it's not long before it goes away.
But then there will be also this.
And then it will be a photo. So that's gonna be yeah. Representation is always a topic. Yes, people ignore it. Yeah, and you have to explain. Like HDA positive just wrong by the course of I knew something was fishy. Let's measure in hours. Something was fishy. Yes.
네. 대전 돌렸다가 네. 얘기 나눠주셨어요? 그 발표 네, 기간 안에 어제 보니까 그 북한이 포스터 앞에 계속 계시더라고요. 페이스북도 발표를 하다가 왜 중간에 인생적 어제 북한이 포스터 계속 계셨어요. 한번 얘기해 주세요. 네.
Hi. No, I might be able to actually call later. Hi. Oh, it's not there? Hi. Oh, yeah. It's okay. Hi. Yeah, so is Haley there? I only have a 15. Hi. Hi. Jennifer, hi. It's all room. Oh, you're making dinner? Oh, wow. Wow, look at you. You are epic. You are epically awesome. And okay. Ah. What is that damn that thing then? Oh, the castle. Yeah. Wow. I feel like I'm inside the house. I feel like I'm a princess in a castle. Ooh, beautiful. Wow. Look at all the stuff they have in the Golden Castle. Whoa, that was brave. Trying to put it back might be harder though. Trying to put them back. Okay, Haley, you appear to be busy. I will try to call you. It's gonna be way later though. It's gonna be like 9:30 at night or something. Okay, I'll call you later. Bye. Are you the virtual chair?
Yeah, do we have a program somewhere? Well, I can get it online, program.
Yeah, everybody except for the one.
Yeah, that's one. So I need to log into the Zoom as well, I guess.
Yeah, I guess. You grew up with your talk, your black outfit. And on the blog. But I have to mention, put on.
Oh, really? Okay, I didn't notice that. I was hiding on the stage. Never thought about that. Watch. Yeah. Are we also I think so. Are we also maybe small Dennis, are we moderating the last discussion part? Also for the virtual one, or not sure? Maybe they want somebody to keep the virtual moderation. I don't know. I'll check. I'll check. Get out of full screen, right? Ah.
Thank you. Yes, thank you so much for inviting me. Yeah.
When you're ready.
Oh, yeah, should I virtually share the discussion? Yeah. Or,
Yeah.
try to just stay here and then just keep an eye on the Slack. I guess, if
Yeah.
there's any
Yeah.
questions.
We're
Do
gonna-
we have a Slack
I
channel?
don't think so, yeah. For the last day. Maybe you could make one
Because-
channel for final.
Oh, how do I make a channel? I am using like X.
Yeah.
And then.
Yeah.
Name.
Yeah, and learning challenging things as well. Like, hey, on that. For the last session.
Yeah.
Yeah, fine.
I don't know what you're at, where they both look here. I didn't know.
How do I do that?
I teach it on a regular basis. I go around, there we go. That's what works, why I have one. Yeah, one of the things that but I understand it's difficult, right? Well, I mean, it's worked out. Program to the class. I agree. I agree. This is a different talk. About modified thoughts about every
Yeah, don't kill yourself.
Okay. You or what? You want to?
Hello, everyone who are already here. I know we had a very short lunch break, so we've decided to extend the start time to 1:45. So you have a little bit more time to mingle and do whatever you have to.
Because I don't see that. Conference reflections and panel discussion. Did I create it so that you can see it? I wasn't sure. Okay, otherwise just maybe you can delete it and overwrite it. Okay. Mm.
Yeah.
Just a quick reminder, we're starting at 1:45, so 5 minutes from now.
Ya, pero ¿sabes? Lo que pasa es que después, a lo mejor sí que animó un montón, ¿veis? Y al final, ahora lo publicó otra persona. Y claro, que estoy ayudando. Y claro, menciona mi proceso y me dijeron, ¿cómo publicaste esto? Porque supervisor me decía, publico y no publicaba.
All right, we'll get started now. It's a few minutes before, but the talk can start exactly at 1:45. Welcome back for the last but not least session of this conference, this wonderful conference. And the topic is galaxy clusters and galaxy evolution. Though we had some of that more local stuff earlier today, this is going to be reaching further out. And I don't know if I have to introduce myself. You saw me up on the stage yesterday, and you saw Yulia on the stage. Will be a virtual chair yesterday and today. So we'll be handling this. And just a reminder that you have two ways of asking questions. One, you can come up to the mic and ask questions, or if you're shy, you're always welcome to write your questions in Slack, and the speakers will address them hopefully quickly. All right, so let's get started. Our first speaker is Jillian Wilson from UC Riverside, and she's the PI of the Gemini Cluster Astrophysics Spectroscopic Survey, G-class, and she'll be giving us an invited talk today. Please go ahead.
So can everyone hear me? Thank you. You may as well clap at the beginning. You may not want to clap at the end. So I'd like to begin by thanking the organizers who originally invited me to give this presentation way back in 2020 at the meeting that was planned to celebrate the 20th anniversary of the Gemini Observatory. Of course, the universe had other plans, but I'm delighted to be here today, this week, in person, and it's nice to be out, at least some of us getting to in-person conferences again. So the survey was a huge, G-class was a huge team effort, but I'd like in particular to acknowledge the contributions of Adam Muzzin, who's now a faculty member at York University. And the silver lining of the 2-year delay is that I'll also be able to tell you some hot off the press results from G-class's daughter survey, Go Green, today. So we've known for a long time that at redshift 0, cluster galaxies are much more likely to be quenched than field galaxies. So the green squares you see there are observations, cluster galaxies, the quench fraction, and the orange triangles are the quench fraction in the field. However, it is very difficult for models of all kinds, they struggle. I'm showing one of the models by a green line. Models struggle to match the quench fraction of cluster galaxies, of satellite galaxies. As you can see it's indicated there by the black arrow. Let's get that on the screen anyway. Indicated there by the black arrow, the models overproduce the number of quenched galaxies, and this is particularly a problem at lower stellar mass. So one of the things we can try to do is go to higher redshift, try to measure quenching over a longer period of time to get some insight into what might be going on. There's clearly something lacking in our fundamental understanding of the physics of how galaxies quench in dense environments like clusters. And that's where G-class comes in. G-class was a spectroscopic survey of 10 rich clusters at about redshift 1 with the GMOS instruments. And what's really fantastic about Gemini is that there are 2 telescopes, one in the north, one in the south. But also the GMOS instrument on both of those telescopes is pretty much a clone. And so we're able to make quite homogeneous measurements, both in the north and in the southern hemispheres. Here is the sample of 10 clusters that were selected from the Spitzer Sparks infrared survey. And GMOS allowed us to get very high spectroscopic completeness. We got in total about 500 members across those 10 clusters. And for its time when we started this survey, I mean, people at redshift 1, they were studying single clusters at a time. So to be able to get observations of so many galaxies in 10 clusters was really quite a step forward, and allowed us to study some more subtle effects that you just can't do with a single cluster. Now, GMOS offers nod and shuffle, which is a rather clever way of doing sky subtraction. And this means you can make observations with much shorter slits than you can with a regular multi-object spectrograph. And that means you can pack in many more high priority targets, potential cluster members, onto one mask than you can with other multi-object spectrographs. I'm showing you there an example on the right from GMOS. These are real masks. There are 52 slits on that mask, and in the middle, a real mask from Keck Elwes. And so you can see that with GMOS, you can get an efficiency of more than 4 times what you can with a regular spectrograph. And that makes GMOS a really efficient redshift machine. So GMOS was quite a large project. It was about 222 hours. And we had 8 allocations of time. And we did this before Gemini offered large and long programs. So we're actually very fortunate that G-class was supported consistently by the US and the Canadian tax, and we're very appreciative for that, that they supported us all through those years. As I said, it's a survey of 10 clusters, and they range in redshift from about 0.86 to about 1.34, about 50 members per cluster. And in addition to the GMOS spectroscopy, we also went and got a lot of multi-passband photometry. We have 12 passbands to pretty homogeneous depth for each of those 10 clusters. When we were designing Go Greenwell, which I'll talk about in a minute, the highest 5 redshift clusters, became part of the go green. And so we were able to go back and get even deeper observations later of those highest redshift 5. So what did we learn? Well, we learned that even at redshift 1, the environment strongly alters the quenched fraction of galaxies. What you're seeing here is a cluster stellar mass function on the left and the field stellar mass function on the right. Black is all galaxies, red is quenched galaxies, and blue is star-forming galaxies. And you can see that there's a significant population of quenched galaxies in those redshift 1 clusters. Now, at the time we started this survey, there were quite a few papers that had been published claiming a reversal of the star formation rate density in clusters. In other words, those papers were claiming that there was a higher fraction of star-forming galaxies in clusters relative to the field. And with this wonderful Gemini spectroscopy, we were able to show that that was just not the case, at least not for this sample of clusters. We're also able to measure the amount of star formation that's going on in the clusters. And we were able to measure that about 45% of the star-forming galaxies, which would normally be forming stars in the field, have actually been quenched by the cluster environment at this redshift. I'll come back to what we think is doing the quenching at the end of my talk. So while we measured a high quenched fraction of galaxies in these clusters, we found that the galaxy scaling relations don't actually depend very much on environment at redshift 1, and I'll show you what I mean by that. So what you're seeing here is specific star formation rate plotted as a function of radius, with distance from the cluster center increasing to the right all the way out to the field there on the extreme right. And the different colored lines, each of those colors is for different stellar mass. So you can see that the specific star formation rate does indeed depend on stellar mass. The lines are of different values, but they're pretty much flat. They're pretty much independent of environment. So specific star formation rate is a function of stellar mass, but lower stellar mass galaxies have higher specific star formation rates, but it really doesn't appear to depend very much on environment at all. Another thing that people commonly plot is D4000, the 4000 angstrom break. Here you see it plotted on the top for quiescent galaxies and below for star-forming galaxies, and again, as a function of stellar mass. Again, we see that the 4000 angstrom break, it does depend on stellar mass. It's a stronger break for higher stellar mass galaxies. Those galaxies are older, but the lines are pretty flat. There's very little dependence on environment. So here I've plotted the mass size relation, clusters on the left, the field on the right. Again, red is quiescent, blue is star forming, and the black lines are best fit scaling relations from 3D HST in the field. And then we've taken the same lines and just overlaid them on the cluster galaxies. And you can see that actually they're pretty well fit by the field scaling relations. Now, there's a little bit of difference. We actually found that cluster galaxies are about 20% smaller than field galaxies at the same redshift. But it's not a big difference. The mass size relation is almost identical between the cluster and the field. So again, not a big environmental effect. Another key finding is that we found post-starburst galaxies to be very common in clusters at redshift 1, and they likely represent a key rapidly quenching transition population. And I'll show you what I mean. Here you see the fraction of post-starburst galaxies, again, as a function of cluster center distance, and with the lines, each different color representing a different stellar mass. Out in the field, there's only a few percent of post-starburst galaxies, a small fraction. But in clusters, there can be 10% of more post-starburst galaxies. And certainly as you go to lower stellar mass, there seem to be more post-starburst galaxies. When we plotted the post-starburst galaxies, they're here in green, on the size-mass relation, we almost couldn't believe our eyes. They fell almost perfectly in this intermediate location between where the quiescent and the star-forming galaxies lie. And not only were they intermediate in size, they were also intermediate in their morphology properties. If you look in the inset there, that's showing Sir-6 parameter. And the green point is the mean value for starburst galaxies, and it falls again intermediate between the value for star-forming galaxies and the value for quiescent galaxies. So it seems, based on this evidence, that the post-starbursts are just gradually fading. They're quenching from the outside in, and their disks are fading. I don't have time to go through all of the findings today, but I have summarized the papers. We've got, including the 3 survey description papers, we've got a total of 20 publications so far from G-class, and I've summarized them there so you can, by topic, so you can go and take a look if you're more interested in learning more of the details. So I'd like to spend the last few minutes of my talk describing Go Green. Go Green, as I said already, is the daughter survey of G-class. And this is a 530-hour large and long program, which took observations between 2014 and 2019, a total of 10 semesters. Because of the deployment of the red-sensitive Hamamatsu detectors, we were able to push out a little bit in redshift to 1.5. And this was a spectroscopic survey of 26 clusters and groups between redshift 1 and 1.5. And again, going back and targeting those 5 highest redshift G-class clusters, but being able to observe their members to lower stellar mass. Again, a large team involved. You can see the names there. Many graduate students and postdocs have contributed to the success of Go Green. So I have plotted the 26 systems there in green, and the tracks are the predicted evolution from redshift 1 to redshift 0, and you can see that what we've got is quite a large range in halo mass. We've got things that are going to evolve into groups at low redshift. We've got some systems that are going to evolve into Virgo mass clusters. We've got some that are going to evolve into coma mass clusters, and then we've got some that would be expected to evolve into clusters of higher mass than coma by redshift 0. So we had a fairly large range in redshift of systems. We had a fairly large range in halo mass. And we also tried to get as large a range of stellar mass as possible, because remember at the beginning I said the quenching effects become particularly noticeable as you push down in stellar mass. The figure on the right shows all the spectroscopically confirmed galaxies that we have. The red ones are quiescent galaxies, and we've managed to push down, we're spectroscopically complete to about a stellar mass of 10 to the 10 at this redshift. We also went and got a lot of multi-passband imaging. We have, again, pretty homogeneous multi-passband imaging for the sample for most clusters in about 14 bands. So this is the fundamental result. This one slide summarizes the largest surprise that we got from Go Green so far. And we find, I'll give you cut to the punchline, that environmental quenching, satellite quenching at redshift 1 is mass dependent, and that's fundamentally different than at low redshift. I'll explain again what I mean by that. So when folks are trying to quantify the difference between quenched fractions in two different environments, they often use this measure called the quenched fraction excess. And as it sounds like, it just means the excess amount of quenching in one environment relative to another. In this case, the excess amount of quenching that occurs in clusters relative to the field. The black points are the go-green points, and the purple line is the measurement made at redshift 0 from Sloan. And it's really a tale of two stellar masses. On the left, you see the measurement for stellar masses less than 10 to the 10.5. The quench fraction we measure at redshift 1 is almost identical to the quench fraction we measure at redshift 0. The relationship is pretty much flat. There's no dependence of the quenching on stellar mass. However, above stellar mass of 10 to the 5, it's a very different story. There's a tilt to the relationship. It's no longer flat, there's a tilt, and that's very different from a redshift 0. At redshift 0, the purple line is still flat. But here we measure a dramatic tilt to that relation. What we're measuring is a dependence of the quenching that is mass dependent. It's dependent on the stellar mass. And again, as I'm showing there, at high stellar mass, that relationship is fundamentally different than is measured at low redshift. And that's the primary result we have so far from Go Green. Now, I'd like to know what's doing the quenching, wouldn't you? This is a piece of work led by Devontae Baxter. He's a graduate student at UC Irvine. And what he did in this paper is he modeled the quenching timescales of the cluster galaxies. So you have quenched fraction on the y-axis, stellar mass along the x-axis of the left panel, and cluster-centric distance along the right, along the x-axis of the right panel. And we found that you could not match the Go-Green observations. The Go-Green observations here are in green. You couldn't match the Go-Green observations with any quenching timescale model that assumed a constant quenching timescale as a function of stellar mass. So we've got timescales assumed from 0 to 3 gigayears. Those are where the colored points are. And the data just doesn't fit any of those models. However, when you assume the model, or when you adopted a model assuming a mass-dependent quenching timescale, he found that that matched the observations quite well. So the model that he's assuming, the best fit model, is those black points you see, and they match the green observations much better than any of the colored lines. So here we have quenching timescale plotted against stellar mass. And the black line is the quenching model that I just showed you in the last slide. And then we make a little correction for pre-processing. We have to make a little correction. So the first thing to note is it's not a flat relationship. As I just said, the quenching timescale is a function of stellar mass, with high stellar mass galaxies having shorter quenching timescales and low stellar mass galaxies quenching more slowly. We make a little correction because of pre-processing, just to allow for the fact that some of those galaxies that ended up in the clusters fell into groups first. So we have to make an adjustment for the fact that those galaxies got quenched in groups before they fell into clusters. And the process that fits best is this gray line. That gray line is a coal gas depletion timescale prediction. And so what it's saying is the best fit to the observations, the red line, is starvation. This analysis is pointing to starvation as the dominant mechanism causing satellite quenching. So galaxy falls into a halo, it gets cut off from cosmological accretion, it keeps forming stars, it just burns through the fuel it brought with it, and when it's burned through that fuel, it starves and it quenches. That's the conclusion of this paper. Again, I've run out of time, but I've summarized that we've got, I think it's 12 papers now from Go Green. We're still working on the data, we're still analyzing it, but I've summarized them there by topic if you're interested in reading more. And this is my last slide. We have public released all of our observations, fully reduced images, the fully reduced spectroscopy, and a number of advanced data analysis catalogs with things like stellar masses and colors and emission lines and all that good stuff. That's all available from the link you see there, and all of the details are in the 2021 Bala et al. Paper. And thank you very much. Stop there.
Thank you very much for that wonderful talk. We have some time for questions.
So you show the cluster galaxies are 20% smaller than the field galaxies. Can you quote the significance of that? And if that's significant, can you attribute to that kind of tighter truncation due to the cluster potential?
So it's a good question, what causes it? It could well be. It could well be. It's possible it's a combination of effects. There's a later paper, and I forgot to say that work was led by Jaslyn Mathrew, who's now a postdoc at Texas A&M. There's a later work that suggests it may be due to ram pressure stripping. Indeed, she has a 2021 paper that I didn't have time to discuss today, but thank you for the question.
Have you had a chance to measure the significance? The 20% is significant, or is it within the statistical error?
Sorry, I couldn't hear the question.
So is that 20% reduction in size, is that significant? How many sigmas?
I can't remember. I mean, not greatly. It's significant, but not a huge result. I can't remember offhand how many sigma. So it was a couple of years since that paper came out.
Hi, great talk and great data. So I was wondering if you could put up the time scale of the satellite quenching as a function of, yes. So I'm probably missing something here. I'm imagining that if starvation is the cause of quenching, then the specific star formation rate for the low mass galaxies is higher. Wouldn't they burn faster through their gas and quench faster? Or is that maybe it's the pre-processing on?
So the low mass galaxies are on the left here. So their quenching time scale is longer than the high mass galaxies.
I'm naively, I would think that they would, if they have higher specific star formation rates, then they would burn through their remaining.
That's assuming they all bring the same amount of gas with them.
So they have lower gas fractions as well.
So there's an assumption here about how much gas a galaxy of a particular stellar mass brings with it when it falls into the halo. I think that's the missing link.
And they're okay. Okay, cool.
Yeah, a bigger potential well can bring more gas, right?
I see.
We have a question on Slack. Joel Rödiger is asking, what role do the Go Green results leave for ram pressure stripping in quenching cluster galaxies? Can those results put an upper limit on the fraction of galaxies quenched by that mechanism?
So first of all, ram pressure stripping is likely to become increasingly important as a quenching mechanism as we move to lower stellar mass. As the clusters, build up their the density of the gas in their potential wells as they go larger halos and the potential wells become deeper. Ram pressure stripping at low redshift is likely to be an increasingly important effect in the quenching. So there's room. This is all I'm saying is this is the dominant mechanism that this analysis is finding at redshift 1.
Well, thank you very much for that. Let's thank Jillian again. So next we'll have another invited talk from James G. From Yonsei University. And he's going to be talking about probing dark matter galaxy clusters at also redshifts greater than 1 using GMOS spectroscopic and HST IR imaging data.
All right. I'd like to begin also thanking the organizers of the workshop, GSM 2022, for putting this wonderful workshop together in this particularly difficult time. Also, I thank the audience for still sticking around. So before I go to introduction, I'd like to acknowledge the contribution from my grad students in my group called the YOUNG, standing for Yonsei Observable Universe Group. In particular, the work that I'm presenting today is part of the PhD thesis by Genia Kim, who graduated this year and is now a postdoc at Oxford University. Because the audience has such a broad spectrum of interest, probably it's not too bad why we need to study high-energy galaxy clusters in terms of cosmology. So galaxy clusters are the largest gravitationally bound objects in the universe. As such, they have been used to quantify the matter content of the universe. So if you examine the abundance in the local universe, you can obtain this elongated banana. The reason why we have this elongated banana is the abundance is function of 2 parameters. One is matter density, and the second is the power spectrum normalization. However, if you add sample from the high G, you can break the degeneracy, and you can tremendously shrink the size of the banana, and you can enable the precision cosmology. Also, sometimes when you find very unusual galaxy cluster, very mass cluster, that can rule out certain cosmologies. So this is a little bit old, but very important result by Bacall and Fan in the year 1998. So y-axis is the abundance of galaxy cluster as a function of redshift. At the time, there was a cluster called MS1054 at redshift 0.8. Given the mass, that existence cannot be reconciled with the matter-dominated universe. So this is pretty remarkable because 1998 is a few years before people talk about dark energy from the supernovae observation. And sometimes extremely massive clusters at extremely high redshift can be a good sanity check whether or not lambda CDM is the most feasible model. So here we can see what we call the exclusion curve. That means if you have a cluster mass that lies above this line, then there should be some trouble with our lambda CDM. So fortunately, in this case, there's no serious tension given by these high-redshift clusters. But when you have more high-redshift samples, it's certainly something you can test to check our lambda CDM model. Oops. Okay, so to enjoy such a game with the high-redshift clusters, the most important thing is, of course, the mass, exact accurate mass of the cluster. As you know, well, there are several pathways to the mass. One can use the richness, loss dispersion, Sunyaev-Zeldovich effect, luminosity, also temperature from the X-rays. But as you know that clusters at high G, they are like teenagers, they are never relaxed. You cannot assume hydrostatic equilibrium. So that means they are not useless, but they need to be calibrated with a proper tool. And here I'm claiming that gravitational lensing is the most useful tool to calibrate those massive processes. So here's one example of a fantastic job by Kim Sharek et al. 2021. X-axis is redshift, Y-axis is Sunyaev-Zeldovich detection significance. So you can tell the relation changes as a function of redshift. So next I'm going to talk about our cluster sample and the data we used. We use 42 galaxy clusters from redshift between 0.8 and 1.8. And that distribution is shown by this solid histogram. They come from many different surveys: optical, near-infrared, X-ray, and Sunyaev-Zeldovich surveys. And 42 is a pretty large photocluster sample, and the sample size is comparable to the largest ground-based programs such as CCCP, Ring the Giant program, and the Locus, etc. Okay, just for the record, this is the list of our 42 clusters, and let me know the list include your favorite target. Lensing can be measured by imaging data, but interpretation is enabled by high-quality spectroscopic survey data. That's where Gemini spectral data contribute. So we utilize the published spectroscopic catalogs as well as our own Gemini data obtained by KGMT program. They allow us to map the galaxy distribution in the clusters, and they allow us to also select the source galaxies. And we can do contamination analysis for the source selection. And finally, they provide velocity dispersion, which is one of the useful mass processes. Then I will just quickly summarize some of the important systematics. So as you all probably have heard of, with great statistical power comes with great systematics control responsibilities. So I'm going to quote a few systematics that may matter to you. First, I like to say cluster lensing at high G is very difficult. So in this image, I want to challenge you to find galaxy clusters. Of course, there's a very obvious one. That's a Lynx nose, but the redshift of the cluster is about 0.6. The mass is 2 times 10 to the 14 solar mass. It's not particularly a massive cluster, but its presence is undeniable. But here, there are 2 more clusters, at least, at G equal 1.2. If I ask you to find that, probably you have to scratch your head. Here is Lynx East at G equal 1.22. Another one, which is the other one, is Lynx West at G equal 1.23. So they are really tiny, and just looking at how thin they are, how small they are, you can sort of imagine how difficult it is to do lensing for those high G galaxy clusters. So they are distant. That means by geometry, the lensing efficiency drops by a factor of 4 in this particular case. And they are small. That means the source density per physical area drops. Here, it's a roughly factor of 10 difference. And you have to rely on galaxies behind these faint galaxies. That means measurement noise increases by another factor of 2. On top of that, clusters grow with time. So you're looking at smaller child galaxy clusters. That means their masses are on average smaller. So lensing signal to noise ratio drops by the same factor. So this is Lynx East that I showed in the previous image. And here comes HST. And without saying too much, you can tell the advantage of using high resolution images for lensing. So here, let's look at this galaxy here. The same galaxy appears very round. Here it's stretched because of lensing, but it looks round because of the PSF. However, if you do a lensing for high G galaxies,
You can ask the same question to the galaxy here that looks very round, but HSD-PSF is also finite, and that galaxy can be smeared by HSD-PSF that looks rounder. That means you still have to care for the PSF modeling. PSF modeling is pretty challenging because HSD orbits around the Earth every 98 minutes. Depending each location, the temperature changes. That means focus value changes. Depending on the focus, your PSF pattern changes. So if you do not correct for the PSF, every galaxy you detect will be stretched along that line. They can masquerade as Earth's gravitational lensing signal. The good news is that it orbits around the Earth every 98 minutes. That means if you know when and where the observation is taken, you can predict the knowledge of the PSF as a function of the location. Knowing PSF is one thing, but measuring shape is quite another because galaxies do not have a simple morphology, especially at high G. They have very different radial profiles. They have come with their own intrinsic ellipticities. So you cannot drive the relation between measured ellipticity and the shear. The only thing you can do is run a bunch of numerical image simulations and calibrate it. So, for example, here is input shear, and here is output shear, and the departure of the slope from the unity is a measure of your bias. The eco-lensing community realized the importance of this test, and they held the so-called shear testing challenging program on a regular basis. And last such challenge happened in the year 2015, and our team participated in the challenge and actually won the challenge. So here I can tell you that at least shear systematic is concerned, we are good up to less than 0.1%. The next systematic comes from the spherical curve. Galaxy clusters are never spherical, especially at G greater than 1, but we assume that they are spherical, meaning that we fit inevitable profile, whatever it looks like. So this is a Marble bias. Fortunately, there's a way to address this Marble bias because we can also measure the projected mass without assuming any projected parametric form of the cluster density profile. Y-axis is the parametric approach. And again, the slope indicates how much Marble bias matters. Given the statistical scatter, currently, we believe that Marble bias is consistent with 1. Okay, so with these tools, we went ahead and measured the masses of all 42 high-G galaxy clusters. And every cluster is a precious baby, and each one deserves 1 hour talk. But for the sake of time, I'm going to just highlight 2 of the most interesting clusters, also present the summary statistics. The first cluster that I want to talk about is this cluster, which has a 2106 minus 5844. The cluster was actually detected by initial SPT survey and looks pretty much round. At the time, the cluster mass was inferred to be 2 times 10 to 15 solar mass. So that's an enormous mass. It's like a 100 kilogram baby, at 3-year-old. But given the redshift, probably the hydroscatic equilibrium assumption could have caused the bias. So you must do the analysis with the lensing and show that I obtained recognition analysis from the HSD data. It looks pretty round, consistent with the round shape seen by SZ. But our lensing analysis based on the initial HST and our near-infrared imaging data allow us to resolve 3 substructures. So how come do you believe those substructures are real? Well, here comes again the role of Gemini spectroscopic data, because we can map out the cross-galaxy distribution, and they support the 3 substructures we found from the lensing. Later, we did a follow-up study with the ALMA. Actually, this is a Sunyavi observation from the ALMA, and the ALMA found 2 significant peaks. corresponding to the north and the southern peak for this galaxy cluster. So the mass that we obtained is consistent with the previous SG result, but still lower than the initial X-ray based measurement. The expected abundance of this cluster is about 1.3 from the 25,000 square degree. That means the probability is about 70%. So it actually does not challenge our lambda CDM. The other interesting cluster is cluster at G 1.8. So this is the highest redshift ever measured with lensing. And you can tell this is the diffuse emission from the Chandra. Our lensing analysis show that actually this might be a merging cluster, consists of 2 mass clumps. The northern clump's mass is about 5 times 10 to 14, and the southern cluster is similarly 4 times 10 to the 14 solar mass. So if you confirm that, it can be very interesting merging cluster at G equal 1.8. The curious thing is, if you add 2 masses together, it's almost 10 to the 15 solar mass. 10 to the 15 at G equal almost 2. That's pretty, big mass. However, the caveat is that the mass uncertainty is large, about 30%. So now is not the best time to claim that we have, lambda CDM is in trouble, but it's worth pursuing. Keep refining the precision of the mass measurement based on deeper observations. Okay, so here is again the exclusion curve. Here we plot every cluster we measured with big lensing, and you can tell some extreme mass clusters, they may have some boundary issues with the lambda CDM. But again, given the size of the error bars, we cannot claim that anything really seriously challenges the lambda CDM. We still have to wait and see when we shrink the error bar considerably. Another important statistic that we can come up out of the 32 galaxy cluster is so-called the scaling relation. So here, E is Hubble parameter, and this is mass, normalization, X-ray temperature, and alpha is the slope. If galaxy clusters are self-similar, the expected slope should be 3 halves, 1.5. And this is our result. So the solid black line is our linear regression from the sample that we analyzed. And the green line here is the same kind of weak lensing study done by Henk Hoekstra, but for much low ratio to sample. And here we find that actually the relation is very similar between the low Z and high Z. And normally consistency is good, but here I'm not too comfortable with the consistency because at G greater than 1, probably the degree of hydrospheric equilibrium or departure from the hydrospheric equilibrium should be different from the one in low Z. So that's something interesting. And the last summary statistic I want to show is the mass concentration relation. Concentration parameter is defined by the virial radius of the cluster divided by the scale radius. Numerical simulations show that as you increase the mass of the cluster, concentration value drops. However, recent theoretical studies predict that if you go high ratio, actually the correlation disappears, and at the extreme end, massive end, actually it shows upturn. That has been considered remarkable and well accepted in the lensing also cluster community. But our observation shows that actually the mass concentration relation still shows a negative slope consistent with the prediction at the low G ratio. Mass concentration relation is very sensitive to cosmological parameters, or also the shape of the power spectrum. So the difference between the observation and the theory is pretty significant and also interesting. But again, this is not the best time to question the lambda CDM because the simulation, embodied simulation, we know that they are not complete. The baryon physics, Asian feedback, stellar feedback, they are all implemented through so-called questionable subgrid physics. So unless we are at the stage to implement the baryon physics, it's too early to call this discrepancy as a problem for the lambda CDM. So here is my summary. While you are reading it, I will take a question. Thank you.
Thank you very much for that wonderful talk again. Questions? And while people are thinking, I have one to ask. So you were mentioning reducing the error bars in the mass measurements. So, going forward, what are the methods you could use to reduce the error bar and get tighter mass constraint with weak lensing?
So the currency in lensing is the source density. Usually we are talking about 100 galaxies per square arc minute. The depth will increase if you increase the depth of the observation. So the normal typical orbits that we use is about 5 orbits per filter. So if you increase that, probably we can have 150, even 200 galaxies per square arc minute. That will shrink the statistical error significantly. Also, Gemini observation will help. Here, we still rely on the broadband photometry to select the background galaxies, but inevitably, that will include the foreground, also the cluster members. But the Gemini spectroscopic data will give us better knowledge of the optimal color range, also the magnitude, the range to increase the purity of the background galaxies.
Well, I'll ask a question. I think this is on if you can hear me. Great talk, James. That was
Thank you.
Very, very good talk. How do you account for the lensing signal along the line of sight? These are galaxy clusters above redshift 1. And of course, there's lensing all the way along that line of sight. How do you allow for that in your estimates of the masses?
Yeah, that's very good point. For every landing talk, you can ask that question and challenge the speaker. That's a concern if you have low G galaxy clusters, because high G galaxy clusters are harder to find, right? So that's a concern if you do lensing analysis for the low G clusters. But for high G galaxy clusters, if there's a low G foreground, it should be very obvious, right? Your spectroscopy survey or the optical image will tell the presence of those low G interlopers. Of course, the situation will change if there's even higher ratio, like a G equal 2 or higher, then there's nothing we can do very much.
Okay, thank you.
I had one last question. Obviously, collecting area and angular resolution is really important. Do you think there's hope of using adaptive optics too?
Definitely, yeah. So GeoMers, I learned how to pronounce that instrument in this workshop. The GeoMers will be a fantastic job. The field of view is not optimal, but that works for high G clusters because the angular extent is a little bit larger than 1 arc minute by 1 arc minute. So if you have a 2 arc minute by 2 arc minute field of view and have a Fourier transform of like 1.1 arc second, I think it would, do a fantastic job.
Right. I guess the other piece that's going to be challenging is the point spread function and its stability across the field.
Of course, yeah. Precision dependent point function. How nasty the variation may be, that's actually the key question.
Okay, let's thank James again. So the next talk will be a remote talk, contributed talk from Scott Chapman. Hi, Scott. Can you see me?
Hello. Yeah, I can. Thanks.
From Dalhousie University. And He's going to be talking about the Gemini follow-up of massive protoclusters at redshift greater than 4 from the South Pole Telescope survey. Please take it away.
Great, thank you. Yeah, so I'm very sorry I couldn't be there in person, but I'm happy to be able to attend the meeting and present some of our work and elucidate a bit how Gemini has helped us uncover the properties of some of these very early protocluster systems discovered by the South Pole Telescope. And what you're looking at on this title page is our firstborn, and something of a crown jewel in the sample, SPT 2349, which I'll go into later with the Gemini observations. But ALMA observations on the right confirmed the South Pole Telescope point source consisted of about 35 ultraluminous galaxies, and our attempts to simulate the core region showed that a good number, 20 of those all very quickly merged together in a gigantic mega merger, building a brightest cluster galaxy. So the challenge then is to figure out the properties of these galaxies and what the evolutionary history is. Oops, how do I advance slides? I just need to figure out, how do I advance my slide? Was that me doing it? Great. Okay, so by way of a brief introduction, for rich galaxy clusters at redshift, say less than around 1.5, we have wonderful, robust methods to detect and characterize these systems. A classic observational approach that Gemini has done a lot of work on is just identifying the red and dead galaxies of the cluster red sequence. But ultimately, you want to measure that hot X-ray gas from the intercluster medium, either directly in X-rays or through the scattering of CMB photons in the Synev-Zeldovich effect. If you go to higher redshifts, then both the detectability and also just the establishment of the ICM itself mean that it's not so trivial anymore to define what the progenitors of these massive clusters are. In simulations, you can certainly trace the evolution of clusters and find what the protoclusters look like. Observationally, you can sort of search for protoclusters. We can search for overdensities of galaxies in any case, but figuring out what their mass scale is and what they evolve to is a very difficult enterprise. So there are various ways you can search for the overdensities on at say redshifts greater than 2, where finding the classical signatures of the cluster are more difficult. Blind spectroscopic or even photometric surveys for galaxies like Lyman break galaxies have identified large numbers of overdensities on the sky. People have also targeted specific rare objects like quasars and radio galaxies. And then more recently, people have started to target the fields around very bright submillimeter galaxies as beacons of rare massive halos that might signpost protoclusters. Another theme that's recently come together is whether these protoclusters might be traced by ultraluminous dusty galaxies, whether they can be a useful tool in identifying and studying these systems. I show a nice cartoon here by Caitlin Casey from a few years ago, showing different phases of cluster evolution from the very earliest protocluster phase, where there's essentially just a inside-out collapse of the core, forming BCG, still very active. And then as you go to more moderate protocluster epochs, you get more activity along the filaments, and the central BCG is already forming. And then we know what happens in clusters later on. It's worth noting that protoclusters are huge on the sky, and we do have tools to characterize that now. Simulations have shown that the amount of material collapsing into a coma class cluster spans about a degree on the sky at redshifts 2 or 3. With Hyper Supreme Cam, you're seeing a Lyman alpha density map here of a protocluster discovered by Lyman break galaxies by Chuck Steidel. And you can see that the Lyman alpha emitters trace a very filamentary structure in projected 2D over this degree scale. But our submillimeter surveys of over this region have shown that indeed this structure is actually traced by ultraluminous galaxies at this redshift 3 epoch. So the South Pole Telescope survey is 2,500 square degree millimeter survey aimed at Sunyaev-Zeldovich and cosmology, but discovered some bright emissive sources along the way here, or about 100 bright thermal dusty sources that it found. So it was fantastic at finding clusters from the Sunyaev-Zeldovich effect, which it was designed to do. These are shadows on the CMB, negative point sources in some sense. And those spanned redshifts up to about 1.5. These, the SPT survey that's been completed is the black squares. And it also found these dusty emissive sources, the majority of which are very clearly, when followed up with ALMA, strong galaxy lenses of submillimeter galaxies being lensed by factors of 5 to 20. But about 10% of them don't show this kind of a signature at all when you follow it up with ALMA, and in fact show that sources, many what appear to be unlensed galaxies contributing to that one SPT source. And when you look at the total flux density in the infrared, that amounts to star formation rates of over 10,000 solar masses per year. So the immense amount of star formation in these candidate protocluster cores. So I showed you the first of this that we found, 2349. It's a redshift 4.3. It was the most obvious one in some sense that popped up. It was ALMA observations very quickly gave us a sense that this was really a big, massive system. In the core region itself, there are about 20 ALMA sources. You can see their emission lines in C+ here. That give something that looks semi-virialized in the core, and then as you get further out into the outer sources, you get outlying halos falling in, presumably. And there are, as I said, about 10% of these things are protocluster candidates, and these are the 9 best candidates we have that are in varying degrees of follow-up, ranging from redshifts 4 to 7. So the key result is basically that there's a huge amount of concentrated star formation in this system, about 17,000 solar masses per year in all those 35 odd ultraluminous galaxies, and a very high density of star formation rate in the core. And then when we use their properties to characterize the halo, it's essentially the most massive halo we've kinematically observed at this high redshift. And it looks nominally like a progenitor of the Coma cluster. Here's Coma and the tracks with redshift of its evolving progenitor. And here's our source measured kinematically. So the key with Gemini I wanted to focus on here is characterizing the galaxies in this system and other SPT systems. So a student of mine, Kaya Roderman, published a nice thesis, a PhD thesis paper, characterizing the properties of all the central core galaxies using Gemini and IRAC multiband imaging, GRIK, and the IRAC bands. And we're able to detect the majority of the core sources and put them on a plot of star formation rate versus stellar mass, with SED fitting giving us the stellar mass. And surprisingly, they don't look like starbursty galaxies at this epoch. They look like typical field galaxies. So their star formation rates are about what you expect for the huge, relatively large stellar masses that she characterized. And even there seem to be a few quenched galaxy examples here. So that was a very powerful use of the very deep Gemini imaging together with IRAC that we need to actually detect and characterize these galaxies. And then the key is then bringing that stellar mass together with the gas mass and dynamical masses from rotation curves from ALMA. So we have all the different components here we can compare to the total of halo mass of the system and see how they contribute. So the stellar mass appears to be within errors. It does appear to be more substantial than the gas mass that's built up from this characterization. And then the two together, of course, are constituents of the total halo mass. So that's another a key way that the Gemini data has really complemented the ALMA analysis, and has shown that about 66% of the halos are dark. Another key breakthrough with from the Gemini data again is searching in the wider field of these SPT systems for overdensities of Lyman break galaxies, and in this 2349 system, you can see the composite RGB from GMOS, which are basically the Lyman break galaxy dropout, and the two redder filters at redshift 4 is GRI. And a clear overdensity was seen in the core region and a moderate overdensity in the larger field, but a good population of redshift 4 candidate galaxies to explore spectroscopically in the wider field, and five in the wider field have already been confirmed by GMOS spectroscopy. But the overdensity doesn't knock your socks off, except maybe in the very core region, and it well, it would classify as an overdensity on the sky by some metric. It seems to be much easier to identify these things from the emissive dusty thermal sources in the millimeter wave survey. A more prominent example is then another one of the systems, also at redshift 4, 0457. Again, the Gemini imaging allowing us to do the Lyman break galaxy analysis and finding it's about 3 times more overdense in the core, and then moderately overdense over the wider field again. The interesting thing about this, the large number of sources in the core, these are comparing these two systems. So these are, the orange is in 2349 are all ALMA sources, and the green are ALMA sources at the time in this new system. And these are the expected gas masses you would measure from all the Lyman break galaxies. It nominally seems to be a bit of a gap in the luminosity function in this system between the bright ALMA sources and the fainter Gemini identified sources. So it's quite interesting. And then finally, one more highlight system I wanted to show is 0303, which we're just getting to now, just starting. The ALMA data is coming in to characterize this system. But we have the Gemini data already, and together with IRAC, it's been very powerful for identifying all the counterparts for the ALMA sources found in this protocluster and characterizing their stellar masses as before. So, and this one show the overdensity in the system in all wavelengths. Looks like it might be more overdense than any other system. So I wanted to throw that out as an early prelude that this may be our new crown jewel once we fully characterize it. Just a few more details then on what we've learned from the Gemini data characterizing the stellar masses in 2349. Well, if we look at all of the mass of all those central galaxies that are destined to collapse into one brightest cluster galaxy, they're already above 10 to the 12 solar masses in stellar mass. And if you compare that to redshift 1 mass of the BCG versus the mass of the cluster, you can see that we're just off scale already. So it's formed all its stars very quickly in the BCG, and then when they merge together, we expect to sort of double the stellar mass. So this is pre-mega merger. This is after the mega merger hypothesized. And then even if it didn't grow at all from the epoch of a redshift of about 3 to redshift 1, where we're making this comparison, it would still be essentially the most massive BCG of any seen at redshift 1. So that's good evidence that we are in fact dealing likely with a redshift, or sorry, a coma class progenitor here, and shows an interesting formation path as well, that the BCG stellar mass is basically there in place, very quickly merging into one big galaxy. Another thing we've been able to use with the very high quality K-band Gemini data from Flamingos 2 along with Hubble at shorter infrared wavelengths is characterize the proto-BCG galaxy, a very compact galaxy that was evident in the K-band already and further evidenced in the HST data. So there's a huge stellar mass present in the core, but it's very, very, very compact, like one of these red nugget galaxies, but at redshift 4. And the simulation shows, though, that the envelope of the dark matter halo is already immense compared to this very compact stellar core. So it somehow must evolve to fill that big BCG envelope so that you see it in stars the way you find them at redshift 1. And then finally, a little cartoon-ish picture here of what happens. So here's the stellar mass measured from Gemini and HST and IRAC for all the constituent galaxies compared to a redshift 1 cluster, kind of a mass function. And then in the sort of 500 mega years, when all those central galaxies merge, you have one BCG sitting down here dominating the core, and then an awful lot of continued cluster mass growth at the larger radius. So yeah, that's the extent of the Gemini studies of these protocluster galaxies, but it's been tremendously useful, and it's a big ongoing program that we hope to continue and really learn about these systems. So yeah, the take home is that the Gemini has been very useful for understanding the individual cluster members and also identifying the wider field overdensity in Lyman break galaxies. So that's the end of my talk. Thank you.
Thank you very much, Scott. We have some time for questions. While people are thinking up their questions, I had one related to the halo mass. I presume, I mean, obviously getting the halo mass right is important to place these systems in context. How well do you think these masses have been estimated?
Yeah, that's a good question. There's all kinds of devils in the details of that, as you well know, but we don't really know how virialized the core region is, or how far we can safely extend out our analysis in radius or anything like that for the kind of kinematical dynamical mass estimates of the halo of the system. Interestingly, we just found out that we were approved an ALMA program to search for the Sunyaev-Zeldovich effect in this particular system with an incredibly deep 90 gigahertz observation searching for the SC decrement. So that would be the, again, wouldn't, because of the poor understanding of the ICM at this redshift, it wouldn't be a silver bullet for nailing the cluster mass either. But yeah, you pointed to the big difficulty in general in protocluster studies is what the heck is the mass scale of any overdensity you're looking at.
Yeah, I wasn't trying to poke holes in it. I was just curious.
Oh, no, exactly. No, it's the most interesting question. You like to dance around the fact that it's very hard to figure out what the mass scale is, and therefore do anything statistical with a sample of these things.
Well, my question was related, but first, thanks, Scott, for a great talk. But today we've seen a whole range of interesting talks that look at clusters from the nearest, today's most massive clusters, to intermediate redshifts, to the talk we heard earlier about the most massive clusters around redshift 2, and now your protoclusters. And so my question is relates a bit to what the previous question. A lot of these studies appear to be sort of pushing the bounds of what classic lambda CDM can do. What do we learn from these protoclusters at redshift 4 that presumably become the most massive clusters at redshift 1.8 and then COMA today? Can you tell us a bit about your comfort level and what degree these are pushing on the ability of the standard model in essence to predict these?
Well, I mean, there's no problem finding halos in the standard model that are massive enough to agree with the things we've found. The issue in simulations in general is finding the amount of bursty star formation going on simultaneously in these kind of systems. It's just completely off scale from what the predictions were. It doesn't really break lambda CDM in any sense, which is basically just the dark halos in some sense, and all this baryonic stuff going on, neither here nor there at some level. So I think it's more of the evolutionary understanding of clusters and brightest cluster galaxies that I think is getting reworked and thought through from finding these kind of systems.
Thanks.
Let's thank Scott again. Now we move to the final talk of the conference. Matthew Bayless from the University of Cincinnati will be telling us about a decade of strong lensing cluster science with Gemini.
Yeah, thanks. And so I'm allowed to go as late as I want since,
Yeah, there's no time.
So I'm just going to go until people start filing out, and then we'll.
Well, no, there is a panel discussion.
Oh, that's fair. It's okay.
Yeah, it's not.
All right, that's a boundary. Fine. All right. Well, thanks for having me. As Suresh mentioned, this is somewhat a summary talk of a lot of different work that's been done with Gemini over the course of effectively my entire astrophysics research career. And so I realized I entitled it a decade, and I forgot how old I was, and it's actually a lot more than that now. That'll become clear. And so all this stuff that I'm talking about is done as a part of the Sloan Giant Arcs collaboration. So this is kind of a current census of the people involved. The folks colored up in kind of orangish brown here. That's my group at Cincinnati who were all presenting work at the meeting. So hopefully you enjoyed what they had to present. But we're a pretty small group, pretty tight knit. And we've been doing a lot of work over the years. It's all built around this idea of finding bright, strong lensing clusters in the available shallow ground-based imaging. So it started with things like SDSS and RCS2, and nowadays it's evolving into things like decals and DELV. And an interesting thing to note here is that we're looking for really bright giant arcs. And so we're actually pretty close to the point where we found them all, because a really substantial fraction of the sky has now been imaged in the optical and multi-band surveys to depths comparable to Sloan or typically deeper. And well, the regions that are outstanding are often very sort of galactic focused, and it's really hard to find extragalactic stuff out there anyway. So we're coming close to a census of what we'd really call all of the brightest giant arcs that are in the observable universe. And it's a pretty good sample to work with for a couple of reasons. I want to first emphasize what I'm talking about when I mention bright. So I've picked out two things here. These are two of the brightest optical giant arcs that are known. One, an arc redshift of 1.7 that we found in 2010 or so, and this sunburst arc, which you may or may not have heard about. It's a more recent discovery, but it's actually the brightest optical giant arc known. So both of these sources were found relatively recently. But if you ever, say, had access to a time machine and wanted to reinvent the order in which we address certain astrophysical topics, you can actually go back to things like the Palomar plate surveys, photographic plate surveys, and find these sources in photographic imaging. So you don't actually need a modern multi-band wide field imaging survey to find some of these amazing sources. Jumps out there pretty obviously. The same thing is true of the sunburst darkness in the south. So I think you'd have to wait until the 70s because there wasn't an all sky photometric survey or photographic plate survey of the southern sky for a little while later, but these were before I was born. And so I think it's pretty fun to think that we're finding things that, when I say bright, are really, really exceptionally bright, and that you can do pretty unique things with. So the backbone, well, I should say, why this is being presented at the Gemini conference is because the backbone of a lot of the follow-up data was taken with Gemini. And so a couple of people have already mentioned the powers of nod and shuffle. Jillian in particular talked about how it's a really powerful technique. We've used a lot of Gemini time over the decade plus to perform a lot of follow-up nod and shuffle spectroscopy of these sources because it's a really, really powerful tool and a really efficient tool. These are not super high redshift clusters, kind of typically redshift of a half, but they are very dense in the sky, and they all show multiple of these, extended strong lensing features. And those galaxies can be at any redshift, right? We're dealing with potential redshift desert effects here. But it turns out nod and shuffle spectra are really, really effective at targeting tons of these things at once. We can even use modified strategies where some sources get targeted for 100% of the exposure, some for half the exposure. That's what's kind of shown here. If you follow this really faint giant arc, you'll note that there are slits catching it at two different positions. Whereas if you were to look at other, say, bright cluster galaxies here, you notice that only gets a slip half the time. It's a really customizable technique that we've been able to use to really, really get effect. And yeah, so I think that's really all I need to summarize there. A lot of the results have come out in a number of papers, but just to give you a sense of what we're kind of finding, I picked out these figures from, I think this is my 2011 paper, so this is not even old news. But it's cluster cores, all obvious strong lenses. And if you can see the sort of horizontal red hash marks, those are all the things that we measure redshifts for. So it's typically 2 to 3 lens galaxies per field. and typically on the order of 10 cluster members, which is pretty impressive considering that each one of these gets observed for something like an hour and a half. So this was an incredibly powerful follow-up tool that Gemini delivered. And then there's the next slide. There it is. When I kind of preparing for this talk was actually fun. I've never given a talk where I just got to look through like all the old observing programs we had and tally things up. So I was a little surprised at how many programs this was, more than I had thought. But this is our Gemini usage to do work with these lensing clusters over the decade and a half. The very first observing program I was a part of as a graduate student is right there in 2007. And then we recently were approved for 2022B. So this is, as I said, spanning pretty much my whole career. But the really cool thing is it's a fair chunk of time, but really, we didn't mean to do like a survey level program, and this isn't really even quite at that level. But I'm really proud to say that we've been quite effective. That even especially for a small team, I was a little surprised, in fact, at particularly how much science this data has produced. So it's been a really great data set to work with. So there's a lot to do with strong lensing clusters, and I try to do as much of it as I can. Broadly, it can be broken down into two things, right? You can use it to study lens background sources. We're using the lensing as a magnifying glass. And then also it's interesting to study the lenses themselves. Again, I do both of these things. And so the rest of the talk is really just going to be a buffet of some of the exciting stuff that we've done and or would like to do with these sources that were all fed by Gemini data. So focusing first on the lens sources, I'll pick out a really fantastic result. This is a spectacular lens source. We're looking here at Hubble imaging, but the source was characterized using data from a number of programs. Just I'll give shout out here to the fast turnaround program that was actually really essential to characterizing the system on a short time scale. Lots of different ways to get great Gemini data. It's a system that when you correct for the strong lensing, you build a strong lens model, de-lens everything, construct what that lens galaxy looks like in the source plane. This is what you see. The scale bar here, kiloparsec. If you're kind of squinting and holding your fingers up and guessing what sort of structures you're resolving here, the answer is that you're resolving little star-forming clumps of some sort that are down to about 30 parsec scales. And this is a redshift 2.5. So this is right smack in the middle of cosmic noon and probing physical scales of star formation that are pretty exciting. And in fact, if you're a person that wanted to understand the diversity of clumpy star formation in galaxies across cosmic history, you can make a plot like this. All the gray points here are tracing out basically measurements of star forming structures in the local universe. So obviously we have no trouble resolving things that are nearby. But up at higher redshift, you see all these colored points. There have been a lot of measurements made over the years trying to measure the scale of star formation, how big are clumps. And you'd see these measurements of giant star forming clouds, which you're really seeing all up here, even up here with a lot of lens systems. But what this source revealed is in fact that there is a high redshift population of star-forming clumps that are on the scale of something more like a 30 Doradus or smaller, the kind of stuff that we also see locally. And this is the kind of thing you'd be completely blind to, right? Without one, looking through a large survey to find all the exciting lens systems, and then going through the work of doing the follow-up to characterize them. And just to emphasize that, how much lensing helps you here. This was a series of 3 papers, and this plot is from the third that Heather Jane Rigby led. And this paper started out as just kind of a joke amongst ourselves, and we were like, yeah, sure, let's write a paper. And it's really just kind of showing what you would see here if you, what we call, candleified this lens galaxy. So what would it look like if it showed up in the candle's deep fields with Hubble? You can imagine doing the same thing if it were in a similar deep field with James Webb, with NearCam. And in both cases, you're not resolving clumpy star formation in any way that's reflective of what's actually there. And so just to drive the point home again, this is really what the lensing gives you. This is actually an extraordinary system. I mean, it's purely coincidental, right? But if you wanted to say, start doing spatially resolved spectroscopic studies of these things, it's extraordinarily well matched to the capabilities of what I used to say was an upcoming instrument, but now of course exists. So really, really spectacular systems that let you do really spectacular things. And again, this all started with a number of Gemini programs over the years. So this is another great system, one of the highest redshift arcs that you'll find from the ground. So this is basically a G-band dropout, redshift 3.6. It's exceptionally bright. The data, all the data shown here are again that hour and a half discovery Gemini data where we're saying, wow, we'd really like to just measure redshifts of things. This galaxy was so exceptionally bright, and also really in GMOS's sweet spot wavelength wise, that the discovery spectrum, which is shown here, was actually enough to characterize most of the physical conditions of this galaxy at redshift 3.65. This is pretty high signal to noise. Pretty much every feature you see is real. Some things not marked or intervening absorbers. That's not really science I do or have time to talk about now, but you could do it with these sources as well. And what we were able to do with this thing was identify families of lines, some associated with nebular emission, those are pretty obvious, others associated with winds from massive stars, others still associated with multi-phase ISM outflows. And cards on the table, I didn't actually double check that this claim is true as of this year, but it definitely was a few years ago. But this is the best diagnosed starburst galaxy above redshift 3.5, which is to say that we can measure its global properties, we can characterize the properties of hot stars, you can measure really any metallicity diagnostic and the terrestrial and optical you like, and then you can even start doing relative abundances of things like neon, carbon, oxygen, nitrogen, which is pretty incredible. The other cool stuff that we'd like to do with these galaxies or there's plenty of cool stuff, I should say, that's still coming. So we've seen a little bit of James Webb data at the meeting. I figure I might as well show a little bit more. That's because two of these sources that we initially followed up and characterized with Gemini had actually made it into an ERS program we had approved. The idea here was to study two unobscured UV bright star-forming galaxies and then two dusty similar star-forming galaxies, all four of which are gravitationally lensed to basically perform spatially resolved diagnostics of star formation, metallicity, ionization parameters, stuff like that. And so, yeah, this program has already taken data, and really it started with Gemini. And a really cool fun fact is that the source, one of the Gemini observed sources from this program was actually the first science target observed by James Webb, which probably was unrelated to the fact that our PI is the project scientist, but I mean, didn't hurt. It was actually purely a schedulability issue. This is an ERS program. It's supposed to be observed early. And if it didn't get observed in June, whenever it was, I think we had to wait like 10 months. And so anyway, yeah, so the EROs happened first, but in terms of targets that technically had the word science attached to them, this was the first, which is pretty cool. And that data looks pretty nice. So this is our near cam and mirror imaging data of that lens source. As I said, it's a UV bright, unobscured star-forming galaxy. And sure enough, when you go into James Webb in the infrared, you don't see a whole lot. Maybe not the most amazing James Webb photo to start with, but it's pretty cool that was first. And again, Gemini is where that started. And so for the last part of the talk here, I'm going to switch gears and talk a little bit more about the galaxy clusters. And this is work that, again, it's a lot of us are involved with within SGAS, and it's really near and dear to my heart. I want to motivate this by saying that a strong lensing sample of galaxy clusters is highly biased, and that's kind of the point. The way that I like to introduce this is to say that, in the cluster cosmology game, often what we're trying to do is connect observations to simulations, and it's always really, really challenging. And so when you typically think of a galaxy cluster sample, SBT, ACT, et cetera, you think of a sample that's selected via some sort of mass observable. You have something that is, scales with mass that you can actually observe, and that's what you count up. And so a mass selection, is emulated here in the simulation results by the sort of purple arrow and shaded region. Now, the simulation result I'm showing here is a plot of mass. So these are simulated clusters in mass, plotted against the strong lensing cross section of those clusters. So basically, how good of a strong lens is that cluster? This is literally the area at a high redshift source plane within which a galaxy can fall such that it is strong lensed, right? It's literally just an aerial cross section. And a strong lensing selection is very different from your typical mass selection, right? SPT sample, you just pick all the clusters above some mass, you have some intrinsic scatter, so you don't have a hard line, but that's your sample. Strong lensing is actually much more like this orthogonal selection in this sort of parameter space, right? You're basically saying, well, is there a galaxy cluster lined up with a background galaxy? That's the sort of randomness of strong lensing. And so at some level, it's a random draw, but it's actually a weighted random draw where this is the exact weight, right? And so the reason this is interesting is because if you look at the values here, within constant bins of, say, cluster mass, you see galaxy clusters have cross sections that span orders of magnitude. So this isn't like a marginal weighting. This is actually quite a strong selection on its own. And it's one that's trivial to reproduce in simulations. You can ray trace simulations. We know how gravity works, and you can produce, a simulated giant arc sample in the same way that we can go into a survey and find the real giant arcs. And so in some ways, this is an easier selection to connect to simulations. But for my purposes going forward, I think it's just a new and innovative way to try and connect data to simulations. And that's what we have been doing a little of and want to do more of going forward. But just to sort of emphasize the point here of what you could do, sort of what tests can you make and what questions can you answer. In simulations, again, this is a simulation result. You could say, ask questions like, how are the strong lensing clusters biased? And one really easy one to understand is that they're biased in terms of orientation, which is to say that if clusters are triaxial and we are observing them, then the sort of typical cluster population will be randomly oriented on the sky because the universe is pretty random. Strong lensing clusters, on the other hand, will be highly biased in terms of orientation. And that's because if you take a triaxial mass distribution, look at it along this direction, you get a surface mass density that's inflated, right? And that's what produces strong lensing. And so this is the kind of thing we can look for in our observed sample and try to test in simulations. You can also look at things like baryonic cooling physics. Can you condense things down into the core with cooling physics? So this is a simulation with a lot of runaway cooling. This is a simulation with no cooling. And you get very clear signatures in the simulations in terms of what happens when you do one or the other. So the shaded regions here basically telling you where you'll find giant arcs in these two scenarios. And what this maps to basically is azimuthal coverage, right? If you have no cooling, you get very elliptical things. You get arcs that sort of line up along some major axis. If you have lots of cooling, you get arcs that cover kind of full azimuthal ranges. These are, again, very relatively simple observables that we can reproduce. And because of Gemini, we have the data to do this. I'm not going to, this is more of a show-off slide. I'm not going to explain all these in detail, don't worry. But these are strong lens models for here, I think it's 37 clusters that Karen Schroen published for us in 2020. Every red curve here is a critical curve. That's a measurement of the surface mass density in the clusters. And all these lens models were characterized by, due entirely to the redshift knowledge that we had from an extensive series of Gemini follow-up programs. That same data allows us to go in and do, weak lensing, strong lensing follow-up of these clusters. These are a bunch of weak lensing plus strong lensing mass profile measurements for, again, a cluster sample. This is from a 2012 paper with Masamune Oguri. You can actually measure masses for these things, out from the virial radius down into the core, just to show that these things do fit quite nicely. The individual measurements are pretty noisy, but if you stack all the clusters together, you get a really, really beautiful measurement. And again, you can perform tests of against simulations. So James G talked about mass concentration. You can measure the mass concentration relation for all clusters, but you can also measure it for strong lensing clusters in simulations because it's easy to find which clusters are strong lenses. So the shaded regions in these plots are the predicted mass concentration relations for strong lensing clusters, and all the red points are the cluster sample I just showed, where you again can directly test these kinds of predictions, and you get results that are reasonably consistent with arguably slope issues. You can also measure, test the predictions for what shapes galaxy clusters are. So you can take your weak lensing measurements for your strong lensing sample, you can stack them, which has been done here in both just randomly stacking them, taking all the weak lensing maps, putting them on top of each other. Or you can take the strong lensing plus weak lensing measurements from the information you actually have, measure ellipticities of individual clusters, align the weak lensing maps along those ellipticities, and stack them there. That's what's shown here. And if you look kind of closely, you can see there is a very highly elliptical signal here that comes out. This lets you actually measure the ellipticity of your cluster sample, which is something you can directly compare to simulations. Actually, sorry, I think this is the simulation result and this is the actual measurement. But really, really cool stuff in terms of direct comparisons. And so that's all I have for kind of past results. The last couple slides are just advertisements of where we're going with this. So we had a recent Chandra large program approved to observe the same cluster sample, which if you've been keeping track, is now a cluster sample where we have strong lensing information, weak lensing information, and now X-ray information. And so this is going to be a great tool for building, sort of extending basically our ability to perform tests of clusters against real data, real clusters, real strong lensing clusters against simulations. The X-ray data are all in, they look great. You can do great stuff with it. Hasn't happened yet, but that's what I'm working on. And then the last thing I have is somewhat of a shameless pitch for what we'd like to do moving forward, which is to fill out our dynamical coverage of these clusters. So we have the Hubble data, we have strong lens models, we have Chandra data, that stuff's been obtained. there's actually a really nice place for us to go back to Gemini and fill in dynamical measurements, both the stellar velocity dispersions of BCGs, so measuring the mass or the gravitational potential on sort of parsec to maybe 10 parsec scales, and then doing cluster velocity dispersion measurements, building up our cluster member numbers. And that's what we're hoping to be doing in the next few years with Gemini. So we've done a lot in the past already, but there's tons more to do. Sorry, I'm a little bit over, but that's all I had. The last slide here was just once again advertising all the work that people from my group have been showing off at the meeting. So we have like a half hour left. If you haven't talked to them but thought you might want to, this is your last chance. Please do. And thanks.
Thank you very much for that nice summary talk. We have some time for maybe 1 or 2 questions.
No.
I actually had a question related to this spatially resolved measurements of your lensed galaxies. I mean, I guess the work that's been done is doing MOS and getting specific regions. What's the benefit of actually spatially resolving it? Can you actually see velocity structure, et cetera?
You mean something like this?
Yeah, something like that. Yeah.
So there's, I mean, a lot of different angles here. So this is no longer cosmology. This is the, star formation, massive stars and star formation and cosmic noon kind of hat that I would have to put on to talk about it. There's a couple of big questions here. One simple question you could ask, which again, I'm not at all a globular cluster person, but you might say, what are these things? Are they globular clusters forming? And so you could imagine going in with near spec, and you can actually can constrain and or measure individual stellar velocity dispersions of these individual clumps, clump by clump within this galaxy. And there's about 35 of them, I think, across the entire structure. So you could actually, with one lensed galaxy here, do a census of 30 parsec scale star forming clumps within a galaxy at redshift 2.5. One of the things that we're really interested in, both here and also with templates, just the James Webb program, is to really address star formation on the physical scales in which it happens. Like, this is a fundamental problem of galaxy surveys. They teach us a lot, right? But in a galaxy survey, the unit is the galaxy. But stars don't form galaxy by galaxy. Stars form giant molecular cloud by giant molecular cloud. And so one of the points of the templates program is to build, literally, maps, effectively data cubes of typical star forming galaxies on, resolved down to the scales that are well below what a field survey can resolve. And so, yeah, it's understanding not just, how stars form on those scales, but the diversity of star formation, the diversity of, say, ionizing photon production, things like that within galaxies of cosmic noon. So there's a whole thing here that there's no Gemini data involved, but the sunburst arc, this thing that I introduced at the start, is really amazing because it is a Lyman continuum leaking galaxy, but it's not leaking ionizing photons. It's like spewing ionizing photons out. And what we've learned from it is, the galaxy itself is huge on the sky. It's extremely bright in the optical, but the ionizing photons are coming from what is from Hubble essentially an unresolved point source, which is to say that ionizing photon escape is definitely not an isotropic process. It's about punching holes and spewing things out on short timescales. And that's the kind of thing that you simply can't get at in like field surveys, right? You can identify the average Lyman continuum escape from galaxies down to whatever your resolution and limit is in a field survey. But the first lensed galaxy we found that's really producing these things like gangbusters is showing us that if you want to know the physical scales in which ionizing photons escape, you're going to be looking at tens of parsecs. So understanding that process is one of the big motivations here with the lensed galaxies.
Well, thank you very much for that wonderful talk. Let's thank Matthew again. And of course, let's thank all the speakers today and I guess the past 4 days. And now I'm going to pass the mic on to Janice.
Okay, what a fabulous last session. So we are going to get set up for our final discussion panel. And we'll have the panelists come up while the stage is rearranged. And Jerry will put up one of the slides. Could someone also increase the lights? Okay, so while all this commotion is going on, I thought I'd say a few words which would then serve as a segue into our final panel discussion. While all of us have been at this meeting, simultaneously, our users committee has been meeting. They started the day before the GSM started, and they actually met in the mornings before we started on 2 of the days. And so one of the discussion items at the users committee was that we wanted to start increasing the cross section between the community and the members of the users committee again. Janelle Walsh, unfortunately, she needed to leave before the end of the conference as the chair, and we'll be sending out information about how you can connect with them in the near future. Next slide. If you want to figure out who is on the committee, in particular those from your partner country, you can go to the website and go into About, and under Governance, you will find the current members of the users committee. So with that, I'll invite the people on the panel up to the stage. Next slide. We actually have a few of the members of the users committee on this panel. Oops. Oh. Yeah, there's a slide with the names of the people on the committee. Oh. Okay, well, we had a list of the names of the people on the panel. But the idea behind this panel discussion is just to give us all a chance to step back. We've seen an enormous range of science, instrumentation, throughout the 4 days of the meeting. A lot of time has passed since we've been able to see each other and connect like this. Virtually, it's just not the same when we're together in person. And so the idea behind the panel discussion is that we're going to reflect collectively on the results that we've been seeing over the past 4 days and think about together what lies ahead for us in the future. So with that, let's go ahead and have the panelists introduce themselves first.
Jennifer Latz, Gemini Director. Victoria Reinaldi, representative of Argentina in the users community.
Nareha from Korea Instrument Science and Space Science Institute, representing Kasi and Korea, and also the Gemini board.
I'm Thiago Gonçalves from the Valongo Observatory at the Federal University in Rio, and I'm the Brazilian representative on the users committee, and actually this is my last year in the committee.
That's convenient. This is my first year on the user committee. I'm Matt Taylor, assistant professor at University of Calgary and former Gemini fellow, and yeah, I represent Canada on the UCG.
I think I only need one of these. I'm Pat McCarthy, the Noir Lab director.
Okay, I'll kick it off here. I just want to say thank you to all of our presenters and all of our speakers. I'm just blown away by the quality of the science, the quality of the talks, especially from our young people, and the breadth. We've gone from, near Earth asteroids to our solar system, to exoplanets, to, distant galaxies, and kind of everything in between. So it just really highlights that you all have been busy while we've been trying to hold this meeting. So thank you for continuing your work. My sort of high level thoughts from kind of reflecting on this meeting and what it's taken to get here is really, I see that the themes that I've been seeing are about connections and partnerships. So it's been fantastic to have this meeting in person. It's been fantastic to be able to have people call in virtually. Last year, we really wanted to have this meeting here, but at the end, we decided it would be great to have a virtual meeting. And that brought in a really broad cross-section of our partnership. So, you know, looking at the observatory, of course, we've got Gemini North and South working together. We're now part of Noir Lab, connecting with other facilities, including the upcoming Rubin Observatory. We've got the strong international partnership, and I think playing to those strengths and building on our partnerships is going to be really crucial for deciding what's next for the observatory. And I'm hoping this panel will say a little bit about what they need and what they are looking forward to going forward. And then the other thing that really struck me was just how Gemini is staying vital, staying very, exciting scientifically by connecting with other facilities. And we saw this over and over again. Gemini complementing Gaia data, Gemini working together with Hubble and now James Webb, Gemini following up LIGO sources, Gemini collaborating with folks from ESO VLT. And I think that really speaks to a broad view of the science that is capable, that Gemini is capable, and how vital it is in the broader landscape. So we, as I said at the beginning, we have a lot coming in the next couple of years, but I think it's time to start looking a little bit further ahead in terms of what do we want for Gemini Observatory, in terms of, what should be the observational capabilities 10 years from now? And how do we do that together as a partnership where we have such a diverse range of science, such a strong and diverse partnership with many different thoughts about what we should be doing and how we should be doing that science. So with that, I would really like to hear from everyone on the panel about their thoughts and reflections on the conference.
Do you mind if I quit my mask? I don't know how to use it to speak in Spanish, imagine in English. Well, first, I want to thank the organizers for making this great meeting, and to the observatory too, because they have invited me, and I'm very glad to be here. Well, I have to say that the participation of Gemini in Argentina has changed the way of thinking and doing science. And well, the access to an 8-meter telescope changed the entire mind of an entire generation of Argentinian astronomers. So our participation here is really important. Thinking about that, I'm coming back with few ideas, but the one that rules them all is that it is mandatory to enlarge the users community. And I feel that it's rather easy or straightforward to do that. First, we need to maintain and improve the exchange with the observatory and between partners too, of course. Well, making joint proposals or the visitor programs are excellent examples to do that. Second, we need to offer courses so people can manage the data in a safely and efficient and fast process. So we need dragons. I will make it a tattoo. In dragons we trust, I will say. And third, we need to promote the participation of young researchers, young students, or grad students, because these are very, very nice meeting they can participate. It is a very warm and friendly meeting for the students and young researchers. So, well, these points apply to every country, I think, but they are especially important for Argentina right now because we have, unfortunately, lost our almost 30% we lost of our time in Gemini, and we really want to recover it and even enlarge it. So the point here is we need to continue making contact with you, with Gemini, with all the partners, because we need to, I insist in recover our time and enlarge our participation in Gemini, because we have everything to do that. I'm convinced of that. We have a very promising generation of observational astronomers. I mean, we have a strong national office. I'm very proud of my national office. They are very efficient, and I will repeat it once and again and again. And most important for us and for every partner, I think we have 20 years. I take my notes. We have 20 years of making Argentinian science growing up with Gemini, and we have during these 20 years we have put our country in the first level with Gemini. So I will insist in making contact and continue growing together.
Okay, thank you for the good comment. And personally, first, so I'm very happy and relieved to see this meeting come to a very successful closure, because this meeting has been actually in a sort of pipeline for 4 years almost. And actually the contract to use this room with the hotel has been signed almost 3 years ago. So I'm very happy. And then also thank you all to make this meeting a very big success. And as you have seen for the last 4 days, I'm very happy to see the many young Korean participants to give you very nice science result. Well, unlike Argentina, we don't have a past 20 years of Gemini experience growing up science for the past 20 years, but we are more than happy to look forward for the future more than 20 years of doing science with you all, making this great partnership even more great. And being in a partnership as a partner, it's important to do a great science as each partner, but the partnership itself should mean a little bit more than that, much more than that. And then making a scientific synergy as a partnership, I think we should work toward and paying much more attention than we used to be. And so we had a brief discussion before we coming to this panel discussion. And then we are more than happy to have any useful input from the audience and the users to make how to make inter-partner collaborations more, how we can promote, encourage between partners, joint proposal, for example, research collaboration, and then so Gemini partnership-wide, how we can make our science collaborations more productive and do more great science. So we are happy to take any good suggestions from you. Okay, thank you.
So good afternoon, everyone. And again, thank you for allowing me to be a part of the UCG for the last few years. Was a great experience, was a great learning experience to see how the inner workings of an observatory happens, especially with Gemini. So it was great. And thank you for allowing me to make some closing comments here on the conference itself, which I think was very interesting. And it was, again, illuminating to see how the community has been using the telescope in recent years, and to see the amazing science that's coming out of it. Of course, I'm more than a little biased towards extragalactic astronomy, just because that's my field and galaxies in general. But it was great to see how everything worked from the beginning of the conference, from exoplanets and stars all the way to galaxies and cosmology, and to see how people were using the instruments in very different ways in their own science. So we saw today some of the work with Zorro, for example, to look at individual stars from at the LMC, which was very exciting. It was very cool data. We saw people working on metal poor stars and making use of graces, and now there's ghosts coming up. So all of the work on high resolution spectroscopy, it was very interesting. And to highlight, of course, some of the work being done by my Brazilian colleagues. We had an invited talk from Delisa Gonçalves. She was discussing her work on symbiotic stars. Also, Bruno Dias was talking about his work on stellar populations in nearby galaxies. Bruno is currently a researcher in Chile, but he also collaborates a lot, and that's a big project in collaboration with many people in Brazil, Leandro Kerber, Beatriz Bambui, and Francisco Maia, and others. So it was, on one hand, it was very interesting to see the very creative use that people are making of instruments like Zorro and Maroon X. Some instruments I'm definitely not familiar with because they're very much outside my field. But at the same time, we saw a lot of GMOS science coming out of here, and GMOS is, I think it's still a great instrument, although it has been going on for quite a few years now. Both GMOS North and GMOS South, they remain very relevant, and I think this is one of the big conclusions that we can take out of this conference, is how GMOS is still very much a big chunk of Gemini science in general. And I would like to emphasize that in our case, being from Brazil, of course doesn't have as much access to 8-meter and 10-meter class telescopes as the US maybe. So Gemini for us is a huge part of our observational capabilities in general. And having something like GMOS, and of course also the infrared instruments as well, which are in heavy use by our community, all of that, I think it emphasizes that since this is the main big telescope that we have access to, having something that's so flexible, it's really conducive to a lot of the different scientific goals that we have in Brazil. So it's great to see it moving forward, and I think this conference has proven that this is still very much the case, not only for Brazil, but we saw a lot of incredible science coming out of clusters. We saw Go Green, we saw Mabelius's talk, we saw a lot of people using GMOS for very different cases, and very highly relevant and high impact science as well. And moving forward, I think there's a lot that has been discussed on the ECG as well, on this strategy to engage the community. So I think one of the main strong points that we can have trying to bring in more people is that there are a lot of very exciting new instruments coming online. There's Ghost, there's Scorpio, of course, which is very interesting. Pretty soon we'll have Germos as well, which is an incredible instrument that I'm very excited about. So I think that's a great way to bring in new researchers, and so that we have new opportunities to use Gemini in exciting and innovative ways, while at the same time not losing track of GMOS and something that's versatile as it is. And I think just to close off on my comments on the on the aspect of collaborations, I think there's a lot that can be done. I really like the joint proposal strategy that Gemini has, because it, on one hand, it allows us, of course, to do more science, because we have let's say a limited amount of time that we can apply for in Brazil. But I think the joint proposal allows us not only to do a little more ambitious science and have more ambitious projects, but at the same time, it serves as this tool and opportunity that we have to connect with researchers from the US, from Argentina. I have a lot of collaborations with Argentinian astronomers now, and hopefully more interaction with Korea in the near future. So that actually it encourages people in Brazil, and especially the smaller communities, to interact with people from other countries and other partners, so that we can do very interesting science together. I think that's a very positive aspect of Gemini. So that's it. I'm really looking forward to seeing what the upcoming instruments are gonna do. It was very exciting to see all of them being presented here, and I certainly look forward to using a lot of Gemini in the future as well. So thank you.
Okay, can you hear me? Okay, that sounds good. Yeah, so first of all, I want to obviously repeat the gratitude for putting on the this great meeting, inviting me and allowing me to serve on the ECG. This is a great opportunity to get a new perspective on Gemini, different from the one that I had before. I was asked to be on this panel nominally to give perspective from the Canadian community, and to be honest, I'm not sure how comfortable I feel speaking for the country as a whole, at least not quite yet. So instead, I'm going to speak from my own personal perspective. And that perspective is of a former Gemini fellow who failed in the job market the year before coming to Gemini. And so coming there it was a really special experience, and Gemini gave me absolutely every opportunity to achieve success into my next postdoc and then into the position I have now. And they showed a keen interest in my success. And I'm not the sort of person to ever forget a favor. And so I showed a keen interest in Gemini's success. And one thing I'm taking out of this meeting is that that interest is very satisfied. Gemini is in a good place, and I think at least in the near and medium term, it is absolutely heading in the right direction. I'm blown away by the diversity, not of just the science, but of the community, from the partner countries, from students to postdocs to senior faculty. The diversity of people, the diversity of science is really something that is unique to Gemini, and it really warms my heart to see that happening, and to see that the strategy in general is really to play to Gemini's strengths as a uniquely nimble and flexible observatory. And I think if that focus is maintained, then the future is bright. One other, I guess, reflection that I've had personally is this will be my first opportunity to really speak in detail with members from the other partner countries and start to understand their perspectives. You know, I'm coming from Canada, and I'm gonna lump the United States in there as well as one of the nominally larger partners. And you know, we have our own challenges, we have our own concerns, but the small partners have their own unique set of challenges and concerns that are fundamentally different than those from the larger partners. And I think it behooves us from North America in particular to maybe take our North American hats off and try to put on the hats from the other partners to understand their perspective and to better understand their challenges and their concerns. Because I think if that cross communication happens and we have a better understanding of those perspectives, then that cross-pollination and the joint proposals and everything will just naturally flow from that. So I think just to close up, that's something I'm going to be thinking very carefully about on my way home, about how to promote that and how to address that. And I suggest the rest of you from particular North America do as well.
Thank you, Matthew. That was really well said. It's a great message. Just a few thoughts here before we open things up. Just to echo what Jen said, I'm really impressed with the depth and the breadth of the science we saw this week. I was impressed at how many people are doing very broad science programs, but Gemini provided the key data they need to get their science done. That was really quite impressive. I learned that instruments that I thought were niche, like IGRINs and the speckle cameras, are actually very broad in their science scope. That was really impressive over and over. Instruments we might think of as old, like GMOS and GNIRS, are still vital. That doesn't mean they'll last forever, but they're still providing a lot of great science for people. One of the things, though, that I thought was most telling was the remark by Stefan from Max Planck, who said, coming to Gemini, he encountered that the group was warm, friendly, and welcoming. That was his experience in observing with Gemini. I think that speaks to the excellence and the dedication of our staff. We often think about the instruments and the software, but it's the staff who really make the experience work. And we've seen that this week, all that they've given us and all that they give the user community. And as you just described, the science that they do as well, and how important that is to them. So I think as we go forward, it's really important to make sure that we hold on to that Gemini culture. It's special. If we lose it, it's very hard to get it back. And it's important that we hold on to the identity of Gemini as an international partnership, because it's vital to all of us, as Matthew said, that we recognize and we sit in each other's seats or stand in each other's shoes periodically and think about what Gemini means to them. We have a new wave of instruments coming thanks to the hard work of our partners here in Korea, Canada, and elsewhere. It's going to be a really exciting decade as those new capabilities come online. But we've learned it takes about 10 years from concept to delivery for an instrument. So we should start thinking, what do we want in the 2030s, in the era when web will be mature, where the ELTs will start to come online? And we should think, what's the right set of adaptive optics capabilities that we want that will be long lasting, because we don't want to continually rebuild, and what's the right set of instruments? And that information has to come from you, the user community, and the representatives from the various partners, because ultimately Gemini is and must be responsive to the community on all scales, whether that means you've got to have something observed tomorrow night because it's a transient, or you need an instrument or a capability in 10 years. Ultimately, our job is to respond to the aspirations and the need of the user community. With that, I'm happy to turn it back to Jen and then open the floor to discussion within the panel and input and comments from the floor.
Thanks, Pat. I think I would just like to open up to anybody who wants to comment on anything said here. But in particular, I'd like maybe a bit of a forward look. You know, what do you want to see happen next? What should we be aiming towards, either in terms of science, instrumentation, partnership in the next decade? Don't be shy.
To comment, please come up to the mics. Don't be shy.
Zach is never shy. Come on up. Zach.
Hey, great discussion. So I actually just want to turn the question around on Pat and pose the question directly to the six of you up here about what instruments we want to see, because we have a unique opportunity right now with JWST showing off its first light images and the first science images, and the public, especially in the US, you know, saying, okay, astronomy is really cool, and we don't think $10 billion in a telescope is a big investment. We need more. So thinking ahead to, you know, the next generation, maybe even if it's just, you know, upgrading GMOS as it is an aging instrument, and, you know, upgrading either Altair significantly beyond like even GNO. So I was just wondering, like, what instruments you all would like to see, because like for me, I really want speckled cameras, and we already have those. So just wondering what you all think.
Maybe I'll take a stab at that. For me, we've just completed our 5-year plan and have been trying to map out what what we should be looking at in terms of the next generation. And there are two ideas on the table really at this point that would be great to get community input and feedback on. The first is the idea of bringing an adaptive secondary to one or maybe both telescopes. And we've started doing the feasibility study. You saw Paul's great talk there. The next step would be to do conceptual design, but also to, broadly understand what the science gains of that would be, particularly with the near-term updates in adaptive optics at Gemini North and South. The other, as Thiago alluded to, is start thinking about our optical workhorse capabilities. GMOS, north and south, still dominate the proposals, both telescopes, but they're aging. And so we need to understand if that is a capability we still want going forward, whether that should be simply updating GMOS, or if we want something that's, next generation, has something that's a little bit different, maybe complementary to Scorpio. And again, the science cases and thinking forward to what the landscape looks like in 2030 with ELTs coming online, what is the niche there for Gemini? How do we, are we going to continue to be the rapid response agile observatory? And so that might aim for a somewhat different kind of science case or science requirements for that next instrument, or do we want something a little bit different? So I would love to hear from GMOS users in particular. What do you want? Yeah, go ahead.
I'll second that and give you a proposal, which is adaptive secondary with GMOX behind it, so you can do rapid TOOs with MOS. And EMCCDs to lower the noise. Basically just squeeze everything out of the hardware that you can. We can't change the mirror, but we can change about everything else.
I'll take a stab at that, and I'll really support the second one, the whatever type of upgrade you could do to GMOS, just because, as I said, speaking on behalf of the Brazilian community, this is something that it's one big telescope that we have access to, and GMOS acts as something that really works for a lot of people in Brazil. So an upgraded GMOS would be great. I think, especially with if we think about the upcoming instruments, there's a lot of in the next decade or so, there are going to be a lot of very wide field surveys. Of course, Rubin, we heard a lot about it, and then there's going to be Euclid and Roman. So follow up of those fields with the high multiplex, just optical multi-object spectrograph, and would be incredible and it would be useful to a lot of people in the community. And as we said in the UCG, I think Scorpio is a great instrument. I'm really looking forward to applying for time with it, but it doesn't have the multiplex capabilities that MOS, the GMOS has. So an upgraded GMOS, I think, would serve a big chunk of the user community of Gemini. So I would really put my money on that if I could.
You're here, and if I could build on what Brian said, we can't make the primary mirror any bigger, but we can make the images smaller, and that's actually worth a lot too. And if we can have a standing adaptive secondary mirror that you just don't even think about it anymore, it's always making the images a factor or two sharper, you'll just come to appreciate that, and it's just part of the landscape. And that, and coupled to the next generation optical spectrograph, would be a really powerful combination.
I just want to push on the adaptive secondary some more. I totally agree with the plan. And one other benefit that it has is it really makes Gemini an IR optimized telescope, because especially if you use adaptive optics, it's just has much more sensitivity without having the additional thermal background. And just baselining an adaptive secondary that can provide some good correction in the optical as well as the infrared, I think will definitely replenish the capability of the observatory. And the other thing to consider is, in the era of the ELTs, if we look at how things have progressed when 8 to 10 meter class telescopes showed up and how they impacted sort of the 4 to 6 meter class telescopes, as they moved more towards survey type science, whereas the larger telescopes focused on individual objects, because that was kind of the low hanging fruit. So that's something else to consider, and perhaps the upgrade to GMOS to make it much more highly multiplexed, better image quality, maybe additional spectroscopic modes that allow for higher spectral resolution, because you're basically optimizing the observatory to get more flux into a slit. Might be a beneficial direction to go. Here.
Hi, Bruno Diaz. Thiago was mentioning that I'm broadly using GMOS here for 3 national projects, including Argentina, Brazil, and Chile. So my 2 cents here, I would say, on the top of everyone else's points here, is that this is the workhorse, right, of any telescope. So any telescope should have this. So for example, Force 2 at VLT is also aging. So they're planning an upgrade now, but they have 2, right? So they have the Force 1 and Force 2, so they keep going to observations there. So I think that if you want to do an upgrade of GMOS, we have to stop operations with GMOS. So that we have to think about that and how this will impact the science. But thinking about, is it worth it to do this, even if you have like Force 2 for like international community or not? I think that's a matter of access, right? So because we have a guaranteed time for this community. So is this community using really GMOS? I think that the answer is the right answer. We have this thing. So I think it's worth it to go for an upgrade, but maybe thinking about like really upgrade, like everything, like thinking about new capabilities and rethink about the needs from the community. If I may add another point on the top of this, since I'm here, is from the tax, because I mentioned that I'm managing like 3 tax there. So when you apply for time, you have to apply actually for 3 communities and 3 evaluations, and sometimes you have actually completely different answers from this tax. So I don't know, sometimes you get first place in one community and then like very criticized in another community. So this is something like difficult to manage. I do not have a proposal how to change it, but I mean, this is a point that I want to raise here for discussion maybe, because I don't know how the international tech manages that when it comes to handle, but maybe when you have this type of joint proposals, try to have an international tech, I don't know, something like glue together and something more smooth procedure, because I think that the idea is collaboration, right? So if you have like different countries here, it's not that each community has its own science, but can collaborate as well. So as like Matt said, okay, so think about the necessities of other communities as well. I think that scientifically you gain a lot with collaborate. But it's okay.
Thanks. Those were really great points. Anybody want to comment on those or have other topics? Yes, please come.
So I'm completely external, of course, but I wonder if a key ingredient couldn't be in the future also really to implement a 15% of guaranteed time observations, because there will be a lot of instrument builders who probably run out of telescopes where to put their things. Everything will concentrate on the ELTs. So you might actually want to draw groups in that Gemini becomes an attractive place to think about. And a similar thought, maybe if you think about the ELTs, they come online, everybody gets 3 hours of telescope time for the next 10 years. Maybe one should think about that the smaller telescopes can be the place where you can implement long, big projects, 100 hours, 200 hours, which you'll never get on an ELT in the first 10 years, so to say.
Yeah, thanks, Stefan. Yeah, we didn't talk a whole lot about our visiting instrument program, but that's been wildly successful for bringing external teams, external instruments in exchange for telescope time. And, just looking ahead at the budget and what some, if we want to have ambitious projects, I think collaborations that bring in a partnership, much in the way that the GERMOS and GNEO project is being funded, is going to be the path forward for the next generation of instruments. But yeah.
Here.
Yeah. Go ahead.
Let's also make sure that, is anyone online with questions? Are you watching, Julia? Okay, great.
So I'm gonna just bypass because so I think everyone in this room noticed a lot of talks based on the visiting instrument, data from the visiting instrument, Allo-Package-O, Maroon X, and iGreens. The problem is we don't have science port to host like extra visiting instrument anymore. And now like we're gonna have like Maroon X becoming facility instrument, and in the south and north, we are all expecting like the big facilities, right? Like Gemini South, we're gonna have Scorpio, and Ghost will be used a lot. So I don't know how much time those visiting instruments will be, allocated. So as a development person, I wish we can have like more science for like extreme change for those front end design, but I don't know if it's possible. But so something to think about, or more creative way to like feed the like maybe fiber, the extra port to use the fiber. Like Maroon X can be installed more often, not just the block schedule, because Maroon X will be like successful for like next 15, 20 years. But if it has to compete with other facilities, then I don't know, we'll lose a lot of users as well. So that's, my 2 cents.
Thanks, all very good points. We have to think about the sustainability and long-term viability of the instrument program.
Now for something completely different, I have a crazy question about partnership. So 22 years ago, the family was established. The partnership included the UK and Australia, who later preferred to leave the partnership. And we were very fortunate to have Korea, not only to replace them, but to bring something completely new. And I would agree with Narae when he says that Korea made Gemini even better. So looking at the portraits that we have today, is there anyone missing? Is there anyone else you would like to see joining us? Is there a country you're having in mind that you think has a lot to contribute and could grow a lot joining Gemini that you would like to see sitting next to you?
India. I think India is doing fantastic things these days. I think with Astrosat, the great science that's coming from UVIT, I think adding the UV profile and having the UVOIR kind of in the full partnership would be just outstanding.
And it's a TMT partner.
Who's going to make the phone call? I think it's an interesting suggestion.
Should we conclude? I know it's pretty late and we've got other things to do here. Does anybody want to have a final word? Janice.
Let's just give our fantastic panelists a round of applause.
So please don't disappear just yet. We have a few thank yous, but we'll keep it really brief.
Yeah, festivities. Can we have the lights turned on completely so we gradually wake up for our last round of refreshments as well? And just because we're disbanding the panel doesn't mean that these discussions shouldn't continue. Of course, this is just the seeds for more discussion during the final break and hopefully in the coming months.
So we have a lot of thank yous because this meeting was a tremendous amount of work. And we had multiple tries at getting it done. So again, I'm just so pleased that we were able to be here in person. I really want to thank everyone for attending. But of course, behind the scenes for 4 years, we've been working on this conference. I really want to thank Nare for suggesting this conference and for continuing to persevere to have the conference going forward. It's been fabulous, and I'm so glad that we were able to do this. Okay. Well,
Want to check that out? Ah, okay. Thank you. Thanks to everybody who braved the trek. It was quite a challenge to get here, and there was a lot of anxiety, but most of us are here. Encourage you to be safe, right? As we go back home, we still have plenty of tests outside. So please give yourselves a round of applause. And also our youngest attendee. We are indeed seeding the future astronomers for Gemini. That's Jian's son, yes? Is he here? Okay, and then, Brett? Thank you to everybody who participated online. There's still a few people online, even though it's very late where they are. And they deserve a special shout out. Thank you. If you want to unmute your video, we can clap for you. It really takes a village, as Jen was saying, to organize this kind of conference. And we will certainly forget people who have contributed through the full scale of whatever distribution function you want to think of this as. If you have contributed to this meeting as an organizer for preparation, please stand up. And this is not just the LOC. I know many of you, including chairs, virtual chairs, in-person chairs, people who have taken pictures, please stand up so we can recognize you. Come on, don't be shy.
LC, SLC.
LOC.
So I'd like to start with the LOC. First of all, I'd like to thank Hui Kim, who is the co-chair of the LOC, and Ann Jordan, who also was co-chair and served as our administrative support. Please come up. Please come up. We have presents. I also want to thank, oh yes, so we have special presents flown all the way from Hilo, from Big Island Candies. If Ji Yeon-sol could also come up, she's a key member of the local organizing committee, of course, our support from the Cassie and the Korea Gemini office.
She did a lot of heavy lifting on Kashi's side.
And we also have a gift for Nara Huang, who is the brains behind the whole thing.
Well, my job was actually to make sure everybody in LOC do their job, but every member of the LOC was perfect and excellent. So there was very little for me to left to take care of anything. So I'm not sure I'm deserved for this.
Okay, other members of the committee. So Chung Yang, are you here? Yes, please come. Jocelyn Ferrara, who gave a fantastic talk on diversity and equity and inclusion. Yijin Kim.
Eugene is sitting outside.
Yeah. Okay.
Songchar took this photo.
Venu Kalarai, who I believe is online, but gave a fantastic talk. And we'll have to ship his, send it back to Chile with someone. Jong Un Hyo, are you here? Please come up. Ki Young Oh.
Oh, she
She
left
okay.
already.
Okay.
Yeah.
Jerry Brower, our fearless tech support. Thank you, Jerry. I think I got all the names. Did I forget anyone, Janice? No. Okay. Nara, would you like to say some final words?
Yeah. Thank you all. I think you guys of course, the LLC members did a hell of a job. And of course, we have to remember that there are many excellent SLC members, including our SLC chair, Elliot, who magically didn't forget to make me an invited speaker even after 3 years. So let's thank our SLC members and all of you, and to make a travel here and also attending this meeting virtually. So you guys made this meeting a big success. Thank you. And let's also thank our excellent hotel staff who made our coffee break time a great joy. I never had this kind of excellent tea and coffee service wandering around the world attending meeting. Thank you. 호텔 스태프분들이 계신지 잘 모르겠지만 감사드립니다. 여러분들 고생하신 덕분에 편하게 잘 미팅하고 갑니다. 감사합니다.
Okay, with that, we are done. Please enjoy the rest of the coffee, and hopefully many of you will get to spend the weekend seeing the sights. Thanks again.
Thank you.
We did it.
We did it. We did it.